Thank you all. Now, I humbly invite the dignitaries of the today's function, Professor Indranil Manna, Dr. S.B. Nakhe, Dr. S.K. Majumdar, Sri R.C. Mittal, Dr. D.K. Patnaik, Dr. V. Ganeshan, and Dr. C.P. Pal onto the dais. I request the convener, co-convener, organizing secretary to escort the dignitaries to the dais, please. Thank you, sirs. This is our privilege to have the eminent dignitaries with us on the occasion. It is your immense pleasure and sincere duty to welcome the dignitaries on the dais. Now I request Dr. S. Satpathy, convener of NLS 33, to welcome our chief guest, Professor Indranil Manna, with a floral bouquet. I request Ms. Vaisali to hand over the floral bouquet to Dr. Satpathy. I request Dr. A. Koser, co-convener of NLS 33, to welcome our guest of honor, Dr. S.B. Nakhe, with a floral bouquet. I request Ms. Shruti Vyas to hand over the floral bouquet to Dr. Koser. I request Dr. Preeti Jain, Organizing Secretary 2 of NLS 33, to welcome the President of Indian Leisure Association, Dr. S.K. Majumdar, with a floral bouquet. I request Ms. Aarti Pathak to hand over the floral bouquet to Dr. Jain. Again, I request Dr. Satpathy to welcome Sri R.C. Mittal, Chancellor of Medicaps University, with a floral bouquet. I request Ms. Aparna Divedi to hand over the floral bouquet to Dr. Satpathy. Again, I request Dr. Koser to welcome Dr. D.K. Patnaik, Vice Chancellor of Medicaps University, with a floral bouquet. I request Ms. Priya Yadav to hand over the floral bouquet to Dr. Koser. Again, I request Dr. Preeti Jain to welcome Dr. V. Ganeshan, Chairman of Local Organizing Committee of NLS 33, with a floral bouquet. I request Ms. Rupali Joshi to hand over the floral bouquet to Dr. Jain, Dr. Ganeshan. Further, I request Dr. Koser to welcome Dr. C.P. Pal, General Secretary 2 of Indian Leisure Association, with a floral bouquet. I request Ms. Priya Dangi to hand over the floral bouquet to Dr. Koser. Thank you, Dr. Satpathy, Dr. Kwesar, and Dr. Jain. Thank you, Baisali, Shruti, and the team. As per the tradition, before beginning of any program, we invoke the blessings of Goddess of Wisdom and Knowledge, Devi Saraswati, by lighting the lamp and offering prayer. Now, I invite the chief guest, guest of honor, and other dignitaries on the dais for lighting the lamp and seeking the divine blessings. Thank you, sirs. Now I invite Dr. Prachi Sathe and her team for Saraswati Vandana.
या कुन्देन्दुतुषारहार धवला या शुभ्रवस्त्रामृता या वीणावरदण्डमण्डितकरा या पद्मासना या ब्रह्माच्युत शङ्कर प्रभृतिभिः देवैः सदा वन्दिता सा मां पातु सरस्वती भगवती निःशेषजाड्यापहा शुक्लां ब्रह्मविचारसार परमा आद्यां जगद्व्यापिनीं वीणापुस्तकधारिणीम् अभयदां जाड्यान्धकारापहां हस्ते स्फाटिकमालिकां विदधतीं पद्मासने संस्थितां वन्दे वां परमेश्वरीं भगवतीं बुद्धिं प्रदां शारदां बुद्धिं प्रदां शारदां बुद्धिं प्रदां शारदाम्.
Thank you, Dr. Sathe and the team. Moving ahead, now I invite Dr. S. Satpathy, convener of NLS 33, for his opening remarks. Dr. Satpathy.
Thank you, Dr. Ramakant. Good morning, esteemed chief guest, Professor Indranil Manna, distinguished guest of honor Dr. Shankar V. Nakhe, President, Indian Leisure Association, Professor Shobhan Kumar Bajondar, esteemed Chancellor of Medicaps University, Sri R.C. Mittal, Vice Chancellor of Medical University, Professor Dilip K. Patnaik, Secretary, Indian Leisure Association, Professor C.P. Paul, Chairman, Local Organizing Committee, Professor V. Ganesan, Co-Convener, Dr. A.A. Kosar, Organizing Secretary, Dr. P.T. Jain, and entire assembly of senior colleagues from RRCAT, DAE, faculty member of Medicaps, and other institutes across India, ladies and gentlemen, most importantly, dear participants. It is my absolute honor and privilege to welcome you all to 33rd National Leisure Symposium, which is a gathering of brilliant minds, innovative thinkers, passionate leaders, working in various disciplines related to leisure. The National Leisure Symposium, a distinguished 4-day-long annual event of the intense scientific deliberations, continues its long-standing traditions of fostering scholarly discourse and spreading cutting-edge research in the domain of leisure science and technology, and their applications by bringing together leading leisure laboratories and academic institutions across India. Since its beginning at IIT Madras in 1992, this annual gathering has traversed the length and breadth of India and has served as a pivotal forums for exchange of knowledge and promotions of collaborative endeavors among researchers, academics, and industry professionals across India. NLS 33, being held in Indore, the cleanest city of India, provides a platform for the presentations and discussion of advancements spanning a broad spectrum of leisure-related disciplines, including but not limited to leisure physics technology, material science, and their applications in nuclear science, chemistry, and biology. To include the transformative influence of the machine learning and artificial intelligence, a new category, machine learning and AI in leisure applications, has been introduced since last year to align with the global trends. Medicaps University Indore, the host institute of this year's NLS, is a premier private university under UGC. It is dedicated to research and development in the field of the science and engineering. Like previous years, this year also, overwhelming responses from the authors of the different parts of the country has been received, and in the form of the contributory papers and the PhD thesis. A total 10 have been out of 236 papers received this year. Additionally, 12 PhD theses have been received for the presentation by research scholars, which is an important part of the symposium, providing the budding scientists a platform to showcase their work carried out in the fields of the leisure science and technology. Out of these, some of these theses will be awarded by Indian Leisure Association. To foster a robust interface between academia and industry, and industrial exhibitions organized by Indian Leisure Association will run concurrently with the symposium, featuring the 22 industrial partners and their international principals. These exhibitions will provide an extraordinary platform for the industry participants to showcase their products and present the latest global developments in optics and lasers. The successful exhibitions of the symposium of this magnitude necessitates the concerted efforts of numerous dedicated teams. We are privileged and honored to have Professor Indranil Manna, a distinguished scientist, Vice Chancellor of Birla Institute of Technology, Mesra, as the chief guest of the symposium. He has also agreed to deliver the keynote address in the inaugural sessions of the symposium. It is our privilege to have Dr. Shankar V. Nakhe, distinguished leisure scientist and former director of RRCAT and former president of Indian Leisure Association, as the guest of honor of this symposium. There will be the special evening lectures, which will be delivered by Professor Jaypal Mittal, former director of Chemistry and Isotope Group, Bhabha Atomic Research Center, Mumbai, a highly accomplished scientist who has made seminal contributions to the fields of photochemistry and radiochemistry. We extend sincere appreciation to all the 22 eminent scientists who accepted our request to deliver invited talks on different aspects of the leisure science and technology during symposium. I am sure all the delegates are looking forward to those talks. The organizing committee expresses its profound gratitude to Sri Unmesh D. Malse, Director RRCAT, for his unwavering support and guidance. We extend our heartfelt appreciations to Dr. R.C. Mittal, Honorable Chancellor, and Professor Dilip K. Patnaik, Vice Chancellor of Medical University, for their invaluable support in hosting the symposium. We are deeply indebted to all the individuals who have contributed to the organizations of the NLS 33. Our gratitude extends to the members of National Advisory Committee, the Symposium Organizing Committee, and local organizing committee for their interest, support, and valuable suggestions. We are also grateful to the referees for their diligent efforts in reviewing manuscripts, ensuring the high technical standards of NLS 33. Last but not the least, we express our profound appreciation to BRNS for their invaluable support in providing full funding for the symposium. On behalf of organizing committee, we extend a warm welcome to all the participants, including postgraduate students, doctoral candidates, faculty, scientists, and industry representatives, and wish them a scientifically enriching and enjoyable symposium. With that, I officially declare the National Leisure Symposium open. Let us make the most out of this opportunity, embrace the new ideas, and work together towards the brighter, more informed future. Thank you. Let's begin.
Thank you, Dr. Satpathy, for providing an overview of various facets of the symposium, that is NLS 33. Now I invite Dr. A. Koser, co-convener of NLS 33, for his remarks. Dr. Koser, please.
A very warm good morning to honorable members on dais. Our chief guest for today's event, Professor Indranil Mane, distinguished guest of honors, Dr. S.V. Nake, Honorable Chancellor of Medicaps University, Sri R.C. Mittal ji, Vice Chancellor, Dr. Dilip Patnaik sir, then President of Indian Laser Association, Professor S.K. Majumdar, and Secretary, Dr. C.P. Paul, convener of this event, Dr. Satpathy, Dean of Research Affairs, Medicaps University, Dr. V. Ganeshan, and organizing secretary of this event, Dr. Ramakant Biswal and Dr. Preeti Jain. And of this, I would like to greet OSD to Chancellor, Mr. Palas Garg, Management Trustees, Honorable PVC, professors from RRK, Medicaps University, and other universities, and dear participants from various organizations. It is my privilege to extend a warm welcome to all to Medicaps University for this 33rd National Laser Symposium, one of the most prestigious events for scientists and researchers working in the field of lasers and allied sciences. We are truly fortunate to host this esteemed event at our university, and we express our sincere gratitude to BRNS, the Indian Laser Association, RRK, and other sponsors for their support in making this possible. I assure all the participants and dignitaries that you all will feel that you are not away from home during these 4 days of your stay. Medicaps University and RRK are committed to making your experience both memorable and enriching. Medicaps University has been imparting quality education for last 25 years, and this year we are celebrating our silver jubilee. We take immense pride in organizing such prestigious event during this significant milestone. Our lush green campus is home to approximately 12,500 students, 350 research scholars, 980 staff members, and 29,000 alumni with 8 faculties across 19 departments. We are accredited with A grade by NAC and approved by UGC, AICTE, BCI, PCI, and MPPURC. While academic excellence is our priority, we also place a strong emphasis on research. Over the past 3 years, our faculty members have published approximately 750 research papers in Scopus and Web of Science. This translates to around 250 papers per year. And if I go more micro level, then it is around 1 paper per working day. We have also many projects in line, funded by DST and MapCost. We are privileged to be surrounded by leading institutes like IIMs, IITs, and research organizations such as RRCATE. We firmly believe that events like this symposium will accelerate our research initiatives, benefiting our faculties, research scholars, and students by enabling them to gain valuable knowledge from esteemed keynote speakers and engage them in fruitful discussions. They will also have the opportunity to make use of advanced scientific facilities at DAE and other prestigious institutes. The networking opportunity provided will undoubtedly help them excel in their research and broaden their intellectual horizons. Such symposium offers a unique platform for researchers to share their latest findings, networks with peers from various institutions, foster calibration, and engage in critical discussion on emerging topics. This event also plays a significant role in enhancing the visibility and impact of scientific research, making it accessible to a broader audience, including policymakers and the general public. In conclusion, I look forward to witnessing a remarkable exchange of ideas and insights that will illuminate the frontiers of the laser field. Let us continue to build upon the spirit of collaboration as we strive to advance knowledge and address the challenge that lie ahead. Thank you, and I wish you all a rewarding and enriching learning experience. Jai Hind, Jai Bharat.
Thank you, Dr. Koser, for providing a glimpse of the host institute, that is Medicaps University, Indore. Indian Laser Association, that is ILA, is the collaborator and coordinator of the National Laser Symposium. As the president of Indian Laser Association, Dr. S.K. Majumdar is the chief architect and principal planner of the symposium, who has led us from the front. Now, I invite Dr. S.K. Majumdar for his ILA executive address. Dr. Majumdar, please.
Good morning. Thank you, Dr. Biswal. Distinguished chief guest, Professor Indranil Manna, Vice Chancellor of Birla Institute of Technology, Mesra. Esteemed guest of honor, Dr. S.B. Nakhe, distinguished scientist and former director of RRCAT, and also former president of Indian Laser Association. Respected Sri R.C. Mittal, Honorable Chancellor of Medicaps University. Professor Dilip K. Patnaik, Honorable Vice Chancellor of Medicaps University. Professor V. Ganeshan, Dean of Research Affairs of Medicaps University and Chairman of Local Organizing Committee of NLS 33. Dr. Srinivas Satpathy, the convener of NLS 33. Professor Koser, the co-convener of NLS 33. Dr. Ramakant Biswal, the Scientific Secretary of NLS 33, Professor Preeti Jain, the Organizing Secretary of NLS 33 from Medicaps University, Dr. C.P. Paul, the General Secretary too of Indian Laser Association, distinguished guests, learned scientists, respected faculty members of Medicaps University, Sri Tushar Puntambekarji, the Additional Director of RRCAT, my senior and junior colleagues of RRCAT, my dear students, valued industry partners, and ladies and gentlemen. A very warm and hearty welcome to the 33rd DAE-BRNS National Laser Symposium here at the beautiful campus of Medicaps University in the cleanest city of Indore, India, that is Indore. It is indeed a great honor and pleasure for me as the President of Indian Laser Association to stand before you today at the commencement of this prestigious event. The National Laser Symposium, or NLS as it is fondly known, represents not merely a gathering of experts, but a confluence of bright minds dedicated to the exploration and advancement of light-based technologies. Its history is a testament to the enduring power of collaboration and the relentless pursuit of scientific excellence, a history in which the Indian Laser Association has played an integral and pivotal role. This symposium is a hallmark of our scientific calendar and represents a culmination of decades of dedicated research, and that's why it is a testament to the vibrant laser community of India. The genesis of National Laser Symposium, as Dr. Satpathy indicated, can be traced back to the year 1992 at the prestigious Indian Institute of Technology, Madras. From its inception, it was envisioned as a platform for the dissemination of cutting-edge research, a forum for the exchange of ideas, and a catalyst for collaborative endeavors in the rapidly evolving field of laser science and technology. Over the past 3 decades, NLS has traversed, as Professor Satpathy indicated, the length and breadth of our vast nation, leaving an indelible mark on the scientific landscape of India. It has served as a crucible where groundbreaking discoveries have been unveiled, where nascent ideas have been nurtured, and where enduring partnerships have been forged. The Indian Laser Association, from its very inception, has been a driving force behind the remarkable trajectory of NLS. We have been steadfast in our commitment to ensuring that this symposium remains a premier platform for the exchange of knowledge and the advancement of laser science and technology. Our dedication stems from a deep-seated belief in the transformative power of light and the potential to address some of the most prestigious challenges the humanity is facing. This year, in collaboration with Medicaps University, we are delighted to bring NLS to Indore, a city renowned for its cleanliness, its rich cultural heritage, and its growing scientific community. Under the aegis of Board of Research in Nuclear Sciences, that is BRNS, the funding arm of our Department of Atomic Energy, we have curated a program that reflects the dynamism and breadth of laser research today. We are profoundly grateful to BRNS for their unwavering support, without which this symposium would not have been possible. Their generous funding has been instrumental in enabling us to create a stimulating and enriching environment for all the participants. For those of you who are new to the Indian Laser Association, let me take a moment to illuminate our organization's journey. The Indian Laser Association was founded with a singular, powerful vision, that is to cultivate and advance field of laser science and technology within India. From its inception, the ILA has served as a pivotal nexus for knowledge exchange, fostering collaboration amongst researchers, academics, and industry professionals. We are driven by a profound commitment to education, to pushing the boundaries of laser applications, and to ensuring that India remains at the forefront of this dynamic field. A cherished tradition of ILA has been organizing pre-symposium courses preceding each National Laser Symposium. We believe that empowering the next generation of laser scientists and engineers is paramount. These courses are meticulously designed to offer students and researchers invaluable insights into the latest advancements in laser science and technology. And we are extremely proud that these courses are taught by renowned faculties and scientists who are true experts in their field of research. This year also, ILA organized 2 pre-symposium short courses. One is Advanced Solid State Laser Technology, and the other one is nanophotonics using structured light on the 4th and 5th of March at RRCAT Convention Center. These courses, each one led by luminaries in their respective fields, provided in-depth training and hands-on experience to our students and researchers. For the Advanced Solid-State Laser Technology course, we are incredibly fortunate to have the expertise of 5 distinguished scientists from RRCAT, Dr. B.N. Upadhyay, Dr. P.K. Mukhopadhyay, Dr. C.P. Singh, Dr. Pradeep Kumar Gupta, and Sri Amarjit Singh. Their collective knowledge and hands-on experience in solid-state laser technology are truly remarkable, and we are deeply grateful for their commitment to sharing their insights. Similarly, for the nanophotonics using structured light course, we were honored to have Professor Nirmalia Ghosh of IISER Kolkata, who is a globally recognized authority in photonics, and he was the course coordinator of this course. The ILA, in this way, is dedicated to providing this kind of educational opportunities, ensuring that our community remains at the forefront of laser technology. The ILA's commitment to excellence is also reflected in the selection of our distinguished speakers. We are deeply honored to have Professor Indranil Manna, an eminent scientist in the field of material science and engineering, deliver the keynote address today, which this time is featuring 22 of our valued industry partners, and their international principles serves as a crucial bridge between academia and industry. It provides a unique and invaluable opportunity for researchers and students to witness firsthand the latest advancements in laser technology, and for industry professionals to showcase their cutting-edge products and solutions. As Dr. Satpathy mentioned, the success of NLS 33 is a testament to the collective efforts of numerous individuals and organizations. We are immensely grateful to the Board of Research in Nuclear Sciences, the Department of Atomic Energy, and Medicaps University for their unwavering support and collaboration. Their partnership has been invaluable in making this symposium a success. We extend our heartfelt appreciation to Sri R.C. Mittal and Professor Dilip K. Patnaik, the Honorable Chancellor and Vice Chancellor of Medicaps University, for their invaluable support in hosting the symposium. We also extend our heartfelt gratitude to all the members of the National Advisory Committee, the Symposium Organizing Committee, and the local organizing committee, whose tireless efforts have made this event possible. And a very special thanks to all the reviewers who have worked so hard to maintain the high quality of the papers presented. And last but not the least, we extend our profound gratitude to our Honorable Director, Sri Unmesh Malsheji, who is also the Chairman of the Symposium Organizing Committee, for his unconditional support and guidance in organizing the symposium. He is not present here today because of his prior commitments, but in a WhatsApp message this morning, he has conveyed his warmest greetings to all the participants of the symposium and wished a grand success of NLS 33. To each and every one of you, I extend my warmest wishes for a truly enriching and memorable 4 days. Let's engage in meaningful discussions, spark new collaborations, and propel the field of laser science to even greater heights. We trust that the knowledge shared and the connections forged here will have a lasting impact on your research and careers. The Indian Laser Association is here to support you every step of the way. So let's begin this journey together. So let's make National Laser Symposium 33 a resounding success right here in Indore. Thank you and Jai Hind.
Thank you, sir, for your insignificant and significant and proactive guidance and planning the various events of the symposium and outlining various roles of Indian Law Association in general and that of in NLS 33 particular. Now, Dr. C.P. Pal, General Secretary 2 of Indian Leisure Association, is coordinating the symposium on the ground through his meticulous planning, out-of-box thinking, and multitasking ability. Now, I invite Dr. Pal for his remarks.
Distinguished Chief Guest, Professor I. Manna, the guest of honor, Dr. S.V. Nake, Shri R.C. Mittal, Chancellor of Medicap University, Professor D.K. Patnaik, Vice Chancellor, and other dignitaries on the dais and off the dais, respected colleagues and bright minds here of the laser community, a warm and enthusiastic welcome to NLS 33, right here at the cleanest city of the India, Indore. It is a privilege to stand before you today as a General Secretary of Indian Laser Association, marking the beginning of another significant chapter in our journey of over 4 decades. The ILA has been a beacon of innovation and illuminating the path of laser science and the technology in India. I would like to begin by expressing my sincere gratitude to the Chancellor Shri Mittal and Vice Chancellor Professor Patnaik for readily agreeing to host NLS 33 at Medicaps University and extending the wholehearted support for making this event a grand success. This is the 4th instant when NLS is being hosted at any private university. NLS 33 is not a just symposium, but it's a converging of visionaries and crucible of the ideas and a testament of the transformative power of the light. We are gathered here to explore the frontier of laser technology, to share our discoveries, research, and to ignite the spark of collaboration that will propel us forward. As we delve into the rich tapestry of presentation and discussion, let us remember the profound impact that laser has made in our life. From revolutionizing the medical diagnostics to empowering advanced manufacturing, lasers are shaping the world around us. And we look ahead, we see a future where India stands at the forefront of technological innovation, a future where our Indian is a leader in the laser research and application. The vision resonates deeply with the spirit of Make in India. We are committed to fostering an ecosystem where Indian ingenuity thrives, where our industries are powered by the indigenous laser technologies, and where we reduce our dependency on foreign sources. To realize this vision, India has been actively pursuing several key initiatives. We see the ground of the centers of excellence dedicated to the photonics and the laser research across our prestigious institutions. Initiatives like National Quantum Mission with a focus on quantum technologies, including laser-based systems, are the pivotal in this effort. Programs supporting the development of laser-based medical devices, advanced material processing and manufacturing, and laser communication systems are gaining momentum. We encourage active participation in these initiatives, ensuring that Indian researchers and industries are at the cutting edge of the global technology. Further, I encourage you all to explore the ILA Industrial Exhibition, which showcases the latest advancement in the laser technology from both Indian and international companies and their principals. This exhibition serves as a vital bridge between research and the industries, providing a platform for the business to showcase their innovative products and for research to witness cutting-edge application. It is tangible demonstration to how laser technology is being translated into the real-world solution and a chance to support the Make in India initiative through interaction with Indian manufacturers. But our aspirations are beyond the self-reliance. We are driven by the dream of developed India by 2047, a nation where technology empowers progress, where innovation thrives prosperity, and where citizen has opportunity to thrive. Laser technology is a vital instrument in building the future. The work we do here, the ideas we generate here, the collaboration we forge here will combine directly to realizing the mission of the developed nation by 2047. Recently, Department of Atomic Energy has established 4 incubation centers, including AIC Pi Hub at Rajaramanna Center for Advanced Technology. AIC Pi Hub is focused on the technology translation to Indian industries and startups using RRCAT developed technologies, know-how, and expertise. Let us embrace the challenge, let us push the boundaries of the knowledge, and let us work together to harness the power of the light for the betterment of our nation and the world using the light technology available with us. I extend my heartfelt gratitude to colleagues from Medicaps University and RRCAT for the dedicated efforts in organizing this wonderful event here, our sponsor for providing the support, and everyone who has contributed to making NLS33 a reality. Your dedication made this gathering possible. May this symposium be the catalyst for the innovation, a platform for the collaboration, and a stepping stone towards a brighter future. I wish you all productive and inspiring NLS33. With this, I stop here. Thank you very much. Jai Hind, Jai Bharat.
Thank you, Dr. Paul, for kindly shouldering several mammoth tasks associated with the symposium and providing an outlook of the ILA activities and NLS 33. As chairman of local organizing committee, Dr. V. Ganeshan is the key person behind coordinating the activities at the host institute as well as with Indian Laser Association to ensure smooth and successful execution of the symposium. Now, I request Dr. Ganeshan for his remarks.
Vanakkam. Narmade Sindhu Kaveri Jalesmin Sannidham Kuru. Kaveri Tungapadrasya Krishnavenya Bhagirathi Gangecha Yamuna Saraswati. This is a Vedic saying that every day we do. National integration, nothing can be more than that. And it is a confluence of water tribunal that was taught. Civilizations have been growing across the water bodies. When the civilization mix, the culture mix, knowledge just flows. So this gathering is one step ahead that of the, in the as far as knowledge base is concerned, for the Mahakumbh just concluded. Number 2, whatever I am speaking is not for any of the stalwarts here. This is just for our very young research scholars who want to do some research and do. Another Indian knowledge contribution that we have is very fantastic quantum statistics called Bose-Einstein characteristics. The contribution of Bose or boson is very, very special. And when people work on low temperatures for a long time, we were thinking that superfluidity is one of the examples, but that's interacting boson. So people have to wait for 80 years to get a beautiful laser cooling and then Bose-Einstein condensate. And just in the millennium, 3 Nobel Prizes have been given for that. That gauges how important is the laser, apart from our own very interesting areas of additive manufacturing and all the way simple ordinary layman can know cataract surgery and many things. That's very wide research. But I request if there is any small a kind of spark within our research scholars, so that I can foresee them very great scientists in the future, I will be successful in conducting such a big conference here. And very important, he said, today is a Guruvar. So it's very important when 2 days before, when Professor Marsha inaugurated the pre-conference lecture series, very beautiful lecture series. I am not fortunate this time to listen all of the lectures, but then they are really good teachers, and next full batch of good teachers are going to give series of lectures in this, and I request all our students to kindly make use of it. And the gentle and very warm greetings by Professor Marsha in conducting this is really memorable. Third is very important is that it is about roughly 4 decades of interaction with DAE and 4 years of interaction with Medicaps, and in between I am just a small hairline bond, but then it catalyzes this event very nicely. I don't know how to express my gratitude, but it's made really happen. And then I'm not supposed to welcome, I'm not supposed to acknowledge, I'm not supposed to talk on laser, which is really not good to talk. I'm not an expert in laser, what to talk? So then one of my friends here asked me, why it's Medicaps? Just we celebrated the Valentine's Day, when 2 days away Women's Day is there, I've been telling. So it is very special. I renamed my department as a research affair. If you keep research as your affair, you will be seeing that Valentine every day. Second, why Medicaps? Medicaps is a very beautiful 25-year beautiful girl. Okay, so Prithviraj will definitely come here and do something very special for us. And we are very interested, very eager to do that. And we are very grateful to all the dignitaries. And finally, how it happens, I just wanted to tell. It just, I love chemistry, even though I'm a physics person, especially from 2-second chemistry is very beautiful. I know what is the interaction. When this proposal, I just as a casual discussion with my friend Majumdar, and then it immediately catalyzes. It's called Majumdar-Patnaik chemistry, with all due regards to all elder people, which is a fraction of a second. Then it all went on, and then you see, this is very nice chemistry. It's an endothermic reaction. It absorbs a lot of heat and energy. So the problem is with me is that when we want to do that, we have to pump in a lot of energy, and then that's where the Paul has come here. And then at some point of time, it is so much active. I will say it's hyperactive. One side, and the other side, Medica's people 125 and odd volunteers, and our cat 125 volunteers. In between, there is a beautiful exhibition called Scrimia. So much things are going on around me. I'm just sitting in the front without doing anything. It has no moment. So I don't know what to do, but everything went on so nicely. The Prithviraj finally came, and we have a very nice event which is happening here. So I'm very grateful to you. And finally, I don't want to tell anything. I remember Professor Manna, when we started UGC DAE Consortium Research Kalpakam node. I remember you came all the way. Whenever we start a small research in the consortium, at that time Professor Chaddan Baldevraj was there inviting you, stayed for more than 3 days to culminate a Bush center. It's now become a center now. It's very important. And then I also know Professor Nake. And finally, the faith which our Chancellor, Vice Chancellor, and the entire team has laid on me that we can do some good quality research. Something is realistic, we can make it. I don't want to talk that in entire research has been told by Kosar and Priti Jain, therefore he will be talking acknowledgements. I am not here just to say the names or everything, but it is a very distinguished academic gathering. There is no age bar, there is no distance, there is no regional bar, but then this knowledge is going to mix it here in this confluence. I missed the Mahakumbh, but now I am very happy to be in this knowledge Kumbh, and I am very grateful to all of you. Nothing I can say, and one of my very, very quantum particle I call Vijay, he says that what to do? I am not able to do anything, I am very tense. Sir, just, he puts his hand, bless me. Dhanam Agnit, Dhanam Vayu, Dhanam Suryo, Dhanam Vasuhu, Dhanam Indro, Brahaspatir Varunam, Dhanamastute. Dharam is not the money, it is the wealth, especially the good health. I wish all these volunteers a very long life and very cheerful, doing very scientific thinking. I am not a religious man, but I take it Indian knowledge system to a little bit different heights. I am very grateful for you, for all the dignitaries, the dais, off the dais, everything, and I foresee a very nice academic gathering. Thank you very much.
Thank you, sir, for being a bridge between the host institute and Indian Laser Association for smooth conduct of the symposium, and thank you for your mesmerizing remark. Sri R.C. Mittal, Chancellor of Medicaps University, is the principal guiding force behind the symposium, who envisaged, enthusiastically proposed, and generously leveraged the facility to host the symposium. Now, I invite the Chancellor for his address.
Good morning to all. Honorable Chief Guest Professor Indranil Manna, our respected guest of honor Dr. S.V. Nakhe, President of ILA Dr. Shovan Majumdar, General Secretary of ILA Dr. C.P. Paul, Vice Chancellor Medical University Dr. D.K. Patnaik, Convener of NLS Dr. S. Satpathy, Co-Convener Professor A. Kosar, Chairman of the Local Organizing Committee Professor V. Ganeshan, Organizing Secretary Professor Preeti Jain, Scientific Secretary Dr. Ramakant Biswal, and distinguished guest. A very warm and cordial welcome to all of you. I also extend a warm welcome to our resource persons, speakers, scientists, participants, and everyone present here today. We are excited to be part of this intellectual journey with you over the next 4 days. Medicaps University, founded in 2000, is known for its high academic standards, discipline, and dedication to research and technical advancement. From its humble beginning, Medicaps has grown into an institution recognized not for just its academic excellence, but also for its focus of cutting-edge research. We have always believed that a university must serve as a hub of innovation and technical advancement, and we are proud to host this event, which perfectly aligns with our mission. This year, we have the privilege of bringing together some of the brightest minds from the field of laser science, and I am confident that the discussions, lectures, and interaction over the next 4 days will be intellectually stimulating and enriching for all involved. This symposium is not just an opportunity to share knowledge, but also a platform to forge partnership, discuss emerging trends, and tackle the challenges we face in advancing laser technology. We hope that the sessions and interactions will lead to groundbreaking ideas and inspire new paths for research and innovation. As you immerse yourself in the proceeding, I encourage all of you to enjoy the beautiful and vibrant atmosphere of our campus and the city of Indore. We are committed to ensuring that your stay here is comfortable, and we hope you will find both the academic environment and the hospitality at Medicaps University conducive to your learning and growth. Once again, I extend a heartfelt welcome to each one of you. May this 33rd National Laser Symposium be a resounding success, and may the next 4 days be filled with fruitful discussion, insightful presentation, and lasting collaboration. Thank you, and I wish you all a wonderful and inspiring experience here at Medicaps University. Thank you. Thanks a lot.
Thank you, sir, for your support to host the symposium at your vibrant campus of Medicaps University. As Vice Chancellor of the host institute, Dr. D.K. Patnaik coordinated all the activities dynamically and enthusiastically by ensuring the availability of resources from the host institute and guiding at every stage of the preparation. Now, I request the Vice Chancellor for his address.
Thank you, Dr. Biswal. Honorable Chief Guest, Professor Indranil Manna, respected guest of honor, Dr. S.B. Nakhe, respected Dr. Patambekar, Additional Director, RRCAD, Honorable Chancellor of Medicaps University, Sri R.C. Mittal, President of ILA, Dr. Shovan Majumdar, General Secretary, Dr. Convener, Dr. S. Satpathy, Co-Convener, Professor A. Kosher, Chairman of Local Organizing Committee, Professor V. Ganeshan, Organizing Secretary, Professor Preeti Jain, Scientific Secretary, Dr. Ramakant Biswal, distinguished speakers, scientists, researchers, participants, and esteemed guests. A very warm welcome to all of you. It is an honor to have you here for the 33rd National Laser Symposium at Medicaps University. Hosting this prestigious event is a moment of great pride for us, and I'm deeply honored to address this esteemed gathering today. Medicaps University was founded in the year of 2000 with a vision to create an institution that excels in academics, fosters innovation, and promotes groundbreaking research. Over the years, we have grown into a vibrant community of over 12,500 students and 550 faculty members who work together to create an environment driven by knowledge, discipline, and excellence. When I remember discipline, discipline is at the core of very successful endeavor. Our motto, Sikkha bhi, Sanskar bhi, education along the values, reflects our commitment to nurturing individuals who not only possess knowledge but also uphold strong ethical values. In the same way that laser technology focuses energy into a highly precise and powerful beam, discipline helps individuals focus their energies towards achieving greatness. Speaking of focused energy, the concept of laser can be beautifully illustrated through an ancient text of Mahabharata and Bhagavad Gita. In Mahabharata, Arjuna's unwavering focus on the eyes of the fish during the Draupadi's Swayamvar is an excellent example of precision, much like how a laser beam is directed with an accuracy towards a target. Just as Arjun ignored all the distractions and concentrated solely on his object, laser technology harnesses light waves and channels them into a singular, powerful beam for maximum impact. Medicaps University is honored to be one of the 22 universities in India awarded the Technology Enabling Center, that is a TEC, by the Department of Science and Technology, DST, Government of India. This recognition empowers us to support local industries with technological advancement and research, contributing to the socio-economic growth. Moreover, our incubation center, My Foundation, provides funding up to 10 crore rupees annually to startups, fostering an ecosystem where students and faculties can transform their ideas into the practical solutions. This year, Medicaps University proudly celebrates its Silver Jubilee, making 25 years of excellence in education, research, and innovation. We are stepping into the future. We are excited to announce our goal for becoming a completely AI-enabled university by the end of this year, 2025. Integrating artificial intelligence into our teaching and research will enhance the learning experience and keep us at the forefront of the global education and technology. Our vision to make our students not only industry ready, but also society ready. True education is not just about acquiring technical knowledge, but also about developing the ability to solve real-world challenges. Just as laser technology has revolutionized fields such as medicine, communication, and manufacturing, we aspire to empower our students with knowledge and skills to drive meaningful changes in the world. As we commence this National Laser Symposium, we look forward to engaging in thought-provoking discussions and collaboration that push the boundaries of science and technology. I encourage you all to make the most of this platform, exchange ideas, and explore new frontiers in the field of laser and photonics. To all the participants, speakers, and guests, whether present in person or in online, I extend warm welcome. May these 4 days of the symposium be filled with this insightful learning, innovation, and meaningful connections. Professor Ganeshan has cited something about the Mahakumbh of this. Yes, the Mahakumbh has just completed. Kumbh tak khatam ho gaya hai. और हमें जैसे पता है कुंभ मतलब होता है जब बृहस्पति वृषभ राशि में होता है और सूर्य का प्रवेश जब मकर राशि में होता है तब जाके कुंभ प्रयागराज में होता है। ऐसे अगर यहाँ पे जहाँ आरआर कट होता है और मेडिकैप्स होता है, यहाँ पे ऐसे ही लेजर का महाकुंभ होता ही रहेगा। और ये 4 दिन आपके लिए बहुत सुखद रहो और कुछ सीखने को मिले। बस मैं यही कहूँगा, मुस्कुराइए, आप मेडिकैप्स में हैं। धन्यवाद। जय हिंद, जय भारत।
Thank you, sir, for your beautiful remark and support and coordination to execute NLS 33. We are privileged to have Dr. S.V. Nakhe, a distinguished scientist and former director of RRCAT, as our guest of honor, who has been guiding all of us at RRCAT, not only in the scientific activities, but also in all the organizational aspects. Before I proceed further, I request Dr. Majumdar to introduce the guest of honor to the audience.
I am really privileged to introduce formally Dr. Nakhe to the audience, though Dr. Nakhe doesn't need any introduction to our DAE fraternity. I thank Dr. Bishwal for this opportunity to introduce Dr. Nakhe. So, Dr. Shankar V. Nakhe was the distinguished scientist and a leading laser expert of the country. He was the former director of Rajaramana Center for Advanced Technology, Indore. He is the product of 30th batch of the prestigious BARC Training School, Mumbai. Dr. Nakhe did his bachelor's in electrical engineering from Walchand College of Engineering, Sangli, which is affiliated to Shivaji University, Kolhapur, Maharashtra. He was the first ranker of his batch of electrical engineering, and immediately following the completion of his bachelor's, he joined Meltron Semiconductors Limited, where he worked for 1 year. He got selected in the prestigious BARC Training School, Mumbai, where he did the orientation course in electrical engineering for 1 year. After successfully graduating from the BARC Training School, he joined RRCAT in 1987. Subsequently, he did his master's in engineering science from Indian Institute of Science, Bengaluru. After joining RRCAT, in the course of discharging various departmental responsibilities, both in research and development and in administration, he climbed the rungs to hold various key positions of the department, such as head of Laser Control and Instrumentation Division, director of Laser Group, director of Material Science Group, and finally, the director of RRCAT. Since his joining at RRCAT, Dr. Nakhe has been actively involved in various R&D activities of the center and contributed significantly in the design, development, and utilization of various laser and electronic systems. The major areas of his work have been high voltage power supplies, electronic instrumentation, and control electronics for various laser systems. Dr. Nakhe has made immense contributions in the development of lasers as well as electronics and instrumentation systems intended for strategic applications in the nuclear program of the Department of Atomic Energy. He played a pivotal role in the development of fiber bracket inscription facility at RRCAT, which is being used for the development and specialized sensors in niche application areas of temperature and strain measurements. Under his dynamic leadership, an incubation center was set at Rajaramana Center for Advanced Technology, an Atal Incubation Center, Pi Hub, which is mentioned by Professor Paul, which is a Section 8 company operating under the aegis of Atal Innovation Mission of Niti Aayog, Government of India, was incorporated to translate RRCAT know-how and technologies to Indian industries and startups. The exemplary leadership of Dr. Nakhe has led to development of numerous indigenous technologies for industrial and biomedical applications, and the transfer of these technologies to leading Indian industries, including Tata Motors Limited, Lokesh Machines Limited, V-Fuse, Metal for Manufacturing, Lord Marks Biotech and Research, India. He has provided exemplary leadership to many engineers and scientists of the center so that they can achieve their best and help the center excel in many domains. Dr. Nakhe served as the president of Indian Laser Association, and Dr. Nakhe has to his credit over 100 peer-reviewed papers in numerous national and international journals. He has authored numerous articles in various professional magazines and over 150 papers in different national and international conferences. He has received various awards, including the DAE-BRNS award as group leader, C. Ambashankaran Memorial Award, various other awards, and he has guided numerous MTech students. In recognition of his significant contributions to science and technology, Oriental University Indore has conferred the degree of Doctor of Philosophy in the Faculty of Engineering and Technology honoris causa on Dr. Nakhe in 2021. He was also elected as the Fellow of Indian National Academy of Engineers. Dr. Nakhe was the major driving force behind successful completion of various R&D projects of RRCAT, and under his erudite and motivating leadership, RRCAT has scaled new heights. We are extremely delighted to have him here today as guest of honor.
Thank you, sir, for your introduction. Now I request Dr. Nakhe.
Thank you, Dr. Majumdar, for very kind introduction. Professor Manna, Honorable Chief Guest of today's inauguration function, Shri R.C. Mittal, Chancellor, Medicaps University, Shri D.K. Patnaik, Vice Chancellor, Medicaps University, dignitaries on the dais, of the dais, delegates, industry participants. Very good morning to all of you. And I, at the outset, thank Medicaps University for hosting this prestigious university at this beautiful campus on their silver jubilee year. And I think this is going to be a very memorable event for the university also and for laser community of India also. As you know, National Laser Symposium is a major scientific event where scientists, engineers, technologists, and industry participants interact and take this wonderful field ahead to the service of nation and mankind in general. And that is the motto with which Indian Laser Association is incorporated and contributing in the area of lasers and photonics technologies and sciences. Recently, we have celebrated the National Science Day. And if you remember, this National Science Day's theme is empowering Indian youth for global leadership in the areas of science and innovation. So I think this theme is very much applicable for this symposium also. I think there should be a lot of interactions between scientific, engineering and technological fields and taking this to the service of mankind through industrialization. There are many such success stories that have come out through the interactions at the platform of National Laser Symposium over many years. And every year, these interactions are increasing and we are adding new chapters to this. Of course, there is a well-set pattern for the National Laser Symposium programs, but it is still a dynamic and depending on the evolutions, we are changing this methodology also. As announced earlier, since last year we have added the theme of AI and ML in laser technologies and its applications. This is a very remarkable area, and particularly when we are thinking now for spectroscopy applications or industrial applications, this is going to be a very contributing and driving area because it needs expertise from both the fields, that is core laser or spectroscopy and AI and ML. I'm sure there are number of papers in this area also, and all these interactions will result into a very fruitful output. I think academia, research institutions and industry, if we work together with proper directions, then we can achieve wonders and rise success stories for Viksit Bharat. This is what our former chairman, Dr. R. Chidambaram, has also said, that we should go for a directed research with all these disciplines coming together. Unfortunately, he has passed away in recent past, but we remember his contribution in taking this laser field ahead. And I'm sure with this large gathering here and lectures from trailblazers, stalwarts, bright minds, and young budding scientists here, there will be a lot of scientific interactions, and these interactions will not be limited to this hall. There will be a lot of interaction outside this hall with industry participants and industrial products also that will enhance our understanding and applications of lasers. So I wish a grand success to this symposium, and there will be a very fruitful outcome out of this. And thank you all for participating in this, and all the best from my side. Thank you.
Thank you, sir, for your words of encouragement and advice. Your advices have always shown us the path to tread. We have immense pleasure and privilege to have a distinguished laser and material scientist in the country, Professor Indranil Manna, the Vice Chancellor of BIT Mesra, Ranchi, and President of Indian National Academy of Engineers, as our chief guest of today's function. Before I proceed further, I request Dr. S.K. Majumdar, President of ELA, to introduce the guest to the audience, please.
It's a great honor to introduce our chief guest and keynote speaker today, Professor Indranil Manna. He's a luminary in the field of material science and engineering, and Professor Manna's contributions have profoundly impacted both academia and industry. Professor Manna was born in Kolkata on January 22, 1961. Professor Manna's academic foundation is built upon a strong and diverse educational background, which has been instrumental in his multifaceted career. He commenced his higher education journey by obtaining a Bachelor's of Engineering in 1983 from Calcutta University, that is Bengal Engineering College, demonstrating his early aptitude for engineering principles. He then pursued advanced studies at the Indian Institute of Technology, Kanpur, where he earned his Masters of Technology degree in 1984, specializing in physical metallurgy and achieving top rankings. Solidifying his expertise, he completed his Doctor of Philosophy, that is PhD degree in 1990 from IIT Kharagpur, further deepening his knowledge in material sciences. His professional career began with a short stint at Misra Dhatu Nigam, that is Midhani, in Hyderabad from 1984 to 1985, providing him with practical industrial relevant experiences. This foundation proved invaluable when he joined IIT Kharagpur as a lecturer in November 1985. His tenure there was marked by a steady ascent, culminating in his promotion to full professor in 2003. At IIT Kharagpur, he excelled as both an educator and researcher, making significant contributions to the field of material science. Professor Manna's research interests are broad and impactful, covering critical areas within material science. His work on microstructure property correlations in nanometric and amorphous solids has advanced the understanding of these materials. His pioneering research in laser or plasma-assisted surface engineering has yielded practical applications. Furthermore, his expertise extends to advanced steels and nanofluids, demonstrating his comprehensive knowledge of materials behavior under extreme conditions. His extensive publications record with over 250 journal publications and his mentorship of numerous doctoral students reflect his commitment to advancing scientific knowledge. Transitioning from academia to leadership, Professor Manna has demonstrated exceptional leadership and administrative skills. He has held significant directorial positions at prominent Indian research institutions. His tenure as director of CSIR, Central Glass and Ceramic Research Institute, that is CGCRI, from 2010 to 2012 marked as a period of strategic growth and development for this institute. During this time, he applied his extensive knowledge of material science to advanced research in glass and ceramics. Subsequently, he served as the director of Indian Institute of Technology, Kanpur, from 2012 to 2017. In this role, he provided visionary leadership to one of India's premier technological institutions, fostering an environment of academic excellence and research innovation. These directorships show his ability to manage and lead high-level scientific institutions. Currently, he serves as the Vice Chancellor of BIT Mesra. His involvement in national initiatives like Impacting Research Innovation Technology, abbreviated as IMPRINT, underscores his commitment to translating scientific discoveries into technological advancements. His service on numerous boards and councils further cements his standing as a prominent figure in Indian scientific community. Professor Manna's contributions have been widely recognized through numerous prestigious awards and honors. He is a fellow of all the 3 National Academies of Science and also the fellow of National Academy of Engineering. He has received the World Academy of Sciences, that is Third World Academy of Sciences, that is TWS Prize in Engineering Sciences, and also Honorary Doctor of Science degrees from University of Kalyani and Kazi Nazrul University. He is also a recipient of this J.C. Bose Fellowship of Department of Science and Technology and the Alexander von Humboldt and German Academic Exchange Services, that is DAAD Fellowship, DAT Fellowships. His past presidency at the Indian Institute of Metals and his current vice presidency of Indian National Academy of Engineering and Indian National Science Academy show his high level of respect and influence in the Indian scientific community. Professor Indranil Manna's career is a testament to his unwavering dedication to research, education, and leadership. Having an indelible mark on the field of material science and engineering in India, throughout his career, Professor Manna has maintained a strong connection to academia, continuing to teach and mentor students, even while holding administrative positions. This dedication to education, combined with his research and leadership experience, has made him a highly respected figure in Indian scientific community. So I invite Professor Manna for his address.
Very good morning to all of you. I hope Shobhan has convinced you that you have got a worthy chief guest for today's function. I myself was actually feeling quite embarrassed. Suffice to say that this is my 41st year in the profession, so I have lost all my hair, and I think that should be enough of a reason for getting this opportunity to speak to you today as the chief guest. But I would reserve my technical part for the next half of the function. But at the very beginning, I would like to profusely thank Dr. Shobhan Majumdar, the President of Indian Laser Association, Dr. S.V. Nakhe, the former president of ILA and former director of RRCAT Indore, Mr. R.C. Mittal, the Chancellor of Medicaps University, Dr. D.K. Patnaik, Vice Chancellor of this Medicaps University, rest of the dignitaries on the dais, my esteemed colleagues from this very university, the faculty members, staff members, students and scholars, the delegates to NLS 33, and dear friends. I obviously am greatly honored to be standing before you and shortly be able to share some of my research exploits in laser. You have heard many ways of explaining as to why this conference is so important. But imagine that we are celebrating because of the enormous power and potential of an electromagnetic radiation which was discovered just about 65 years ago. 1960, Theodore Myman first showed the generation of existence of light amplification by radiated emission of, amplified emission of radiation. So this light activation has 4 major characteristics because of which we every year celebrate in India and throughout the world, the entire community of physicists and engineers are so much enamored with laser. Number 1, coherency. Number 2, monochromaticity, almost a single wavelength or very low divergence. The ability to deliver exactly the directed amount of energy onto the desired spot. Now these attributes make it one of the most widely exploited tool over a very large number of applications, very large number of subject domains. The physicists, of course, in fact, if you come to any of the NLS, National Laser Symposium, 80% of the deliberations are related to various exploits in physics. So no wonder that National Laser Symposium is dominated largely and rightly so by the physics community. But there's enormous application in engineering as well. I mean, talking about physics, we can think of starting with spectroscopy, interferometry, atmospheric science, confocal microscopy, various forms of spectroscopic applications. There's enormous application in terms of medical treatments, starting from identification all the way to removal of even large tumors, from cosmetic surgery to cancer therapy. Laser now is very routinely and very extensively used by the medical professionals. And in engineering, you can use it for several applications, starting where you remove material, where you add material, or you treat material. So you can do machining, you can do joining, you can do forming, and you certainly can take care of the surfaces. And the recent buzzword in engineering, application of lasers in engineering, is all related to additive manufacturing, which is what I would like to expound in my lecture. RRCAT being a very major organization of the atomic energy, I'll be failing in my duty if I don't mention the application of laser, not just spectroscopy, but high-power lasers in acceleration and even fusion reactions, which is what's being pursued even in this very country. Then we also have applications for various military purposes, high power laser is something which is not just very common in engineering domain, but also very widely pursued by various institutions and organizations the world over. Shovan mentioned about my association with CGCRI, Glass and Ceramic Research Institute. In fact, I just also made sure that Dr. Nakhe, because he worked on fiber brack grating, so I just made sure that he knows about CGCRI's contribution. In fact, there was a time when CGCRI had a very strong interaction, I'm sure it still continues, with RRCAT and BRC together for developing high power laser, this I think neodymium doped high power laser and YAG lasers, but glass, not garnet, not crystalline. Then we also were involved in developing fiber brack grating, like you just heard the mention about very precise measurement of temperature and dilation. One other application I forgot to mention, the domain of physics and engineering common, is metrology. I mean, you actually can, just because of the coherence and single wavelength, you actually can measure to a precision which is not possible by other tools. So there's enormous application of lasers, and Medicaps University, having engineering as the largest faculty, I'm sure the students and scholars here would be willing to exploit the facility available just next door. RRCAT has one of the finest laser facility. In fact, not this visit, in the last visit, I was shown the additive manufacturing unit they have, both direct energy deposition and powder bed. So the mechanical engineering and hardware engineering discipline students should take advantage of this. Incidentally, that allows me to very fondly recollect I just told about my association with CGCRI, but I should have mentioned that you heard, actually I've been associated with IIT Kharagpur. Even today, I'm on LEN to BIT Misra. And I had the privilege of interacting with truly a pioneer in the field in laser material processing, Professor Bill Steen in Liverpool in 1995, and that's when I first, or maybe 92, I got the first brush with laser applications. Until then, I was a solid state phase transformation guy. So that exposure, little exposure, allowed me to learn a little bit and then also make some forays into the world of lasers. And the very first laboratory which I visited in India after returning from Liverpool was RRCAT. I think that time it was only CAT Indore, not RRCAT. And Dr. Bhabha was the director, one of the stalwarts in the field who I'm sure those of us who are in the field of lasers would always hold him in very high esteem for his contributions to this particular field. And at that point of time, must be in late 90s, A.K. Nath proudly showed me, took me to a workshop and showed me the chamber which was supposed to deliver high power CO2 laser. Maiman discovered laser using ruby, the L203 special variety of crystals. But the ruby laser actually was useful only for certain characterization applications, not so much for material processing. The real high power laser application started with CO2 laser, and there we have reasons to be, especially proud about CO2 laser because CO2 laser was first developed and demonstrated by an Indian based in US though, C.K.N. Patel in 1963, 63 or 65. The RRCAT developed the first CO2 laser, high power CO2 laser in this very campus. And of course, the beam wasn't very stable. And power could be at times kilowatt, at times maybe few hundreds of watts. But that was my first brush with laser. In fact, I came here, camped for 3-4 days with my own PhD scholar to do certain experiments. And I was doing, I mean, any physicist would say that must have been a very foolish idea. I was at that time trying to alloy chromium in copper. Now, copper actually is actually a reflector in CO2 laser, whereas I was trying to melt the surfaces of copper using CO2 laser. Of course, we achieved that through certain innovative ideas, but that allows me to fondly recollect that I think the Chancellor mentioned about or the Vice Chancellor mentioned about the holy combination of Medicaps University and RRCAD being in the same city. So I would say that this certainly augurs well, because laser has in India, laser activities in India has definitely a very strong connection with this very city, Indore, and particularly RRCAD. So I won't take any further time because Shobhan has taken a lot of time, and I would like to save the rest of the time for my discourse, and I hope you'll have some appetite to know about additive manufacturing. I was going through the list of speakers and so on. I see that quite a few very important topics are being covered, and I also have a very strong connection with ILA. I reminded Shobhan that I have been a life member of Indian Laser Association for decades, from the very formative days. I would like to congratulate Medicaps University for taking this initiative. I would like to compliment them, because I now work in a private university, so it's not very common that you see a private university coming forward to host a national event of this magnitude. So both the Chancellor and Vice Chancellor and rest of the members of this university deserve a big compliment and a big applause for hosting National Laser Symposium. I must also compliment Indian Laser Association for keeping the flag high and pursuing the field of laser development and application very strongly in this country. India has a lot to deliver, much more than what we have achieved. And here is a field where we actually certainly can make a difference. So ILA should take the mantle forward. One little correction, the academy that I was until recently, and I am no longer the president, by the by. I mean, Mr. Patil, J.D. Patil is the current president, and he would kill me if he hears that I'm announced here as president of INE. I was president of INE until 31st December 2024. My term ended last December, so I'm now a former president. And it's called Indian National Academy of Engineering, not engineers. We are not a club of engineers. We are an academy of engineering devoted to the cause of engineering, wherein we always say that engineering is nothing but an exercise to design and develop solutions to human aspirations. For example, Maimon showed that he could energize by simulated emission and emit rays which are coherent and monochromatic and parallel. But the real application started much later. So the engineers always learn from the fundamentals of a science and take it to the society to find an answer to human aspirations. So I'm very glad to be part of this event here, and I hope all of us here would take home new knowledge and new inspiration for doing something great for the country and for this profession. Thank you very much. Jai Hind.
thank you, sir, for correcting the mistake. Also, thank you for outlining various aspects of laser material processing, and laser materials related to the lasers. That are also related to the symposium. I also thank you for your kind support during your CGCRI days, having cooperation with RRCAT. I am sure your insightful thoughts will ignite many bright minds present in the audience. Now, we are excited to release the abstract book of NLS 33. This compilation brings together the key insights, research findings, and innovative discussions shared by our esteemed speakers and participants. The abstract book serves as a valuable resource, highlighting diverse range of topics covered and offering a glimpse into dynamic and thought-provoking sessions that are going to take place. Now I request Ms. Vaishali, Priya, and Aparna to bring the book of abstract. Now I request the dignitaries to release the book of abstracts of NLS 33. Thank you, sirs. Now it is a time for the much awaited keynote address by one of the brightest mind and stalwart on laser material processing in the country, Professor Indranil Manna. Before we proceed further, I request all other dignitaries to take their seats in the audience gallery. Now I request sir for his इसको थोड़ा सा ठीक कर दो इसके ऊपर ही लगा अपना हटाइए HDMI हाँ HDMI इसको रखा दो इसको आज इसके ऊपर
Color mic if you have, yes.
Yeah, color mic very
Or I think more, maybe I can, yeah, I can vary screen. Acha, the boards. Okay. Then you could as well speak from here.
Yeah, now it's visible, sir.
me. No, but this is a laser will not work, no? You have a. Okay, I'll operate.
You can make a pointer on the mouse.
That's only, I can use it.
It's working.
Oh, it's working. Okay, I think I should be able to. So good morning once more, and I wish to basically present before you the excitement of a field possibly no longer emerging, which already has made huge ripples. I'm going to show you quite a few of these examples. So it's all about, when we look at these various engineering machines or components or devices, we generally tend to believe that you go through a long process of manufacturing those components. What I'm going to show you is that the current trend is to do away with many of those conventional approaches and then adopt something which is fairly modern and very energy economic. So before anything, let me say that I have the privilege of wearing two hats at least. I currently belong to Birla Institute of Technology, Mesra, Ranchi, but I still retain my position at IIT Kharagpur, and once I finish at BIT Mesra, then end of the year I'll go back to IIT Kharagpur. And as I said, I'm not the president, the former president of INAE, but the current, one of the vice presidents of Indian National Science Academy. So if you look at this view graph and if you just compare these two rows, so typically this is how conventionally you would develop a component. If we want to develop such a cube with certain perforations or designs, then you would start with a block and you go through a huge lot of machining, if not any other material processing. And by the time you develop this three-dimensional object, you would have amassed a huge amount of material which is kind of a waste unless you are able to recycle. If you do the reverse, that you start with powders, a lump of or a heap of powders, and then use laser as a tool which actually can do very localized melting and allow development of material layer by layer, then you actually can build over a period of time the same shape, exactly the same shape and dimension of the same functionality with practically no waste. So any industrialist would always prefer the second possibility than the first. So this is, in very simple words, what is known as additive manufacturing. And so what is that? What are the characteristics? That you actually can do the entire design digitally. You don't have to perform an experiment. So once the design is ready on the design board on the screen of your computer, then you would have exercised by then a lot of flexibility and precision and accuracy. You didn't need any special tool or special facilities for making that design. The process is fairly green and clean with, as I said, very minimal waste. And you actually literally can use any solid. I mean, we know very well that by solids we can have, in the pure form, three possibilities, namely the metallic, the ceramic, or the polymeric, depending on whether you have metallic bonding or ionic bonding or covalent bonding, in the purer form, of course. But then generally laser is, can be used for forming any of these components, but for additive manufacturing until now is more successful with the polymeric and the metallic, but not so much with the oxide type of ceramics. So it is actually ideal for high cost, low volume components. This is one phrase we have to keep in mind, and I'll explain why this is important. It also is very useful for product repair and replacement, but then when we pursue something, we tend to create an impression as if it is 100% successful. There's nothing in the world, we live in a world of relative merits, so there's nothing which has only merits and no demerits. So the demerits are the following, that there is size restriction, there is an element of porosity and anisotropy which goes along with this. Is not suitable for non-weldable solids like I mentioned, oxides. Not competitive for mass production. If you are, for example, producing the small caps that we see on the top of the water bottles, you would not use laser additive manufacturing for making those caps or the bottles. The most important thing is that the mechanical properties that we derive from these additively manufactured components is somewhat in between the cast product and the wrought product. The wrought product will obviously give you the better combination of strength and toughness but then the cast product will have its own defects. So additive manufacturing products would be somewhat in between. So the scheme is like you start with a design file, then you go dump that file onto your computer, the computer drives the laser head, and you keep on moving. Now, the most important thing for us to understand is that when you, for example, want to create a big component, let's say a gear or an engine block, then you'll have a mold and you'll pour the material, let's say a metal, and over a period of time, the casting is complete and you have your component. So that's also a one-shot operation, but over a period of time, and the most importantly, you need a preform, you need a mold or something like this. If you want to do manufacturing of the same engine block without having a mold, then you actually are to go through a process called droplet integration. So in casting, you solidify in one single shot for the entire volume. It could be even few tens or hundreds to even kgs to even tons. Whereas in additive manufacturing, at a time, at a particular moment, you actually are processing only a very small volume, maybe a 1 millimeter cube or maybe just less than a centimeter cube area. But you integrate that along X, Y, and Z, and then you prepare the three-dimensional component. So you actually can do the processing through liquid, through solid, and also using powder. And accordingly, we have number of processes which are patented and doing rounds in the profession. So the development, I said droplet-wise, and if you actually think of one single spot, just like this laser spot, so if you have irradiated one spot and then the next along x-axis, and you repeat the same line along by a little shift along the y, so by then, as you complete the entire region, you would have formed a sheet or a layer, and then you keep on building layer upon layer, then you actually can develop also in the z-axis. So that's how you can create a complete three-dimensional product. Now, so it's something like this, that in order to develop this kind of a shape of a dome, I can go layer by layer like this, so it requires a process of integration. And the process of integration need not be just a simple sheet metal like this. It can be any complicated shape or dimension like this. So there's a huge list of processes which are patented and are doing rounds, using sintering as a mechanism of consolidation, or melting using laser, or even electron beam, and also spray approaches for polymers, even ultrasonic beam for consolidation. So there are multiple ways you can do that. That's not very important. This will certainly, again, draw the attention of the industrialists. For producing an engineering component using the machining approach, so that means you have a solid block, and if you machine out of that, like I was showing in the very beginning, then you consume easily somewhat like over 1500 kilowatt hour for one single component on an average. Compared to that, compared to 1500 kilowatt hour, if you're doing something with direct energy deposition using laser, or using a powder bed, you are going to consume anything like about 1/5 of that amount of energy that you have consumed in a conventional process. So it's a much more energy efficient process. But there could also be other additive manufacturing approaches using, for example, binder jetting, where you primarily spray the polymers and allow them to polymerize, or joule printing. In those, the energy consumption per unit could be even less. Even more attractive is the proposition that, so there are two, since I mentioned about low volume, high cost, I'll explain why did I say that. So if you compare the cost per component that is involved with the conventional approach of manufacturing, so this is traditional manufacturing. So the cost per component or part goes exponentially high as the complexity or customization increases. So imagine a gear typically used for any automobile or any other dynamic units. So if you want to produce a gear by conventional manufacturing, you have easily something like maybe a dozen different steps. So as the complexity of the gear in terms of dimension or geometry or contour changes, then the complexity increases and the cost per part increases exponentially. With additive manufacturing, whether it is just a ring or a gear or a sophisticated gear assembly, in all these, the cost per component remains nearly the same. The other very important thing is that if you are to produce 5 component or 5,000 components, laser-assisted additive manufacturing is practically independent of that number. But in case of conventional manufacturing, say for example, injection molding, there the cost per part drastically reduces if you produce more number of components. So that's why I said that additive manufacturing, particularly using laser, is most appropriate for low volume. That means you want customization of high order, fewer components, but which are very expensive. Say, for example, using titanium or some other precious metals, then you would rather go for. You don't mind paying any amount of money for the stent to be implanted in the body of a patient, right? But if it's a simple tube, which is going to be used for some engineering purpose, then you would go for the cheapest possible cost. So you would not produce a simple tube, whether it's of polyethylene or stainless steel or something else using laser. But for a very sophisticated component, whether for medical application or engineering application, you don't mind going for laser. The market is expanding. This fairly old data, 2018, already crossed 10 billion. And today, the market would be easily more than twice that amount. So already there's a business available globally, which is, let's say, $25 billion. BMW invested a large amount of money to create an additive manufacturing plant. Why? What was their motivation? Because they decided that they don't want to maintain warehouse. Now, let's say you are running a BMW car, whether in India or Europe or in US, you require easily some 10,000 or more number of various parts. And something may be related to the wheels, something maybe to the steering, something to the engine or the transmission rod or various components. Now, you have to maintain spares for the automobile and throughout the world, not just in one location. So maintaining warehouse is a very expensive affair. So when you actually pay some, few crores for a very sophisticated and a modern automobile, you pay not only for the particular unit that you have bought, but also the entire support system that are necessary for that kind of a machine to be successful. If you don't want to maintain a warehouse, and instead if you just have a small laboratory in different parts of the country, you place an order today from Indore, and the manufacturing unit in Mumbai will immediately start working on it. The component may take a few hours, and next day or the very next day, the component will be shipped and delivered to your doorstep at Indore. And in the process, you would have reduced huge amount of investment required to maintaining warehouse. So likewise, there are also similar initiatives taken by not just the automobile companies, even the aircraft manufacturing units. Now, where are the uses mostly? The largest use is in various industrial manufacturing practices, aerospace, motor vehicles. What is coming up is electronics and certainly the medical and various dental applications. So you want a tooth implant replacement, or you want a certain prosthetic parts to be developed, customized, because no two patient will have the exactly the same bone dimension or the density, or for example, a cancer patient wants a part of a bone to be replaced. So first you have to open up and then use some kind of imaging technique to look at the contour of the half destroyed bone and then start developing on that, and then, so it takes enormous amount of time. But if you have actually a AM plant very next to the operation theater, then as soon as the image is available, transferred to the CAD file, to the computer, and the corresponding CAD file can be developed, and through that you develop this component and deliver to the patient in the same operation, not another day. So this is how these things are changing. So just a few basics, not for RRCAD people, but for the rest. This is what I was saying in the beginning, that we can divide the entire set of solids into just two compartments, where we have overlapping bands, electrons in the overlapping bands, the metallic materials, or where we have a band gap between the valence and the conduction band. So there you push all the rest of the materials, polymers, ceramics, semiconductors, and so on. Either way, whether you lift electrons from the valence to the conduction, or you already have electrons in the Fermi surface and you excite. So there's a process of excitation and de-excitation. And in this course, you're able to absorb the incident energy onto the solid matter that you're irradiating, and the excitation of phonon allows you to, so you actually go through either an electron-electron collision or electron-phonon collision, by which you can convert the incident energy coming from the laser beam onto lattice heat or sensible heat into the solid. We are interested in laser, which I mentioned in the beginning, because it's coherent, monochromatic, low divergence, and of course, you can deliver very high power. As engineers, I'm interested more in the high power aspect. For the physicists would be not so much worried about the power, but more so on the spectral purity and the purity of the wavelength and so on. The advantage of laser lies here. The entire gamut of activities you can think of, whether you want to machine remove, whether you can add or form, or you want to join, or you want to treat the surface. In all these operations, you may have to go through melting casting or melting solidification or vaporization deposition or simply solid state heating. So a single tool which actually can help you do all kinds of materials processing. There's no other parallel to laser, because I'm dealing essentially only two process parameters, namely the power density and the interaction time. I'm assuming I'm using continuous wave. I can also use pulse laser. In that case, the pulse width. So the time and the power density are the two principal parameters. Well, if you are using a direct energy deposition, then of course feed rate becomes another parameter. Otherwise, using these two parameters, I can do only heating, I can do melting, or I can do vaporization. In the process, I can do, say, for example, bending or melting and alloying, or even deposition or drilling or and so on and so forth. So all kinds of engineering applications I can control using only these two parameters. Onto the materials, important that all of us understand that generally in conventional processes you do operations like melting, casting, heat treatment, sintering, rolling, extrusion. These are standard practices the mechanical engineers routinely do. These practices have certain limitations in terms of the enhancement of property that you can achieve. And instead you go for, so that's why they are called equilibrium processes. I'll come in a minute, what do I mean? So we also prefer to go for processes which are non-equilibrium in nature, that I don't have enough time, I'm in a hurry, I want to produce something very good to my desired recipe, and hence I may try one of these operations, and laser material processing is one of the best possible options. So when we talk about equilibrium, there are two constraints that we have to deal with, and this is imposed by Mother Nature, but nature also tells us, shows us how you can defy the equilibrium and do something different and better. So the constraints come from two facts. Number one, the solubility limit. The materials people would immediately recall that this is an eutectic diagram, and it shows that I'm dealing with a binary system, A and B, and this is A 100%, this is B 100%. The maximum amount of sugar that I can add to water is dependent on temperature. The same way, the maximum amount of B I can pack in A is only up to this extent and not beyond. This is set by the equilibrium thermodynamics, okay? If I want anything beyond this, then I end up in two-phase aggregate. I can't maintain a single-phase aggregate anymore. The second constraint comes at the diffusion coefficient. If I want a change, for example, if I want all the people sitting here to change the arrangement, all of you will have to get up and move to another place. So some transportation will be required. So the rate at which I can enforce this change will depend upon how fast you can move. The same thing in an aggregate, it all depends on how fast the atoms or the species that you have, atoms, ions, molecules, radicals, whatever I have, should be able to rearrange themselves. And that rate of rearrangement is the so-called diffusivity in solid state. And that's the second constraint. And if I want to get away out of constraint, I would like to use the so-called non-equilibrium approaches. There, I showed you a series of possibilities that I can actually use, but I would just confine myself to these two major approaches called powder bed fusion. So essentially, I'm aiming to develop such very complicated component, very complex shape and an exciting shape and so on. And you can imagine if you want to do it by conventional process, then how much of casting, heat treatment, machining, post-machining treatments and so on I have to do to make these turbine blades or these kind of porous structures and so on. But if I simply look at this structure and simply operate it by slicing layer by layer in the Z direction, then on every XY plane, I know where I have material, where I don't have material. And I stitch all these layers one after the other, one on top of the other in the Z direction, then I can produce this component. So how do I do it? I basically use a tank of powders, and I use a laser beam from the top to describe exactly the shape that is dictated by my CAD file. So a place where I have material, I'll use the laser irradiation to melt the powder and allow them to solidify and consolidate. Where I don't have material, where I have a open structure, porous or sort of a void, I won't irradiate at all. So I'll leave the powder as it is. So likewise, if I have a bed of powder and if I translate my laser beam around, I can create a ring, hollow ring. There's nothing in between. But if I want a complete circular plate, then I'll have to make my laser move all along and then melt the entire circular or rectangular area to make a plate. So the same way, if I keep doing that vertically upwards, I can create a complete component. So this I can do using a powder bed, or if I want to move away from the conventional, because you can very well imagine that the powder bed has a fixed composition. So instead of a brass component, if I want to make a stainless steel component, I have to change the entire powder bed and bring a new material. But if I want to do it dynamically, then I have another way where I not only have the laser ready for irradiation, I also can feed powder through the concentric nozzles. So here I actually can change the composition dynamically. So I may start with brass, I may in between move to aluminum and then later on, or maybe A, B, C, or keep changing that. So if I am developing something new, tailoring a component to my requirement, I would rather prefer this direct energy deposition approach than powder bed approach. On the other hand, if I'm producing a nozzle for a company and the same nozzle, 1,000 pieces, then I would rather use powder bed because I don't need to change anything in between. So this is the facility that I mentioned late 90s when I first came to RRCAT, and my first exposure to laser operations was in 95. So from 95 until 2020, you can imagine nearly 25 years, I waited and aspired that someday I'll have a laser in my own laboratory. So finally, thanks to DST, it happened in 2019. Actually, the machine was delivered in 2019, and by the time it was made operational was 2020. Excuse me. So 2020, and so this, by that time, the machine was operational by, let's say, January, February. And by March came May, all of us would, pandemic, the dreadful pandemic. So far, and as would have it, I also moved out of Kharagpur, decided to move out of Kharagpur and join Ranchi, Mesra in 2020 August. So there was not a soul around to maintain the machine. Still maintain the machine and derive a lot of good results I'm going to show you. I'm immensely grateful to my students and colleagues who actually maintain. I do visit Kharagpur every month, if not more than once, and take care of it. So why I'm showing this to you is that I have all these components now available. So I have a complete KUKA Robo, 6-arm, and it can deliver 6 kilowatt laser. I have a stage, the stage can be moved. This laser head can move in any direction, so I actually can develop any amount of shape that I want. And I have a powder feeder, twin hopper, so I can change the composition dynamically. And I have a shroud, I have all other control systems and gas shroud and fume collectors and so on. So I would now like to, this was the introduction. So now I'd like to go to the actual applications, what we do in materials processing. You know, this is the heart of the aircrafts, the engine. And this big diameter one is the compressor, and this is the actual, where the combustion takes place, the combustion. And we all know that these are superalloy blades, which can withstand 1050 or even higher, nickel-based superalloys, single crystal. Not just the engine, even each blade costs enormous amount of money. So the whole assembly is several hundreds of crores. For whatever reason, if you develop any defect onto the corners or somewhere, you can't throw it away because it's so expensive. But you cannot run the machine with that amount of risk, so you'd like to repair. So laser additive manufacturing is the best way to handle such situations. You also have to take care of its protection from high temperature exposure. You're talking about over 1,000 degrees centigrade metal with highly oxidative atmosphere, so it's very prone to oxidation. So the biggest threat to the turbine blades come from the oxidation, apart from, of course, creep and thermal fatigue and so on. So you'd like to protect, and the normal way of protecting that is having a top coat, which basically is an oxide, maybe zirconia or something like oxides, and you need a bond coat, and combining this is a nightmare. It's not a very easy job. Only few manufacturers can do that. Even more exciting scope of application is, we are all aware that ISRO has made the country proud and has also made the country very, India is very keen to send manned mission to space and bring back. So we need re-entry vehicles, and for re-entry vehicles, you have these red marked areas which can withstand temperature in excess of 1650 degrees centigrade. So you can't expose any metal. And please remember that when you come back, when you go out, it's easy. When you come back from rarefied, very low pressure to very atmospheric pressure, the frictional temperature at the surface can rise well above few thousand degrees. So that can lead to disaster if you expose any metallic component at all. So you have to cover up the metallic component, and for that you need certain thermal protection systems, which are mostly ceramic in nature, oxides in nature. But you know very well that you can't make a spacecraft only by oxides or ceramics. You can't make it only by metal, like we see in case of aircrafts, because it won't be able to withstand that high temperature rise. So you need a combination. And ceramics and metals don't talk to each other very well. They're not necessarily very good. The simple reason that on one hand you have ionic or covalent bonding, on the other hand you have metallic bonding. So marrying these two is a major challenge, and I'll show you. So now onwards, I'll be relying totally on my students who do all the jobs. So Manoj created a new type of thermal barrier coating where he has replaced partially zirconia with gadolinium oxide. The advantage is that this gadolinium oxide has lower conductivity and also lower sinterability. So we don't want them to sinter very well and make 100% dense, because air pockets actually are good thermal insulators and also reduces weight. So, so what he has shown is that this has nothing to do with laser. What he has shown is that he has understood which way he actually can reduce the oxidation kinetics by using gadolinium oxide as a part of this oxidation resistance exercise. Now, when he was successful and we published our own work in the past, way back, Josna Datta Majumdar is a colleague of mine in IIT Kharagpur, and she's the one who actually came and worked here in late 90s for her, a part of her PhD thesis. So she carries 2 PhD degrees. In the second PhD she did in Germany, and there she showed that if you take titanium, which is the compressor part of the turbine engines, and alloy with silicon or aluminum, then it does wonders in terms of oxidation resistance. So what it means is that if this is how titanium would oxidize at these temperatures, then with this surface alloys will undergo very little and practically negligible amount of oxidation. And that is purely because of these silicides form onto the surface. And this is where I'm recalling my proposition of using non-equilibrium thermodynamics. You cannot produce these microstructure by equilibrium processing. You can do it with laser because laser allows you very fast cooling, and as a result you can retain a lot more solute than what normally is allowed, and moreover you actually can shift the phase diagram towards from hypo to hyper side or have a different microstructure which is not possible in normal courses. So if you can develop this kind of a microstructure, then you can make such a huge difference in terms of oxidation kinetics. Remember, this is mass gain as a function of time. So if that was demonstrated in 1999, so I told Manoj that we should try and replicate this in your case. So he said, I mean, of course, we have published already about this using gadolinium oxide and zirconia. So now what he did was to alloy with aluminum and silicon, and also a bit of zirconium diboride, and develop this kind of an interface. I'm keen to show you that there is a defect. So if you have ceramic oxides and metal, invariably you need bond coat on which you'll grow the ceramic oxide. I don't have any bond coat here. I have the metallic substrate, and on top I have created an alloyed zone, this kind of an alloyed zone, which grows directly and epitaxially from the underlying substrate with no major or no discernible defects in them. And the advantage of that is that this is the hardness profile. The biggest advantage is that it gives you, now you compare the top curve, which is Inconel 718, and the bottom one, which is the blue one, which is 718 surface alloyed with silicon. And you can very well see that we get very large difference in terms of oxidation resistance. This oxidizes faster, this oxidizes much later or much slower and very marginally. And this is all because of this kind of a microstructure. So I'm not going to all those details of characterization. I hope you believe that this improvement, significant improvement in oxidation resistance was possible because of this kind of a microstructure created by laser alloying. So subsequently, Manoj, what he has done is he has also done serial sectioning layer by layer and understood the various kinds of microstructural changes in terms of composition, in terms of mechanical properties like hardness, and the various wear damages that these layer undergoes. So basically, you have a thickness of about, let's say, a few hundred micrometers, less than a millimeter, or about a millimeter. So he does serial sectioning and looks at depth-wise, how does the microstructure changes and how does the wear and other properties change. Now, I was talking about, say, dredging bucket or these kind of wheels or railway wheels or pulley wheels and so on. In all these cases, we undergo very large amount of wear and tear at these parts. Each of these is a very expensive component. So you don't want to throw them away. Similarly, for one such combustion unit, the combustion chamber, you have some nozzle, which in normal course will have 13 parts. So this particular nozzle is a complex unit, which is a combination of 13 different parts. If you use additive manufacturing, you produce the same component in one single operation and is a single part. So obviously, this is much more attractive to any aircraft manufacturer because you save time, material, and earn a lot of flexibility. Because you can always customize the beam, the diameter at the nozzle tip, and so on. So this is these are also examples where you have a lot of wear and tear. I'll show you an example on this continuous casting rolls, what we have done. Sometimes back, there's a scientist in, I think Ravi Bhatte is going to speak here in his lab, ARCI. One of my former student, Gururaj, he showed for the first time, this was reported in 2014, more than 10 years ago. He showed that H13 is a very standard tool steel. He showed that the tool steel, you just look at this diagram. So this is the normal condition in hardened and tempered tool steel H13. And this 2, 3, 4 are the conditions additive manufacturing components. So he actually deposited H13 tool steel on H13 tool steel, and in the process, since you have a large metal base at the bottom to extract heat faster, so he developed the same martensitic microstructure. Normally, those steel metallurgists would know that when you melt and directly cast, you don't expect that martensite would form. You'd end up getting a lot of retained austenite. But here he showed, because of faster cooling, he was able to get not only martensite, but also finer martensite. And as a result of this kind of a microstructure, look at this 4 and 2. It is not only showing higher tensile and yield strength, but also higher ductility, higher toughness. That's something very extraordinary. So using a cladding, using a deposition overlayer, you actually can improve the property of already an existing substrate. So using this approach, we tried not only deposit the same material, why not a combination? So Abhishek made mixture of stainless steel and 718. So, 718, we all know, is a superalloy, is a very expensive superalloy. So if you can use a stainless steel component, maybe a disc or a drum or something, but make a clad on top, which is superalloy, then all the protection will be given by the clad, and the base structure is a much inexpensive stainless steel. So obviously, this is a much, a very attractive proposition. And you don't have to take a drum or a tube and then deposit. Actually can use a powder feeder to make, let's say, create a diameter of X of a certain wall thickness of stainless steel, and then you make a thin layer of another millimeter or two, slightly X plus delta X diameter with 718. So you create a tube where the inner core is stainless steel, the outer surface is 718. So the student at that point of time realized that the surface contour, which is responsible for reflection, in fact, those of you who are in that much of the incident laser is reflected because of the metallic nature of the substrate. So very major exercise goes in how to absorb more laser incident power. So, and there actually Manish showed that the surface roughness plays a role. You don't have to go into the details, but if you look at these two comparisons, so it's the same material, same alloy, same process, same power, same methodology, everything same, except that in one case, he used sandblasting, and in another case, belt grinding. And you see the differences in microstructure. And this certainly leads to very major differences in properties. So that means we learned that when you are depositing, you have to make sure that the surface condition is reproducible. A very similar exercise was done by Dilip, and he showed this is for biomedical applications. So he wants to develop bone implant placements. So titanium alloy, one of the standard materials. For osseointegration, that means you not only replace a bone, you actually create an implant, and you allow you expect or you desire the tissues to grow on top of that. So that's called osseointegration. So for that, certain element of surface roughness is necessary. So he used picosecond and nanosecond pulsed lasers to create such patterns. So he called it surface structuring, essentially the same. It's also called micro-patterning, or in the literature, various words. So essentially, he creates these calculated array of patterns onto the surface by removing material at some regular intervals, so that you create intentional roughness onto the surface, whereby the tissues will integrate better. And of course, he got better results in terms of osseointegration. How am I doing in terms of time? I'll just try to expedite. So Sharath used stainless steel and 718. He used smelting to see how the material changes. Say, for example, in this, actually it's too busy a slide. If you just look at these microstructures, easier for you to follow. So in case of normal 718, this would be the kind of microstructure that you would get. And after surface melting, you get much refined microstructures. And as a result of this, the properties, not only mechanical, but corrosion, are significantly improved because of finer grain size. And so borrowing from this, then he used actually direct deposition of stainless steel, and later on also he did with 718. So the idea is that we learned what happens if you only do surface melting, and borrowing from that, we applied powders to build a three-dimensional structure, and then as we expected, we did see improvement in properties in terms of both strength and certain functionalities, corrosion resistance. And this is what we actually learned from Guru Raj's work earlier, that the deposition can actually give you better properties than the basic components. Now, here is something another very interesting. Those of you or AutoCAD, few times join. You know, if you look at I hope it's working. Any other engineering component, there's rarely you'll find an automobile made out of one single. Rarely find a machine which is only one alloy A and not B or C. In other words, what I'm trying to say is that if you look at a complete component, be it a laptop or even a small component, you'll always be forced to use various combination of materials, solid materials. Maybe metal, maybe non-metal, maybe different alloys and so on. So you need joining. And laser is a good tool for joining, so is also electron beam, other than, of course, the conventional arc processes. So whenever you join, expect these to form very good bonding and not create any problem. But problem may come when you are trying to join dissimilar materials like aluminum with steel. That's primarily because you end up making a lot of intermetallic phases which are very brittle in nature. So on the whole, from the outside, you'll see very nicely joined, no crack or nothing, but you have some inner mines at these intermetallic phases. Very different lattice parameters load, then they tend to fail because of large differences in lattice parameters. So any manufacturing unit needs to join aluminum with steel, but always is very worried because it may cause a lot of brittleness. Now, Bidipta has shown something very interesting, that she has shown that this is the original stainless steel, and now she is able to deposit stainless steel on aluminum without any crack. So you have to believe me. So what she did was, this is the aluminum 1100 substrate, pure aluminum, and deposited a ferrous alloy, which is a trademark alloy from a company, Rocket 401. And she shows that if you deposit once, twice, thrice, and multiple times, then this layer does not see aluminum. This layer does not see aluminum. Only this layer sees aluminum below. So the danger of formation of intermetallic phases is maximum at this interface, and that threat gradually diminishes as you go higher and higher. And in the process, so this is a kind of a microstructure that you develop, and she's able to show that under load, under various kinds of activations, this is the level of damages you see on the top layer, and this is the level of damage in pure aluminum. So in other words, can make aluminum wear resistant, erosion resistant, and so on, or be able to withstand much larger mechanical activation by depositing, by cladding with ferrous alloy without having the danger of steel, danger of brittleness. Now, why is that possible? How is that possible? It's possible because you have to identify the very narrow process parameters which will allow iron to mix with aluminum and form a solid solution, not allow formation of any intermetallic phase. If you go into the phase diagram, you'd be able to see that iron and aluminum has a certain solid solution range, maybe about 10, 15 weight % or even more. So if you can confine or if you can restrict interdiffusion to an extent that the maximum amount of iron-aluminum combination will be within the single phase region, then you can avoid formation of these intermetallic phases. So this is a clue with which you can, and if this is true, then one can also do aluminum iron welding in the future. So Nikita worked on these these are continuous caster rolls, easily 1200, 1100 degrees centigrade or more, with a large amount of halide ions like sodium fluoride, calcium fluoride kind of salts which are used as lubricant. So these fluorides at that high temperature are extremely corrosive. So these caster rolls are required to be changed very often. So she's trying to deposit certain martensitic layers, martensitic clads, onto the surface and develop these kind of structures so that they can be more wear and erosion resistant. A similar approach is followed by Mangesh, where he wants to develop clads on these railway wheels and make them more wear resistant and so on. I have a lot of examples, but I just want to fast forward now. Amitabh is working on depositing either an austenitic stainless steel or martensitic stainless steel on SAE 4140, which is a very standard alloy. Then there are also other similar work where not only this kind of a clad, but also with dispersion, these carbide dispersions. This is another student, and this is by Subra Kamal, who is now developing AAA 800 on stainless steel. He also uses a serial sectioning methods to show that how the gradation can be achieved. So essentially the whole idea is that as you go layer by layer, as you change the composition of the layers, then the properties also change. And this is how you actually can make a much tougher clad or even a complete component on that. This is a similar approach by Tapas, where he used a titanium alloy. So this is the last example I want to show. These are more experimental work. The microstructure is a very strong function of thermal history. So what temperature, what cooling rate, what thermal gradient, and so on. So Pawan is working on modeling of such. Is not direct irradiation of a solid. It's actually direct deposition powder bed method. So this is the configuration which he uses, and these are the kind of simulation results he has developed. So this is the powder bed, and this is the laser track that he produces. And on the cross-sectional pool, so this is the kind of temperature profile you develop, and you actually can make a keyhole or a conduction melt configuration. And this is the kind of temperature as a function of time. And this is how you actually, also you can convert temperature time to heating rate to time and try to correlate with the kind of microstructure that you develop. So that's all. I would like to end saying that if this is what we want to develop, then you have to start from somewhere. This is borrowed from Skyroot. Many may know the name, is one of the startups who produce now this hygienic tank by a single additive manufacturing operation. Stainless steel, not so difficult. So essentially you start from the bottom, and then you keep moving the laser like this, and as you change the diameter, this is a hollow of course, as you change the diameter, you have different configurations. So in a single operation, over a period of time, of course, you can produce this entire tank by using laser additive manufacturing. On the other hand, if you want to do it by either by extrusion or by forging, this would take days, if not months. And moreover, not a single operation, multiple operations. So in my opinion, the additive manufacturing is a droplet integration process wherein you build 1, 2, or 3-dimensional component devices or machines. This technology is already established with multiple success stories, and a huge potential lies ahead. But then far from saturating, we still have a lot of scopes for innovation and development. What we need in the country is basically a series of job shops. For example, RRCAD next door could be one. They can actually, if you go with an idea and try out there, buy time from them, and then you can try out these. So we actually need to try the various composition, size, and morphology, and of different materials to come out with some newer developments. And there are challenges. I mean, we don't have atomized powders available for all the alloys that we need. Interface is a problem, oxidation is a problem, porosity, micro cracks. All these are issues to be taken care of. But what we need to do is a long-term evaluation of these structures. It's like that today you show something which is happening, but you don't know how did it behave after 20 years or 40 years. Whereas for all conventional products, the experience shows how well or how bad they can actually work. So we have to do that kind of evaluation. So I feel that there's a large amount of opportunities, but we do have hurdles, and we need serious efforts. So before I thank you all, I would thank the the group who actually supports me in all these activities. As I said, many of them have submitted, some of them have submitted their thesis, some of them are about to submit, and some of them are working. And these two colleagues of mine, they actually are very, very big help when I'm away from Kharagpur. So I'll stop here and thank you for your patience. Thank you very much.
Thank you, sir, for your wonderful and highly enriching mesmerizing lecture on the highly emerging field of laser additive manufacturing and process engineering, highlighting its scopes and challenges. I am sure this lecture will be an impetus to ignite the minds of many scientists and accordingly. Indian Laser Association to present a memento to our chief guest, Professor Indranil Manna. I request Ms. Aparna Dwivedi to bring and hand over the memento to Dr. Pajapur. Thank you, sirs. I request Sri R.C. Mittal, Chancellor of Medicaps University, to present a memento to our guest of honor, Dr. S.B. Nakhe. I request Ms. Baisali to bring and hand over the memento to Sri R.C. Mittal. Thank you, sirs. Thank you, Aparna and Baisali. Now, I request Dr. Preeti Jain, Organizing Secretary 2 of Analyst 33, to offer vote of thanks.
Good morning to all. It is my privilege and honor to propose the vote of thanks on this esteemed occasion. On behalf of the organizing committee, we extend our heartfelt gratitude to all the dignitaries, speakers, participants, and attendees who have contributed to make this event a grand. we would like to express our sincere thanks to Professor Indranil Mane, Vice Chancellor of BIT Misri, for accepting our invitation to be the chief guest of this function and delivering an enlightening keynote address. His insights have set the perfect tone for this symposium, inspiring researchers and academicians alike. A special note of thanks to our esteemed guest of honor, Dr. S.V. Nake, former director of RRCATE, for his gracious present and thoughtful provoking address, which has added immense value to the inaugural session. My heartfelt thanks goes to Dr. Shovan K. Majumdar, President of ILA, and Dr. C.P. Paul, General Secretary of ILA, and Shri N.S. Banerjee, Treasurer ILA, for their leadership and commitment to organize this symposium. They have been the driving force behind all the things, big and small, you are witnessing here and are going to witness in next 4 days. I would like to extend my gratitude to Dr. V. Ganeshan, Chairman of Local Organizing Committee, NLS 33, for invaluable guidance and unwavering support in arranging this event. A special acknowledgement to Dr. S. Satpathy, Convener of NLS 33, Dr. A. Kosar, Co-Convener, NLS 33, Dr. R. Biswal, Scientific Secretary of NLS 33, and Shri Rajesh Patidar, Organizing Secretary, for these efforts in organizing this prestigious event. The dedication and meticulous planning have ensured the smooth execution of this symposium. We are deeply grateful to Dr. Shri R.C. Mittal, our Chancellor, Medicaps University, for his constant support and encouragement, and to Dr. D.K. Patnaik, our Vice Chancellor of Medicaps University, for his inspiring words that have motivated all. On behalf of the organizing committee, we would like to extend our deepest gratitude to the Board of Research in Nuclear Science, BRNS, and ILA for your invaluable support as a sponsor of the National Laser Symposium. Your gracious contribution played a pivotal role in making this event a remarkable success. We would like to express our heartfelt thanks to the chairperson of the scientific session, invited speakers, PhD thesis evaluation and poster evaluation committee, invited dignitaries for agreeing to be the part of the symposium. This symposium has been a platform for rich academic discussions, and we would like to acknowledge all the scholars and researchers who will participate in the paper presentation and technical sessions. Your research contribution and innovation will truly enrich this gathering and will foster knowledge exchange and intellectual growth. We are also grateful to the National Organizing Committee, Symposium Organizing Committee, Scientific Committee, and various subcommittees, volunteers, and teaching staff whose restless efforts behind the scene have ensured the seamless execution of every session. Your hard work and dedication are deeply appreciated. We are thankful to media team for giving coverage to this event. Last but not the least, a big thank to all the delegates and participants for your enthusiastic engagement and active participation. Your presence has made this event more meaningful and successful. Once again, I express my deepest gratitude to each and every one of you. Thank you, and we look forward to meeting you again in future academic endeavor. Thank you very much.
Thank you, madam. That is a small announcement. I request all the participants to remain seated till the dignitaries leave the auditorium. Before we conclude, let us rise up for our national anthem. I request Dr. Prachi Sathe and team to come forward.
सावधान. जन गण मन अधिनायक जय हे भारत भाग्य विधाता, पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंग विंध्य हिमाचल यमुना गंगा उच्छल जलधि तरंग तव शुभ नामे जागे तव शुभ आशीष मागे गाहे तव जय गाथा जनगण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे भारत माता की भारत माता की भारत माता की एट ईज विश्राम
Thank you, Dr. Sathe and team. Now, I request all the dignitaries to proceed for the inauguration of the industrial exhibition at the lawn outside. I request the participants to follow the dignitaries. And I request all of you to join Chancellor's high tea following the inauguration. Thank you all. Please assemble in the auditorium for the next session immediately after at 1 o'clock. Thank you.
अरे इन्होंने लैपटॉप बंद कर दिया बंद कर दिया जाएगा ठीक है हाँ मैं लोड कर रहा हूँ सर आपका ही लोड आ जाइए
नहीं तो अगर पीडीएफ करना होगा तो डायमेंशन अलग है थोड़ा है ना इट इज अ बिट डिफरेंट फ्रॉम
सेंटर में रहता है
तो आता है
नेक्स्ट सेशन से यार नाखे जी एक सोफा एक टेबल रखें
सब हटवा देते हैं
नहीं बाकी हट जाएगा एक टेबल एक चेयर रहेगा बंद कर दो बंद कर दो
सेंटर में कर दिया जाए।
यहाँ पे नहीं है, यहाँ पे 2-3 बॉटल, एक तो यहाँ पे है उसके लिए, स्पीकर के लिए।
खुला नहीं है तो
नहीं नहीं खुला नहीं है, ये तो स्पीकर के लिए है। यहाँ पे 1 या 2 बॉटल रख देंगे। ओह है सुदीप,
अनाउंसमेंट का कुछ है? अनाउंसमेंट का
मिलता हूँ।
एक अनाउंसमेंट करना पड़ेगा तुझे।
ये तो जो पढ़ेगा इनका बायोडाटा जैसे संचय का, हाँ। और यहाँ से इसको बंद कर देते हैं। अभी ऑनलाइन मत करो, अभी देना है फोटो को, हैं? अभी ऑनलाइन मत करो, क्या है यार इनका।
अच्छा हाँ ठीक 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 पूरा फोल्डर है.
We will shortly start the first technical session, but before we do so, there is a special request from the authorities of Medical University, particularly the Chancellor, Vice Chancellor, and Professor Koshar and Professor Jain, that they would like to felicitate our chief guest on behalf of the Medicaps University. So now I request Professor Koshar to come on stage, and I also request Professor Manna to please come on stage. कुछ नहीं चाहिए किसको किसको बुलाना है तो इधर है Now I request Aarti Madam to please bring the memento. Thank you, sir. Thank you, Madam and Professor Kose. Now I request Dr. Ajit Upadhyay to please start the technical session.
हाँ वो ये मैं बोला था ये बायोडाटा है सबका पता है बोला हुआ
Welcome back to the first technical session. The session is on laser physics and technology. The first session is on laser physics and technology. I request Dr. S.V. Nakhe to chair this session. Sir, please take your seat. Dr. Nakhe does not need an introduction and he was introduced very well in the morning. So I won't take time. His brief biodata is listed here. Yeah. So I request, sir, over to you, sir. Mic, please.
Good afternoon. We are going to start a session. It's laser physics and technology is a very core area of NLS. There are many application areas, but this is a core area. Now in this session there are two speakers. We'll start with Dr. J. Padma Nilaya from BRC. She has worked in various areas, particularly her research interest is in the gas lasers. She has worked on carbon dioxide and carbon monoxide lasers, and its laser applications also that includes laser assisted surface modification and molecular laser isotope separation and fluorescence based biosensors. She has been awarded DAE Group Achievement Award in 2010 for laser assisted decontamination of nuclear fuel elements. This is a very critical area for Department of Atomic Energy. She had a US patent also on helium-free TCO2 laser. That is because helium is, as you know, is a costly and rare element. So this is an important achievement. And she had more than 80 papers in international peer-reviewed journals to her credit. So I invite Dr. J. Padma for her talk, and please leave 5 minutes for interaction after the talk is over. So it is 25 minutes talk.
Just a minute, went out.
Now it's on. Slide changer is this. A very good afternoon to you all, and thank you, Nakhe sir, for your kind introduction. It is always a great pleasure to be here in NLS, and I thank the organizers for that. The title of my talk is Enhancing Properties of Titanium-64 Alloy Through Laser-Assisted Surface Modification. But then seeing that I am presenting in a session which is dedicated to laser physics and technology, I thought I'll tweak my slides a little, make it more appropriate for this particular session. So anyway, so in the first part of my talk, I'll tell about CO laser development, and in the second part, I'll go to laser-assisted surface modification, and these are the contributors. The plan of the talk is going to be somewhat like this. I will tell about what is so special about the laser that we have developed, action obtained at 5 micron in the first place, what is the lasing gas mixture, you will understand why I'm saying this, and of course the line nitrogen-free operation of the CO laser. In the second part, I'm going to tell about how surface properties affect the functionality of the biomaterial, laser-assisted surface modification, and what we have achieved in terms of enhanced biocompatibility with microstructuring and enhanced wear and corrosion resistance by surface coating. Now, as keynote speaker was already saying in the morning, discovered in 1964 by C.K. Patel, CO2 laser is undoubtedly the most powerful mid-infrared laser and it is well researched, well documented technology, very well understood. Now, CO laser was also discovered immediately after CO2 laser. It is very similar in the sense that it is also a discharge-driven laser, it is also a diffusion cooled, it is also a molecular laser, and yet it's not so popular neither in the research laboratories nor in the industry, and mostly that is the reason is the usage of toxic CO gas. CO laser emits in the 5 micron region, has many applications, and for us molecular spectroscopy and separation of isotopes is of particularly dear application for Department of Atomic Energy. So, yeah. So what is special about our laser? Well, we were actually operating a CO2 laser under liquid nitrogen cooled conditions. We know that CO2 laser under free running condition emits at 10.4 micron, a single transition. And we had a spectrum analyzer to actually see the transition. Now, when cooled to very low temperatures using liquid nitrogen, we suddenly saw that the single transition has gone into multiple oscillations, lasing on multiple lines, and the position of the transitions was very weird, unlike emission from a CO molecule. So this initially baffled us, but then we got the reason, and the reason is that the lasing medium has actually changed. How has it changed? Well, CO2 undergoes dissociation when bombarded by energetic electrons in a discharge. In fact, a CO2 laser has about 40 to 50% dissociation of CO2 into CO and oxygen. So, but at such low temperatures, CO2 freezes, most of it freezes, while CO remains in the gaseous form, gets excited by the, pumped by the energetic electrons, a population inversion is created, and under proper cavity conditions can get to laze. So when we change the spectrum analyzer to a CO spectrum analyzer, then we could readily see that whatever signature that we are getting is indeed from the transitions of a CO molecule. So what have we achieved? We have got operation of emission in the 5 micron region, but by making use of CO2 laser gas mixture. What is CO2 laser gas mixture? CO2, nitrogen, and helium. So with that, what we have got is 5 micron oscillation, and usage of extraneous toxic CO gas is totally dispensed with. Now, before going any further, let me just explain very briefly how this multi-line CO operation takes place. Free running CO2 laser emission is resultant of 3 main processes: anharmonic pumping, which leads to partial inversion, which in turn leads to cascade lasing. Now, you know that the vibrational levels not changing. So the vibrational levels, as you know, they are closely spaced as you go up the vibrational quantum number. Now, suppose we consider two molecules in the levels N and M, and they collide with each other, then it is energetically favorable that this N goes up while M comes down, because the delta E is then positive, and this is realized as heat inside the discharge medium. So in an electric discharge, large number of vibrational levels are populated, and therefore total inversion between any 2 vibrational levels is not possible. And what we have instead is partial inversion, where population inversion is obtained between rotational levels corresponding to 2 different vibrational levels. And this gives rise to the interesting possibility of series of cascade lasings which obey proper transition rules. So how is that happening? See here, initially suppose the population inversion is between these 2 rotational levels of the neighboring vibrational levels. Then because of the lasing, the lower level, this gets populated, and inversion is created between this and this. So the next lasing happens between this, and then this continues, and what you have is a series of cascade lasing, and therefore you get a multi-line oscillation, just as we had got. And we could actually determine what are these wavelengths, and we could also establish cascade lasing from the kind of transitions that we have obtained. Now, whenever you talk of a laser, you know what is the laser gain medium or the gas mixture. But here our gas mixture is actually formed in situ, and we have no idea what it is, what is the ratio or what is the concentration ratio of these. So to that end, we tried to find out the mixture composition, and we devised an experiment where the gas mixture is taken out from the exhaust into a sample cell, and the contents are studied in FTIR. So this is the result of that. So when there is no discharge and when there is no cooling, what we see is the typical signature of the asymmetric rotational vibrational transition corresponding to a CO2 molecule, and this is centered at 2349. Now, when there is a discharge struck, but without the cooling, then we see a second one. This is typical of the CO molecule, the rotational vibrational spectrum, and the absence of this here clearly shows that our incident, whatever gas mixture that we have given, it does not have CO in the first place. So now for varying temperatures of the discharge tube, wall temperature, for different cooling, we got different CO and CO2 ratios, and the partial pressures of CO2 and CO in the collected samples could be experimentally estimated using the absorbance law. Now our mixture has, apart from CO2, CO, of course nitrogen and helium, which we are assuming will not change in the discharge, also has oxygen, because the dissociation reaction clearly forms oxygen as well. So oxygen being homonuclear diatomic molecule, FTR will not bear a signature, but we could calculate the molar concentration of oxygen from the CO2 dissociation reaction, and we got our lasing gas mixture, the ratios of various gases. And this gas mixture is very, very different from what is normally used in a CO laser, because a normal CO laser does not have this high CO2 as well as oxygen. And so you will see that what difference we got from a conventional CO operation. So we also operated this laser in line-tuned configuration by inserting a grating inside the cavity, and power on various transitions are shown here. Interesting thing, the literature on line-tuned CO laser is not so common. That is because the efficiency drastically drops. In fact, it is less than, it is almost 1/100th, and that is because of the partial inversion, kind of inversion process that happens here. So another interesting that we saw is that these lines are generally not reported in the literature. And this we attribute once again to the very unique gas composition that we have, and the presence of oxygen and excess CO2 actually changes the lasing dynamics of this particular laser. We also operated the laser in, we also operated it without nitrogen, and we realized that addition of nitrogen stabilized the laser discharge, increased the output power, and also the richness of the multi-line spectrum showed that more number of vibrational levels participated in presence of nitrogen. So this is a brief summary. Operation of CO laser without any extraneous toxic CO gas was achieved. The composition of the laser gas mixture could be found out, and it was operated in dispersive cavity, and nitrogen-free operation was also possible. Further characterization is in progress. I would like to say that our very senior colleague and mentor, Nandi sir, is also here, and he is actually helping us with the rate equation modeling of this particular novel laser. And you will also have a poster, I think, in this NLS in this regard. Now, coming to the surface modification of biomaterials, well, materials that are compatible with human body are generally termed as biomaterials. They have to be biocompatible, chemically inert, similar mechanical properties to the part that they're going to replace, and definitely non-toxic. So there are several metals, alloys, ceramics, polymers that are used as biomaterials, but titanium and its alloys have gained prominence and are predominantly used for orthopedic and load-bearing applications because of their much more suitable mechanical properties. Now, even if the material is biocompatible, the body rejects. This is called implant failure, and there are many reasons for implant failure. Where it could be surgical trauma, poor osseointegration. Osseointegration is the ability of the implant to actually bond with the tissue, the bone tissue, so as to integrate with the body. So, or there could be wear, corrosion, etc. So all these lead to implant failure. And therefore, it would be of great advantage if the functionality of the existing biomaterials could be improved further to overcome this implant failure, and this is possible by actually altering the existing biomaterials. See, the bulk properties of the biomaterial you would not want to change because that is decided by the application, where it is going to be in the body. But the surface properties is what we want to change because the biomaterial surface comes in contact with the body fluids, etc. This is possible by a variety of ways as shown here: mechanical grinding, sandblasting, electrochemical treatments, cell seeding, etc. But what we are concentrating are the physical methods of surface modification technique, basically laser-assisted microstructuring and pulse laser deposition. Our keynote speaker was also speaking about this in the morning in his address. So some part of it is somewhat similar, as you can see. So, yeah. So how do these change in surface properties actually help? Increase in surface area due to micro and nanostructuring enhances the interaction with body fluids. Depending on the type of surface structuring, it may also provide contact guidance to the growth of cells. Then increase in surface hardness improves wear, corrosion. Surface oxidation also supports osseointegration. And hydrophobicity can also lead to improve in corrosion resistance, self-healing, etc. So therefore, the judicious modification of the implant surface can fine-tune the interaction of the implant with body and accelerate its integration process. Before going any further, let me just very briefly tell the mechanism of absorption of laser radiation in materials, whether it is a metal or a semiconductor. So this is a representative diagram which shows the percentage absorption as a function of wavelength for metal, which is copper here, and for semiconductor, sorry, not semiconductor, it's insulator, ceramic, it is alumina. So for the initial high frequencies, the method of absorption is generally direct electronic excitation, where the atom or the molecule absorbs the initial photon, incident photon, and gets energized, gets electronically excited. It is for both metals as well as insulators. Now, further, as we come down to UV, in case of metals, the dominant process can be inverse Bremsstrahlung as well as electronic excitation. What is inverse Bremsstrahlung? Inverse Bremsstrahlung is when electron receives energy from the incident radiation and transfers part of it to the lattice or another particle through collision. So this way, it takes the incident energy and gives to the lattice. In case of insulators, it is generally electronic excitation. Now, when we come closer to the visible and near infrared, the absorption drops in both, and is generally because of multi-photon absorption, where number of photons together try to bridge the gap between the electronic levels. And as we go further into the infrared and mid-infrared, far infrared region, as you can see here, the absorption drops a lot for metals, but for insulators, it increases, and that is because of the possibility of vibrational and rotational excitation. Now, deposition of a very large amount of energy over a very short period of time can cause melting, vaporization, ablation, etc. And in case of laser-assisted microstructuring, the ablation and flowing of the melt and its consequent resolidification gives rise to what we finally see on the surface structure. So the laser parameters and the extent of overlap of neighboring pulses will decide what kind of a microstructure we are finally going to get. So this is a typical setup where we have used a picosecond Nd:Arc laser, frequency doubled, focused onto the sample, which is scanned as per our requirement. And by changing the laser parameters, we have generated a very large number of microstructures of varying size and dimensions, and a few of them are shown here. Of all these several structures that we had seen, we found two which are quite promising. One is groove structure, as we see here. The separation between the grooves was about 40 micron, while the internal structure, as you see, this was separated by 5 micron. Depth of the grooves was about a micron or so. And when this sample, along with the control, they were immersed in simulated body fluid. It is just the body fluid with salts, electrolytes. Minus, it is acellular, there is no cells in it. So when it is put in simulated body fluid, the HAP growth was almost 6-fold as compared to the pristine, and the healthy nature of HAP, Ca by P is 1.62, shows that it is a healthy HAP growth. HAP is hydroxyapatite, which is actually a bone cement that we call, that joins the implant with the bone tissue, which is essential for osseointegration. So the growth was so high. Then we also saw the, and this we attribute, of course, to the increased surface area, and also the fact that when a titanium dioxide layer is formed, it can be the phase of the titanium dioxide, which could be rutile or inertese. In our case, we found a mixed phase, and one of them, the crystal structure of one of them matches with HAP, and therefore ensures its efficient growth. We also saw this is what protein adhesion, And we found that there is a 2.5-fold increase in protein adhesion. This was for fetal bovine serum. We also saw for SBA. So basically the hydrophobic nature of the laser treated sample attracts the hydrophobic patches in proteins. Some of them have these strong hydrophobic patches, and therefore there can be this plus of course the increased residence time, etc. Is probably responsible for this. We also saw that there is a cell growth which is 2-fold improvement, and interestingly these cells align themselves along the grooves, which tells that it is giving rise to some kind of guided growth kinetics, which can be very useful when you want to actually guide the growth of tissue in a particular direction. Then the second structure that we saw was some kind of island structures, as you can see here. These are, we call them island structures. This we got by predominantly by changing the overlap factor. This had much less overlap, much increased overlap and much more overlap. And of course the fluence was also slightly changed. But then basically the size of the structures here, you can take maybe around 10 micron by 10 micron, 5 by 5, and maybe 2 or 1 by 1 kind. And these also we tried to study its biocompatibility as well as corrosion. What you see, we find that this structure has given the best results of all. Its hydrophobicity was highest. We could see that its hap growth here was much more as compared to the other 3 for the same time, that 25 days that we keep. As you can see, for pristine titanium it is almost not there, whereas this is much higher. And also the biocompatibility was highest for this structure. It is almost equal to that of the control. Control is the thing where you have just the medium and the cells put in it. There is no metal surface at all there. So this clearly shows that this SF2, this particular structure seemed to have all good properties. We also saw the corrosion behavior of these laser treated samples by immersing them in SBF once again and doing the typical 3 electrode electrochemical setup. So as you can see, there is a clear anodic shift and the absence of unwanted fluctuations here in the laser treated samples indicates a defect-free nature of the oxide film. As I said, in the laser microstructuring, because of the temperature, there is this titanium dioxide layer which is created. So this oxide layer is totally passive and defect-free. That is why this rise in the anodic shift. In addition, we also saw that the passivation current falls down. It is almost 2 orders less as compared to pristine. So this points to the corrosion inhibition efficiency of the laser treated samples. So what we saw was so while laser treated samples in general showed much better than pristine, this one gave much better results, and we attribute this definitely to the kind of structures that have been created here and the depth of the structure also. This was also about 1 micron depth, while these two were about 6 micron troughs were formed, and therefore the ability of the surface to actually promote this cell adhesion, protein adhesion, or hap growth and all, the biofunctionality definitely depends on these microstructures that are generated. Now, these microstructures being very thin actually show a little high wear when in the initial stages, and wear can be a little problematic when it comes to moving parts, for example, bone and socket. So in such cases, what one would want, what one normally does is a creation of a thin layer, 200 to 500 nanometer of ceramic on the metal surface, and that is known to reduce the wear considerably. We have seen this by depositing zirconia, alumina, or bioglass on titanium and its alloys, and this we have done by making use of pulse laser deposition. Once again, because it is a very controlled process, it can the laser parameters can be controlled. It gives uniform film deposition, maintains good stoichiometry, and etc. So this we have seen. Now I'm just going to tell you one interesting experiment that we have done in terms of wear study. We coated titanium 64 with zirconia and in another case with alumina, and we tried to study the wear of these with respect to 4 counterparts: stainless steel, tungsten carbide, zirconia, and alumina itself. Why study with 4 different counterparts? Well, in some some of the implants, especially in the moving parts, you can see that it is a hybrid implant. I mean, there are 2-3 types of structures which are present, and when you want to know about the wear, you would want to see the wear, how each one wears against the other one when rubbed. So the wear in conjunction of the pair is more important rather than individual, and therefore this study was taken up. And what we saw was that the wear rate for pristine, this is for the zirconia coated and this is alumina coated. So the wear rate was found to be, the zirconia coating gave a superior wear resistance for all the 4 counterparts, as you can see here, while alumina gave a wear rate which is much higher. Alumina is actually harder than zirconia, and this result initially we did not expect, but when we look deeper, then we realize that the fracture toughness of alumina is low, and therefore when it gets fractured, the wear debris which is formed is can actually give rise to abrasive wear, much higher wear, and therefore alumina against alumina gave a very bad performance.
Dr. Panna, please conclude in 2 minutes.
Definitely, sir. Yeah. Dependence of substrate temperature on PLD, during PLD, like when we are doing pulse laser deposition, we can keep the substrate at various temperatures. So we tried to do that and study the wear and corrosion. So this is for zirconia coated samples. It was done, this is pristine, room temperature, 200 degrees, 400, 600 and 800. And we found that the wear rate is minimum for the one coated at 800 degrees, and the adhesion is highest for that coated at 800 degrees, followed by much 4.5 times improved hemocompatibility also for 800. The corrosion resistance was also much high, as you can see here. So the zirconia coating, which was done at 800 degrees substrate temperature, showed an improved performance in all respects. And this reason we understood when we studied the Raman spectra of the coating. For all others, while we could see the definite peaks of ZrO2, for zirconia coated one, we could also see the coatings corresponding to zirconium carbide. So this carbide is diffused into the coating when PLD is taking place at 800 degrees from the atmospheric carbon. So this formation of zirconium carbide is what is responsible, because zirconium carbide is much harder than alumina, is from zirconia itself, and also it is much more biocompatible when used in small quantities. So this is the reason why this zirconium carbide had such higher biocompatibility. So more experiments are in progress actually to understand the combined effect of microstructuring and coating. We have already started this, and very soon we would try to start in vivo experiments for the ultimate verification of laser surface treatment. So thank you for your kind attention.
Thank you. Thank you very much for an exciting talk. You have covered this CO laser,
yes,
and biocompatibility of materials, how the surface modification assists. The session is open for questions or discussions. So 5 minutes for that. Any question? Comment? Yeah, please, sir.
Well, I will be quick. So what's the CO concentration in the active concentration?
It's about 0.1% kind.
But that
in
changes.
Yeah,
but that changes.
That changes, yes.
So then when you have these 3 emissions, then the concentration.
Which emissions, sir?
You said there are 3 emissions, no? Or when you have the mixture, CO active medium.
CO2, nitrogen, helium, and oxygen.
No, these are the gas mixture,
Yeah.
but you have a single wavelength?
No, it's a multi-line. When it is operating in free running condition, it is multi-line, and that is because of the cascade kind of lasing. So basically between 2 rotational levels there is partial inversion, lasing happens, then inversion is created in the next ones, again lasing happens. So this is a cascade type of lasing.
If you keep at room temperature, then
Room temperature, CO is not, it doesn't laze. Yeah, but there are some experiments which are happening where you can get CO lasing at room temperature, but by changing the gas mixture in some manner.
okay. Now about the other part, the PLD of
alloys. Yeah.
So generally PLD you cannot make more than not even a micron thickness.
No,
generally
no, 200 to 400 nanometers.
Very
yes,
small thickness.
Yes, yes.
And you have a sharp interface.
Yes.
And this interface is almost like a non-compatible. Of course, there'll be some bonding.
There is, yes.
But then in orthopedic implants, do you think that 200 nanometer is sufficiently thick? And
so we have tried also to see the adhesion of this surface coating which has formed. And we find that it is with alcometers we have tried to test. And then we find that the coating sustains.
No, that in actual body fluidic condition, when
yes,
you actually have wear and tear.
We have seen in flowing SBF conditions. Yes, it seems to be sustaining, but then we will do the actual tests later.
Okay, thank you.
Padma, let me just ask one curiosity-driven question. Very nice talk indeed. So when you say that biocompatibility, basically the material which was not biocompatible otherwise, so your surface modification?
No, initially it has to be, see like titanium alloy, we know that titanium is bio-inert. I mean, that means the body takes it, but it is not toxic to the body, but we can try to make it more adaptable to the body by this kind of structuring.
Okay, fine, thank you.
Yeah, if there are no more questions, I'll ask just one or two.
Yes, sir.
Is there any special distribution of CO in the generation? Because electric discharge has a striations, etc.
Yes, because as the CO2 is entering and as it passes through, the concentration of CO2 is also changing because part of it is freezing and also as it is going that concentration. So there is a gradient of CO as well.
So you have to remain tuned to the particular line. In particular
multi-line
application.
oscillation, there is no problem. Even in grating tune, there is no problem.
Okay.
But we are trying to actually insert from two different, have two inlets to the gas.
Fine,
so as to make it.
That's clear. Yeah. And you talk of groove structure.
Groove,
so,
yes.
Yeah, is it having directionality?
Pardon, sir?
Directionality, in which direction the grooves will be?
Right now, it is. Right now, we have a square kind of a thing.
Because
where we have
when the bones will be, when it is actually implanted, the directionality will matter in which direction.
Directionality can be made as per the requirement. Yes.
Fine. Thank you very much for a nice talk.
Thank you, Dr. Nilaya. Now I request
just a second.
Nakhe Saab.
Just a second.
Hey, Padma, I just wanted to ask. See, when you are grating tuning, and you were saying that some of those wavelengths are not reported in the literature, I couldn't make out. If it is a CO laser,
no,
all the...
in the wave, wherever grating tuned, configuration of CO has been reported, the various wavelengths are reported in that, but these wavelengths are generally not seen there.
I mean, they are from...
They are of CO transitions, of course.
CO,
yeah, they are CO transitions, but not reported as lasing output from a CO laser.
Okay, thank you.
Yeah, now I request Nakhe Saab to present a memento to Dr. Padma Nilaya. I request Priya Dangi to bring the memento.
Check, hello.
Yeah, our next speaker is Dr. B.N. Upadhyay. He's from RRCAT. He's heading high power solid state lasers division there, and he's research interests are in high power solid state lasers, laser material processing, fiber optics and optical engineering. He has been awarded DAE-BRNS award for technical excellence and group achievements awards. He has been also awarded Nuclear Power Corporation of India Limited High Performance Annual Award and 2 PCT and 1 Indian patent, and he has 55 journal papers to his credit and 180 conference papers. His work has been highly appreciated by Nuclear Power Corporation of India Limited because it has resulted into a lot of economic benefits and unique contributions in the world in the area of lasers for nuclear reactor life extension and maintenance. So Dr. Upadhyay, 25 minutes for your presentation and 5 minutes for discussion.
Yeah, it's all yours. Okay, good afternoon to all of you, and thank you, Dr. Nakhe sir, for nice introduction. So, this topic on the high power solid state lasers for nuclear field applications becomes more important when we are talking about sustainable development, and nowadays we are talking about 100 gigawatt of nuclear energy as an energy mix for development Viksit Bharat in 2047. So, outline of my talk is like, first I will introduce a brief what are solid state lasers, and then high power solid state laser development at RRCAT, then material processing technology developed at RRCAT for nuclear field applications, which include in-mass coolant channel replacement, single selected coolant channel removal, triangular block cutting, water jet assisted underwater cutting, laser cutting of large diameter pipelines, laser welding of fuel pins, laser welding of brachytherapy assembly, and then laser pinning system. So, when we are working in a normal job shop or anywhere, then there are no restrictions and we can do anything. But when we are utilizing lasers in nuclear field, there are several issues. Like one is the radiation dose. It can be internal and external, and when we go for doing anything inside the reactor, we have to be worried about radiation dose. And then there are several space restrictions due to location of the job. So there is a space restriction, means in a minimum constrained region we have to do the job, like cutting or welding. Then there is a unique nature of problem. Every problem is unique, and every time we have to see for different kind of toolings. And then safety of reactor means we don't have to do any hazard or any problem in the reactor, so that it is a large construction. Then secondary waste generation, it can be liquid waste or solid waste, so we have to worry about that. So, and there is no provision for trial and error. We cannot do any trial and error, so that cost involved and as well as time and other things will be lost. So we have to be dependent on training of unskilled manpower, because it is required that we cannot do the job, because there is a maximum dose limit for a person, like 5,000 mR per year for a nuclear industry employee. So based on these restrictions, and there are several type of cutting requirements. Sometimes it is required to have a dry air environment, sometimes underwater cutting environment with gas jet assisted or water jet assisted. Then welding requirement also is there. Sometimes it is autogenous, sometimes it is with filler wire. And our strength, we can see that we are developing laser systems in-house, and we are tailoring the systems depending on the needs. And different types of laser material processing techniques we are also developing, and design of tools and manipulators as per field requirement. So laser material processing basically provides the advantage of reduction in radiation dose, time and cost. So laser material interaction, if we look, laser acts like a thermal tool, and when it interacts with the material, some part of it is absorbed and some part it is reflected. And depending on the material, absorption will be different. So we have to optimize various parameters, like its wavelength, peak power density, beam quality, all these parameters. Then in cutting case, there will be either melting or vaporization, and we have to use an assist gas to remove the molten materials. Like if assist gas is oxygen, like a reactive gas, then exothermic reaction will take place and it will help in cutting. But if it is inert gas, then exothermic reaction will not be there. So we have to provide more power. Like power density requirements is like in melting, we require about 10 to the power 5 to 10 to the power 7 watt per centimeter square. So, and in vaporization, we have to go to 10 to the power 7 to 10 to the power 9 watt per centimeter square. And beyond that, it is not of any use for material processing applications. So, we have to be mostly material processing applications will be in the range of 10 to the power 5 to 10 to the power 9 watt per centimeter square. So, in solid state lasers, basically if you look at the technology, then there is a laser material, that is a gain medium, and there is a pump source, it is either flash lamp pumped or diode pumped, and we have a resonator. So, there are three regimes we can say, that one is lamp pumped solid state laser technology, diode pumped solid state lasers, and the fiber lasers. And modes of operation, it can be either continuous or pulsed mode. In continuous mode, we will be having a continuous laser output. In pulse mode, we will be having a pulses of different duration. In free running mode, we can generate pulses in the range of about 50 microsecond to 42 millisecond, depending on the pump pulse length. And in Q-switch lasers, we can have it depends on the round trip time and loss modulating element in the resonator. Then mode locked lasers, we can have femtosecond to picosecond pulses, but mostly we are utilizing free running type of lasers and Q-switch lasers for various metal processing applications, because in nanosecond and femtosecond region, we have to, means it will be only on the surface, but for deeper cutting or welding applications, it has to be in the millisecond region so that it can penetrate deeper into the material. So here, if you look at the bulk solid state lasers versus fiber laser, then there is a gain medium here, and we have a gain medium, and we are pumping by some means, whether it is a flash lamp or a diode pumping, and there are two mirrors. One is highly reflecting, one is partially reflecting, and crystal can be Nd:YAG rod or it can be other crystals also, and we have a flash lamp. Then in fiber lasers, basically because of these two mirrors, it has a certain misalignment sensitivity, and when we shift the system from one place to another, it has to be realigned and get the power output to be maximum. In fiber lasers, basically it is all fiber integrated system which is pumped by diodes, and we have a gain medium, it is all integrated along with the mirrors which are in the like a fiber break grating mirrors, and it is integrated with the system, so there is no misalignment, and we also get a very good beam quality of m square about 1, and heat load is also very less as compared to these bulk solid state lasers. So based on these techniques, we have developed several laser systems, and one of these is our basic workhorse, like a 250 watt average power pulse Nd:YAG laser. It provides, it has a reflector, it can be either gold coated reflector or it is a ceramic reflector kind of thing, and this is the kind of resonator in which rear mirror is 5 meter curvature, and here it is output coupler is 50 to 60%, and it provides average power of 250 watt, pulse energy of 100 joule, 5 kilowatt of peak power. Pulse duration we can vary 2 to 20 millisecond, and repetition rate in the range of 1 to 100 hertz. It is delivered through optical fibers of 600 to 400 micron. Although efficiency here is less, but it is very much useful, and it can cut up to 12 mm thick steel sheets, and about 2 mm depth of welding can be done in SS, and several such systems we have installed in DAE units. Another system of the similar type, it is pumped by two flash lamps, and we have resonator mirrors again here. There is Nd:YAG, similar type of Nd:YAG rod. But here you can see average power has increased to 500 watt, and peak power is about 10 kilowatt with pulse energy of 300 joule. So this has a capability to cut about 25 mm thick in steel, and it is about 4 mm depth of welding can be done by using this laser in SS. And about 6 such systems we have deployed in various DAE units. Then further, we have developed a 1 kilowatt Nd:YAG laser. It uses 2 Nd:YAG rods in a single resonator, and there are 4 flash lamps. It is driven by 2 power supplies, and each of 10 kilowatt, and it provides 1 kilowatt average power and 20 kilowatt peak power, and pulse energy here you can see it has 600 joule, and again the peak power is 20 kilowatt. It is delivered through 600 micron fibers. It is capable of cutting up to 35 mm thick sheets. So, and welding can be done in SS up to SS and copper, aluminum, all other materials we can do the welding. Here also efficiency is 5% above. Now recently we have developed a 4 rod based, a single resonator 2 kilowatt system, in which there are 4 rods and 8 lamps. These are driven by 4 power supplies of 10 kilowatt each, and here you can see the peak power is 40 kilowatt, and pulse duration, pulse energy about 600 joule again, and we have delivered it through a 600 micron fiber. So here you can see the linear output variation. So here the problem is in solid state lasers that these rods have to be identical and its thermal lensing has to be identical in the resonator, otherwise power coupling from one rod to it will not happen, that just it is by putting several rods we can just multiply the output power. So we expect that it will be able to cut up to 40 to 45 mm thick sheets and about 8 mm depth of welding in SS, but we have not yet utilized this for any application reactors. Further in fiber laser stream, we have developed 500 watt Nd:YAG fiber laser. It is all fiber combined and we are pumping with 915 nanometer laser diodes. There are 6 diodes, such diodes. Here you can see the combiner and 5 brake grating mirrors. Then output we are getting through a QBH delivery fiber. Here the efficiency is very high as compared to 5%. Here you can see the efficiency is 71%. And this we are utilizing for cutting and welding applications, as well as it can be deployed for lime applications also. And further in this direction, we have developed 1 kilowatt monolithic all fiber laser. And here you can see the cutting can be done by using this laser. It has been integrated into a single cabinet here. Efficiency is again 74%. And beam delivery through 20 micron fiber. So very fine cutting can be performed using this laser. So here 2 kilowatt, another laser we have developed 2 kilowatt, in which actually 1 kilowatt lasers we have developed, but by combining several lasers, we can go to much higher powers. Even this is a signal combiner in which several modules, there are 6 ports, and if we combine 1 kilowatt each, we can generate about 6 kilowatt output. So based on 1 kilowatt basic fiber laser, we have just combined 3 fiber lasers of 700 watt each to generate, these are the 3 units, 1, 2, 3. And by using a signal combiner, we have generated 2 kilowatt output, and it will be integrated into single unit for material processing applications. So based on these lasers, we are doing several material processing applications in reactors. Over the years, during last several years or 15 years, you can say, we have deployed these Nd:YAG lasers as well as for various material processing applications, and this count is increasing. And recently we have done 30 mm thick recirculation loop cutting in TAPS 1 reactor in 2023. Then here you can see in reactors what happens. There are several coolant channels. These are called coolant channels, and in one coolant channel there is a pressure tube. It has a limited life because of high pressure, high temperature, and neutron field. And there is a hydride pickup in the pressure tubes, and this gets means there will be certain cracking or hydride pickup will be there, and after a time of about 10 to 15 years, we need to cut these pressure tubes and remove all these coolant channels so that it can be refurbished with new fresh pressure tubes. So if you look at the various things here, it is about 2 meter deep. This is the end fitting, and at the end there is a bellow lip which has to be cut for its removal. So here you can see the internal. So there are several obstructions, like feeder pipe is there, yoke assembly is there, then there is a bellow lip which is very much deeper into the thing. So for cutting application or removal of these coolant channels, we need to remove first all these feeder pipes, this yoke assembly, then only we can access to this bellow lip and then cut and remove these coolant channels. So here you can see we have developed a tool which is there is a optical fiber beam delivery for the beam, and about 15 joule with 15 joule of pulse energy, 3 millisecond duration, and 17 hertz rep rate, we can cut in a time of about 6 minutes this one of the bellow lips, and this coolant channel can be removed. Here you can see a small movie, I think, whether it will work or not, I don't know. So here it is in the working in the reactor. So you can see the tool has been deployed in the reactor, and actual cutting is taking place in the reactor. So you can see that these are remotely operable. So because of remote operation, radiation dose will be minimized, and you can say that about as compared to mechanical methods, it has been estimated that mechanical methods it will require 3 months time to remove all the 612 bellow lips. But by using laser technique, 1 week is sufficient, and we have already deployed in 6 reactors, and a lot of man-RAM saving has been done by using this laser technique. Then further, one of the problems, like there is a study on enhancement of life of these pressure tubes, and for that single channel removal is to be required. Even in the running, means on condition, or when there is a fuel in the coolant channels, it becomes very difficult to remove one of the coolant channels. So it is required that a single selected coolant channel, based on EARB recommendations, we have to remove out of 306 coolant channels in 220 megawatt reactor, or one of the coolant channel in 540 megawatt reactor. So that technique, it requires, there are several constraints like hindrance of feeder pipes, yoke assembly, and nearby coolant channels. So there is a technique that we have to first cut the pressure tube from inside. Then there is a liner tube which has to be cut by laser method. Then end fitting has to be cut. Outboard end fitting will be removed. And then using the space of outboard end fitting, laser cutting has to be done for the bellow lip, because bellow is not directly accessible in case of single channel removal. So after cutting of bellow lip, inboard end fitting is removed, and then underwater cutting for retrieval of pressure tube is performed. So here you can see these are the various tools which have been developed. So for cutting of end fitting, it is again a fiber optic beam delivery. There is a nozzle, bending nozzle you can say. So it can be inserted inside this end fitting pipe, and we can cut liner tube and both end fitting. There is a controller for this. And after cutting of outboard end fitting, we deploy this another tool for cutting of the bellow lip. And once this cutting happens, this inboard end fitting can be removed, and then pressure tube as well as from both the ends we have to do similar, and all the coolant channels, one of the coolant channels can be removed. Next, for pressure tube, actually PI studies are done for the roll joint area, because roll joint area where pressure tube, it is made of zircoli, and there are 3 groups here you can see. It is roll joint with the end fitting. So it has to be tested for PI studies, means what has happened means most of the crack happens here. So for that study, it has to be done, underwater cutting has to be performed. So we have devised a tool 2 meter long, and it is again a fiber optic beam delivery, and there is a nozzle. So here you can see a water tank in which this laser tool goes, and there is a fiber optic beam delivery again goes, and it cuts in several pieces of this pressure tube roll joint area, so that these pressure tube stubs can be removed, and then PI studies can be done. So it requires a lot, because of high radiation dose here, no one can go there, and we do it remotely from a long distance about 50 meter, so that means the radiation dose is minimized. Here the requirement is, you can see the energy requirement has increased, because this is a pressure tube and it has to be done by compressed air. So here you can see the energy requirement has become 35 joule per pulse, and about 8 milliseconds, and it takes about 12 pieces has to be cut, and about 18 meter length, and about 5 hours of time is required. Next, here you can see after cutting of these pressure tubes, it is shifted to PID, and we have recently given a system 250 watt ND-YAG laser to cut out the sample pieces, so that stress testing and other parameters can be done by using this thing. Otherwise, so this laser is deployed in hot cell, means mostly the things, these pressure tubes will be kept in hot cell because of high radiation dose, and then these pieces will be cut by using manipulator, and then stress studies can be done. So here you can see another problem of yoke assembly. Sometimes actually in RAPS 3 reactor there was a problem of triangular block. So this triangular block, in place of a rectangular block, there was a triangular block. So it was like in 2 years, there is a gap creep adjuster in each reactor. So these bolts are opened, and by 2 mm there is an increase in length. So after a 10 to 15 years of life, this has reached to its end. Here you can see at the end it has reached. So this triangular block was creating a hindrance that no further creep adjustment can be done. So for that purpose, it was required that if we can cut this triangular block in an arc and remove this 18 mm thick piece, then reactor can be operated, or some coolant channels can be operated again. So for that purpose, again we have devised another tool here. So this tool can move in a circumference and in a circle, and it can remove the triangular block. So here you can see how it is working there. In reactor, actual piece, it is cut like a triangle here you can see, and the tool which was deployed here, it was, so here the cutting requirement restriction is that this yoke should not be cut, only the triangular block has to be cut. So laser beam is, cutting is done in multi-passes so that there is no effect on the yoke assembly, only a triangular block comes out and rest of the pieces retain as it is. So in RAPS 3 reactor, it was done during the period of 2014 to 2021. About 64 number of triangular blocks were cut in 32 channels, and you can say that we have averted the quarantining of several channels, and power generation loss of about 160 mega unit per year was saved. So here you can see another example in which several pipelines are required to be cut for replacement of some of the components. So one of the things is laser cutting of secondary shutdown system pipeline for replacement of double check valve. So there was a double check valve nearby this pipeline. Here you can see the double check valve. So nearby there was a space restriction. So this pipeline was to be cut, and laser system was delivered through optical fiber again, and we have devised a tool so that it can circumferentially cut. No mechanical tool was possible because there was a hindrance from the all the sides of this thing. Only 300 mm space was available. So within 300 mm space, you can see the cutting was performed, and in the next slide you can see this how it was done. So here you can see a small movie, and this is the laser system is running, and here you can see the laser beam is coming, and slowly we are moving. And after cutting, this was again welding was performed with the after replacing this double check valve. So another example of large diameter pipeline cutting. Here you can see in TAPS, recently it was done in TAPS 1 reactor, TAPS 1 and 2 in both. It has already lived a life of 40 years and of power generation. So it was required that these pipelines, which were called recirculation pipelines, these got intergranular stress corrosion cracking, and there was some leakage in these pipelines. So it was required that to be these pipelines should be removed and by any method, and then after cutting, these tubes need to be replaced. This is SS 316 tube. It is a very large diameter, about 700 mm diameter and about 30 mm thickness. So we have developed a tool which can rotate around the circumference of the pipe, and there is a nozzle, again a bending nozzle through optical fiber delivery, and using a 1 kilowatt fiber Nd:YAG laser. It is again a pulsed laser, and by deploying this tool, we have cut in the circumference, and in one pass we are able to cut up to 30 mm thick steel, and we have deployed in TAPS 1 reactor, and one of the critical locations in which no other mechanical tool was possible to be deployed, and it was done successfully. And later on, all the pipeline of about very long pipeline in several pieces was cut and removed. Further, you can see this is another application. It was done very much earlier in 2014-15, but is a different technology in which underwater water jet assisted cutting was done. So if you see, laser beam is coming, and if you can guide through water, water will work like a optical fiber. So after focusing the beam, it is guided through water. So it was required that in Dhruva reactor, there was a SFSB pool of 5 meter deep. So from the 5 meter top, and there were several tubes lying on the ground, and these tubes were having a bottom bulge portion. So it was required to salvage these tubes so that fuel can be removed from those, and water contamination can be avoided. So it was having a wall thickness of 2.5 mm, and here you can see a small just working movie how it is cut underwater and with water jet. Here no gas assist is there, water is provided through here. 2 minutes. So here you can see water jet is coming through another nozzle, and a laminar flow is maintained, so that with a gap, very small gap, we are able to cut this tube. And several such tubes were salvaged, and the whole, it is the actual reactor SFSB pool where you can see from the top we are operating. These are the optical fibers lying there, and these are the ends of the tubes which were salvaged, and several such tubes were done. About 12 number of tubes were done, and with water jet cutting you can see that there is no airborne activity, which will be because of no turbulence in the water. Here this is recent application in which you know that cobalt requirement has increased recently because of its utilization in sewage treatment. So recently it has been planned in DAE that in 19-pin fuel bundle, central pin will be of cobalt, and when it is radiated for 2 years in reactors, this will be converted to from cobalt 59 to cobalt 60, and then it has to be cut, means central pin has to be removed in water pool so that it can be extracted and for sewage treatment can be utilized. So the criticality is that no other pins should get damaged. Only we have to cut this end plate at 2 locations, but laser will move in a circle, and one point we have optimized this process and already installed the system at in Kaiga 3 and 4. Looks like this. There is a nozzle on both the ends, and it will cut from both the ends of the fuel bundle, and it will be removed. So here another example in which laser beam is utilized for welding application. So this is a 500 watt Nd:YAG laser, and we have given 3 units at FF-BRC Tarupur for welding of PFBR fuel pins. So it is a fuel pin SS316L, and SSD9 tube is there, and SS316LN plug. So these are dissimilar materials, and welding we have optimized the process, and it has been utilized for production of these type of fuel pins at FF Tarapur. So this is another example in which zircaloy pressure tubes have been welded. 4.3 mm thick welding can be done in pressure tubes, and this has been pressure tested up to 450 bar of water. 2 more examples, just these are the few last slides. So here you can see a laser system we have developed. It is a micro welding system in which a very tiny capsule like this, it is a titanium capsule, there is an end cap, and this end cap has to be welded by putting a iodine source inside. It is a low dose source and about 3 to 4 millicurie source. So this welding is very difficult by any other method, but laser welding can be deployed, and we have deployed this system at RPSD-BRC, and they are producing this kind of capsules for eye and prostate cancer treatment. This kind of plaque they made, several capsules are kept there, and then it is means doctors utilize in various hospitals. So here another example, it is a micro welding example in which we have developed a welding system. It is a workstation in which a very tiny source of iridium, it is a high dosage source, so it cannot be done outside, it has to be done inside hot cell. So this tiny source is a 10 QE source, and it has a 1 mm diameter only. So with 1 mm diameter and 80 micron wall thickness, it is very difficult to weld by any conventional method. But laser welding has been deployed to weld at 3 locations, and we have provided it to Brit, and they are now producing this kind of assemblies. Just to give an example, another laser system is a 10 joule pulse Nd:YAG laser pinning system. Just last slide. So laser sock pinning system we have developed. It is a 10 joule, 10 nanosecond system, and it is being utilized for pinning up application in which a tape is kept on the surface, and a high energy pulse beam falls on that. It creates plasma. So plasma creates a shock waves, and it means atoms or residual stress is avoided. So in BRC, actually for BRC requires several types of several DPSS green laser systems. So we have developed a 50 watt average power pulse green laser with 532 nanometer wavelength and about 6.25 to 9 kilohertz pulse this repetition rate with 45 nanosecond pulse duration. About 15 such units have been provided to BRC, and they are utilizing it for medical isotope separation program, and in future it will be more systems, such systems are required at BRC. So I will conclude with last slide that we have developed about 250 to 2 kilowatt average power Nd:YAG lasers with fiber optic delivery, and up to 2 kilowatt all fiber integrated wide doped CW fiber laser systems, and installed in various DA units. There are several innovative laser metal processing techniques have been developed along with tools and manipulators, and they have been deployed for maintenance in nuclear power plants, which has eased the process, reduced man-random consumption, time and cost. Now we see that laser-based technologies have potential to solve many more nuclear field-related issues such as decontamination, pinning for life enhancement of reactor internals, laser welding of reactor components, etc. So in future we look forward that these techniques will be deployed in a big way. So last slide, just I will conclude with that. I will acknowledge this was possible with a team of several members, management from RRCAT, then team members from NPCL sites, BRC, IGCAR and BRIC, because without their help it was not possible to do all these things, and all my team members. So thank you.
Thank you, Dr. Upadhyay. And the session is open for discussion, comments or remarks. Yes. You may introduce yourself first. So.
Myself, Dr. Dhara from IGCAR. Thank you very much for not only this talk, also to your wonderful service to all the sites, including, excluding of course our DAE also. Many other places also you do it. Otherwise, I have a naive question, not to your technology, you are too hi-fi. That is, you saw somewhere that iron and oxygen is making Fe3O4.
Yes.
How you can make that phase formation is quite critical in Fe3O4.
No, it is actually when laser beam falls on the surface, it is being absorbed into the material.
Correct.
And oxygen we are providing.
Now, I'm talking of that phase particularly, Fe3O4 phase, which is one of the metastable phase of iron oxide. FeO is fine, Fe2O3 also fine, but Fe3O4 is
No,
one.
actually, when it is a powder, it is a kind of powder kind of thing. It comes out at the surface, these debris which are coming out, if you analyze that, it is not on the surface, it is just the powders which has come out. It is burned, when Fe is burned with oxygen, Fe3O4 or Fe.
Anyway, we'll discuss this. This is slightly more differently. Thank you very much.
Yes, any more? If no more questions, let us thank the speaker. And I would like to add that this has saved crores of rupees, because you must be knowing one reactor down for one day will cause a revenue of loss of at least 1 crore, and it saves at least 2.5 months per reactor per maintenance CCR cycle. And as I know, this taps cutting, there was a foreign quotation which was to cut around one channel, one pipe. It was around, they were charging around 1 crore, and this was in-house developed technology that has helped a lot. I think there is a lot of scope for such type of innovations and contributions from young researchers here, where we can directly contribute to the nation's development, and lasers are already there. Thank you, Dr. Upadhyay and your team.
Thank you,
sir. May I request Nakhe Sahab to present a memento to Dr. Upadhyay. I request Vaishali to bring the memento to the dais. Now it's time to honor our session chair. May I request our chief guest, Professor Manna, to come to the dais and present a memento to Dr. Nakhe. I request Aparna to bring the memento to the dais. Thank you, sirs. I have an important announcement to make. The poster session is from 2 to 4:30. The judges have reached the venue, but it seems students have not pasted their posters there. So I urge the poster presenters of this session to try to rush and put their posters as early as possible. Now we disperse for the lunch.
लेजर पॉइंट है वो काम नहीं कर रहा। नहीं नहीं वो प्रॉपर प्रेस नहीं होता इसलिए।
माइक बोलने वाला है अपने पास है ना पूरी प्रोफाइल यार फिर हेलो हेलो मैं है योर अटेंशन प्लीज। हाँ जी रोहित जी आपका क्या सवाल है बताइए। कितने बाकी है मैं बता रहा हूँ भैया कितने बाकी है। अब आपके सामने एक मुजरा पेश किया जाएगा।
welcome back. We are going to commence the fourth session, which is on biophotonics, and I request Dr. S.K. Majumdar to come to the dais to chair this session. By now, all of you are very much familiar with Dr. Majumdar as ILA president and chairman of all this. But this slide is about his research work. So, apart from being Director, Material Science and Advanced Technology Group of RRCAT, he heads the Laser Biomedical Application Division and Medical Division, 2 divisions of RRCAT. So he's an expert, internationally acclaimed expert in optical spectroscopy, imaging for biomedical diagnosis. His list of awards he has received, I think only since there was limited space for 6 awards only, so they are listed here. I won't read them here. And over to Dr. Majumdar. So.
So thank you, Ajit, for your kind but unnecessary introduction. Welcome to this session, the second technical session of today. And this session is on biophotonics. And we have 3 speakers here. The first speaker is Professor Manik Pradhan from S.N. Bose National Center for Basic Sciences, Kolkata. Manik is basically an authority in spectroscopy, and he has done a lot of work, and you can see from his list of recognitions, awards, etc. So without taking any time, I would request Manik to present his talk. It will be 25 minutes, Manik,
okay,
plus 5 minutes
fine, yeah.
for discussion.
Okay, thank you so much, Professor Majumdar, for your kind introduction. Pleasure and honor to be here today. My sincere gratitude to all the organizing committee members and the conveners for having me here and giving me an opportunity to present our work in this wonderful platform. Thank you so much. Here is the title of my talk. So in this talk, I will give you a brief overview of cavity ring down spectroscopy, its magic trick, and try to explain how these spectroscopic signatures can be used for disease detection. So before doing this, let me briefly share your research activities. So our research is highly interdisciplinary, so and at the boundary of physics, chemistry, and material science. So while we do basic research, so we also do application-oriented and technology-driven basic research in chemical, environmental, and biomedical sciences. So in the domain of experimental laser spectroscopy, so we do high-resolution spectroscopic investigation of molecular or vibrational levels, sensing of trace molecules, isotopes, and nuclear spin isomers. So not only in the gas phase, but also in the condensed phase to understand the real-time interfacial dynamics and aggregation kinetics. In the domain of nanophotonics and precision metrology, we do the quantum weak measurement to understand the very tiny weak optical phenomena in different materials such as half-wavelength scale. And in the domain of plasmonics, we do the surface plasmon resonance to understand the various chemical and biomolecular interactions occurring at the interface. Okay, so in the last few years, we have developed several new generation optical techniques like cavity ring down spectroscopy, evanescent wave cavity ring down spectroscopy, wavelength modulation spectroscopy, surface plasmon resonance, and quantum wave measurement in the domain of spectroscopy, photonics, plasmonic sensing, and precision metrology. But today I'll only mainly talk about cavity ring down spectroscopy only in the gas phase. Okay, so you know that traditional absorption spectroscopy is based on the Beer-Lambert law. So this is the Beer-Lambert law. So this law essentially tells you the relationship between the absorbance and the concentration of a molecular species. If we know the incident light intensity I naught and the transmitted light intensity I passing through a sample cell, we can easily calculate the concentration X of a particular molecular species if we know the absorption cross-section sigma at that particular wavelength. Now the traditional absorption spectroscopy has two main drawbacks. One is it has a very limited sensitivity. So we can measure the minimum absorption coefficient of the order of 10 to the power minus 4 to 10 to the power minus 5 centimeter inverse. And another major drawback is lack of selectivity because of overlapping absorption features at a particular wavelength due to multiple absorption. But we can avoid these two fundamental issues by the cavity ring down spectroscopy. Now let me briefly tell you how these spectroscopy techniques work. So this is the high finesse optical cavity consisting of two ultra high reflectivity mirrors, the reflectivity greater than 99.99%. The laser light is injected along the central axis of the cavity. Most of the light is reflected straight back of the input mirror. Only a fraction of the light is transmitted through this input mirror. Then the light bounces back and forth inside the cavity. This is called the cavity's ringing. Now when the light is moving back and forth inside the optical cavity, at each reflection a very tiny amount of the light is transmitted through this output mirror, and if you keep a detector here you can see an exponential decay of light. So in this way you can trap the laser light for the order of microsecond, and this gives huge effective path length few hundred kilometers, far better than for any conventional multipass absorption cell. Suppose there is no sample inside the optical cavity. Then the leaking light intensity can be described by this equation I is equal to I naught e to the power minus t by tau 0. This tau 0 is called the empty cavity ring down time. Now if you put some gas sample inside the cavity, then the rate of decay becomes more faster. That is called, then we will get the tau. Now if we know the change in ring down time or decay rate, tau and tau 0 with and without sample, we can easily calculate the concentration X of a particular molecular species if we know the absorption cross section sigma at that wavelength and sees the speed of the light. And we can also calculate the limiting sensitivity by measuring the alpha min. So basically tau 0 is the characteristic lifetime of the light inside the cavity. Longer the lifetime means better sensitivity. Another beautiful thing is that you can see that the ring down time depends only on the length of the cavity, the distance between the two mirrors, and the reflectivity of the mirror. So by measuring the ring down time rather than the absolute intensity of the laser pulse, short to short variations of the laser output is completely removed from your final spectrum. So it is insensitive to laser intensity fluctuation. It is a time measurement, not the intensity measurement. Okay, so now I'm not going to talk about all the technical details here due to time limitation. So now the question is how the light is trapped inside the cavity. The light is trapped inside the cavity only when the laser frequency is matched with the frequency of the cavity mode. So this is actually the output signal from the oscilloscope when the laser frequency is actually matched with the cavity mode, and this is the ring down time. Now the question is why this cavity ring down spectroscopy is so unique. The thing is that it is an ultra-sensitive detection method. The minimum absorption coefficient you can measure 10 to the power minus 11 to 10 to the power minus 13 centimeter inverse. So 10 to 100 million times better improvement in sensitivity. We can measure the gas sample parts per billion to parts per trillion levels without any secondary calibration. And it gives the direct quantitative absorption measurement and the measurement done in the time domain. And we use the quantum cascade laser in the mid-infrared region. So the quantum cascade laser give you the extremely high resolution. So resolution is 0.0001 centimeter inverse. Okay, so and this is, so basically we will give, so we will get the high resolution, so that much resolution, and the sensitivity is parts per billion to parts per trillion level. So this is the beauty of combining cavity ring down spectroscopy with quantum cascade lasers. Okay, so now in recent years the technique has been modified greatly. So, and found huge applications in a varieties of fields. One of the most fascinating areas is the medical science. And the most important thing is that this cavity ring down spectroscopy is a general technique. You can apply anywhere of the electromagnetic spectrum. It is valid for ultraviolet, near infrared, mid infrared terahertz region. So depending on what kind of applications you want to do, you have to only change the laser and optics. But the basic principle remains the same. Okay, so I will talk about the cavity ring down spectroscopy medical diagnosis. How we do, we'll collect the breath sample, inject the optical cavity, shine the laser beam on the molecules, do the high resolution spectroscopy, and try to find the new breath prints in our Excel breath, which are associated with the diseases. So, okay, so there are many slowly progressing diseases like heart disease, lung disease, peptic ulcer, cancer, diabetes, SIBO, CKD, gastric disorder. And a disease is only detected once the symptoms occur. But the main problem is that most of the diseases remain asymptomatic and undetected for a long period of time. So we cannot stop a disease. But what we can do that, we can catch and treat it early, way before any symptoms occur. So in medical science, it is called the medical screening. And the test can be done so rapidly and easily. But many of the existing methods are exactly opposite. So therefore, we need to develop a new methodology. One of the medium is our breath, so which has long been actually overlooked. Because our breath is easily accessible and non-depletable as compared to the endoscopic biopsy and the tissue samples or the blood samples. So endoscopic biopsy, that is tissue samples, turns out the breath biopsy, that is the Excel molecules. So okay, now you know that the fingerprint have been used to solve mysteries for generation. Similarly, we have the unique fingerprint or the breath print which are associated with the disease that doctor could use to diagnosis. So therefore, breath analysis would be a promising technology where disease detection, diagnosis, and treatment can happen at the very early stages way before any symptoms occur. Therefore, it will certainly be a game changer in medical science. Okay, so now the first question comes to our mind, what are the molecules actually present in our breath? So, okay, so every time we exhale, if we do something like this, actually we are giving 4,000 molecules in our breath. And so the major component, we can see the nitrogen, oxygen, carbon dioxide, and water vapor. We also exhale a very large number of different volatile organic compounds, alkane, aldehyde, ketone, alcohol, sulfite, amine. But interesting thing is that when we have any disease or metabolic disorder, this chemical composition changes. And underlying chemical reaction among the biologically relevant molecule changes. Then the second question comes to our mind, how breath molecules are produced? There are several reasons. The breath molecules actually produce endogenously because of some biochemical reactions occurring inside our body as a part of the metabolic process. They might come from any bacteria, microorganism, tumor cell, etc. And these are the typical molecules actually found in our Excel breath and their physiological basis. You can see that their concentration parts per billion to parts per trillion level. If you really want to detect such a level of concentration, you need an ultra-sensitive detection method. And these are some of the example, hydrogen sulfide, methane, and the nitric oxide and their physiological basis. Now, this is some typical examples of the CRDS cavity ring down spectroscopic signature of Excel breath molecules. This is the example of nitric oxide. We can probe the nitric oxide parts per billion to parts per trillion levels in our Excel breath by just probing this absorption or the rotational line using the quantum cascade lasers at 5.2 micron. This is another beautiful example. This is hydrogen sulfide. We know the sulfur has 3 stable isotopes, 32, 33, and 34. We can precisely monitor the 3 stable isotopes within a few seconds at parts per billion to parts per trillion level if we use the quantum cascade laser at 7.4 micron. So this is another example. The methane has the 2 stable isotopes, carbon-12 and the carbon-13. That can also we can probe in our Excel breath by ring down spectroscopy. So this is another example of the nitrous oxide. So we also know that we can also probe the water vapor. We know the 3 types of water, the H2O, normal water, D2O, heavy water, and H2O, semi-heavy water. If we have a mixture of H2O and the D2O, so there will be some kind of H2O is produced, but chemically we cannot actually probe the H2O. We cannot separate it, but spectroscopically we can probe it. So you can see that we can not only probe the H2O, we can also the triple oxygen content H2O. So at the same time, okay, so basically the isotope selective and oxygen content H2O that we can probe in our Excel breath. This is another example of human breath. Okay, so now I'll talk about some Excel isotopic molecules for medical diagnosis. We know that the carbon dioxide is the major metabolite in human breath, but it is not a disease marker itself. because depending on the basal metabolic rate, everybody's CO2 production will change. So, but if we look into the different isotopes of carbon dioxide, oxygen has 3 stable isotopes, 16, 17, 18, and carbon has the 2 stable isotopes, 12 and the 13. But if we probe the oxygen 18 and the carbon 13 isotopes of XLCO2, that may contain a signature of varieties of medical conditions that I am going to talk about. Now, the first question comes to mind, why we are interested of oxygen 18 measurement in our Excel breath samples? How does it actually come? So, there is some little bit biology is there. So, when the glucose is metabolized, carbon dioxide is produced, and oxygen 18 of CO2 is the third major abundant isotope of CO2. And now what happens is that in our red blood cell or erythrocyte, oxygen 16 of CO2 and oxygen 18 of water molecule, they are rapidly interchanged, and then produce the oxygen 18 isotope of CO2. Then oxygen 18 isotope of CO2 is transported through the blood, comes to your lungs, and then we exhale the oxygen 18. This is the actual source of oxygen 18. So now, these isotopic exchange reaction actually controlled by the carbonic anhydrase enzyme, which is present in our body. And this carbonic anhydrase also associated with the altered metabolism. Now, this is already known. Now, as the diabetic is an altered metabolism, we thought that there is some kind of connection of oxygen 18 with the carbonic anhydrase activity. Then it did the experiment with the real patient with collaboration with the hospital. So this is the things that how the oxygen 18 of CO2 molecule changes with time for the 3 different types of patient, normal, pre-diabetic, and the type 2 diabetic patient. And we also measured that there is actually significant isotopic enrichment and the depletions at the 120 minutes. And we also measured the carbonic anhydrase activity in the red blood cell. So you can see that there is a strong correlation between the isotopic enrichment and depletion. Then we found some kind of statistical analysis. It is widely used in the medical science, the ROC analysis, true positive versus false positive, sensitive versus specificity, and we found the different diagnostic cutoffs. And then, so basically, oxygen 18 of CO2 is a new breath-spraying for non-invasive assessment of diabetes. Okay, so then we try to focus, is there any kind of carbon 13 isotope of CO2 molecules? All are doing actually doing the spectroscopy, laser spectroscopy, nothing else, the rotational vibrational spectroscopy. So then, then what is the science and idea behind the measurement of carbon 13? As we know that in a type 2 diabetic patient, as the insulin is not working well, less glucose is transported through the cell. So basically then the 12 CO2 production will be less. We thought that if we can replace the 12 CO2 glucose by the 13 C enriched glucose, that is the CAG glucose, then the 13 CO2 production will also be less. That is the simple concept, and we found the exactly same thing. Type 2 diabetic patient exhale the carbon 13 in their exhale breath. Then we found the different diagnostic cutoff levels, how we can classify this a type 2 pre-diabetic and the normal patient. Now I'm going to talk about another problem, the diagnosis of Helicobacter pylori infection by cavity ring down spectroscopy. So this bacteria is usually found in almost everybody's stomach. And this bacteria is responsible for the development of peptic ulcer disease, stomach cancer, gastritis, even the type 2 diabetics. And more than 50% of the world population carry this bacteria, and in India 80 to 90% people have this bacteria. But the interesting thing is that this infection is often asymptomatic. Having said this, what I mean is that most of the time we really don't face any kind of sign or symptoms related to this bacteria. Therefore, early detection is very important before any complication happens. And we know that the standard method is endoscopy and the biopsy test. We all know it is an extremely painful method, and this kind of methodology is not suitable for routine clinical checkup and also not attractive for children, pregnant women, and also the elderly person. Okay. So then, okay, so this is the real fact actually. So this is very interesting things that, so this bacteria actually identified in 1982. Dr. Barry Marshall was convinced that H. pylori bacteria causes stomach ulcer, but no one believed him. Since it was illegal to test his theory on humans, he drank the bacteria himself, developed ulcer within days, treated them with antibiotics, and went to receive the Nobel Prize in 2005. So it took more than 20 years to believe in the medical community that H. pylori bacteria is responsible for the ulcer. So then what we did, our idea is very simple. It's a simple chemical reaction, urea hydrolysis. What we did that, actually we are given a 13C enriched urea, 75 milligram, it's FDA approved. This bacteria secretes urease enzyme. So, and in presence of urease enzyme, 13C enriched urea breaks down into ammonia and 13CO2. Then 13CO2 is transported through the bloodstream, comes to your lungs, and it will excrete carbon 13. that means if I have this bacteria in my stomach, I will exhale more carbon-13 than a healthy person, and that is exactly observed. So basically, endoscopy biopsy test by the breath print test. This is some kind of the examples on the real patient, the carbon-12 and carbon-13 isotope ratio. Okay, so now the question is that 13C urea breath test actually identify the presence of the infection, not any ulcer or non-ulcer patient. So this is then we found some kind of another breath print, so different, that is the mass specific breath print, then we actually combined with the laser spectroscopy. Then actually did this pattern recognition based clustering method. Actually collected, so more than 10 years actually we are collecting lot of data. Then we did this, the pattern recognition with K-means clustering analysis in the domain of unsupervised machine learning. And we found that there are 6 types of actually the patient. We can classify all the patients in 6 groups. And we can found that actually the dyspepsia, gastritic, ulcer, GERD, and the multiple diseases, so many things actually happening. And we can classify all the individual patients, which group they belongs to. And this is the patent granted, and this is some kind of clinical validation in the hospital. So we can identify the initial stage of infection, advanced stage of infection, diagnostic sensitivity and specificity is more than 97%. This is also some kind of clinical validation. Okay, now how this technique is so much robust. So after giving the medication, how do we know that the disease has been cured or not? Okay, without going for any second time endoscopy. Then we found that, so actually our breath print actually working fine. So we really don't need any second time endoscopy. Okay. Right. So this is so what we this is another problem that we exhale water vapor and isotopic fractionation actually happens. So the idea is that this kind of isotopic fractionation actually happens in our stomach. Then we track this actually HDO, because HDO actually we can probe in our exhale breath by means the cavity ring down spectroscopy. And then we did the experiment on the real patient. And we found that there is a significant difference of just semi-heavy water between the 2 types of patient. And also the diagnostic sensitivity and the specificity, we calculated also the cutoff value. So exhale HDO is a potential breath print for the H. pylori detection. And this is the prototype device, and this technology has already been transferred to a company, startup company, for successful commercialization. Okay, so and the patent has been granted. It's a huge societal impact because it's a non-invasive breath test. Okay, so it's a painless. There is no cross-infection. So you will get the result only the few seconds, and you can repeat your test as many times as you want. You can collect the breath sample from home, hospital, or whatever it may be. You don't need to travel in the hospital. Just collect your breath sample, inject into this our system, the pyrobreath, and immediately you will get the result. Okay, so this is some kind of media in the press, and this is the technology has been showcased. Now, I will give you 2 more examples where the cavity ring down spectroscopy would hold the tremendous promise. One is small intestinal bacterial overgrowth. The standard method is the endoscopy and the colonoscopy-based microbial culture of jejunal aspect. We know it's how extremely painful. But if we only track the hydrogen sulfide, so in our exhale breath, that measuring that hydrogen sulfide by ring down spectroscopy, we can classify actually who has the SIBO positive and who has the SIBO negative, small intestinal bacterial overgrowth. Because hydrogen sulfide is produced in human colon by sulfur-reducing bacteria. If you have this kind of bacteria and in IBS, irritable bowel syndrome patient, we can actually identify without going for any colonoscopy that you have this the SIBO positive or SIBO negative. Okay, the another problem is the end-stage renal disease in CKD, chronic kidney disease present during hemodialysis. This is really public health concern because at this stage the people need the dialysis. And it is extremely difficult to do the experiment because the dialysis is going on. We have to collect the breath sample from the patient. We need a lot of ethical approval, the consent of the patient, from the family. It's not easy to do the experiment. But fortunately, we did some patient, and some of the patients, unfortunately, they have the diet. We could not repeat this experiment. But the idea is actually valid. And we found that there is some kind of correlation between carbon-13 and oxygen-18 with the KTY-V values. KTY-V is a very unique parameter actually nephrologists use to make sure that the dialysis has been done properly or not. The current method is the people use the serum urea and the serum creatine, so during the pre and the post dialysis condition. Okay, so the conclusion outlook, our breath and mixture of volatile organic compound that we exhale hold tremendous amount of information on our physiological basis. So therefore, breath analysis would be a promising technology where disease detection, diagnosis, and treatment can happen at the very early stages way before any symptoms occur. But what we know today, we have just only scratched the surface, and breath analysis still in its infancy stage. So what we need a strong collaborations between technical, medical, and the commercial profession for full exploitation of this breath analysis technology. So what's the take-home message? You know that life starts and ends with a breath, right? So our breath is really a very rich source of data. So what we can detect in blood and tissue sample, in principle, we should be able to detect in breath samples using the laser spectroscopy. Only we have to find the right biomarker. So that is the challenging task. Okay, we have to do a lot of research, which markers actually work for the cancer. Cancer are also different types of the varieties. It's extremely challenging to find which biomarker. It's lung cancer and it's a head and neck cancer, or there are many things out there. Okay, so our breath may reveal our health status. There is a strong correlation between good breath and bad breath, because drinking wine at night and hangover the next morning, okay, so that's a it's a good breath or the bad breath. Okay, and there are a lot of reviews, and so we have written on the cavity ring down spectroscopy. If you're interested, you can have a look. Also, book chapters, books are there. Okay, and thank you very much. I would like to thank all the funding agencies, Department of Biotechnology, Department of Science and Technology, Ministry of Earth Sciences, Technical Research Center, RSSDI, to doing the experiment on the diabetic research. And this is my current group. And thank you so much for your kind attention. If you have any questions and comments, I'll be very happy to give you the answer. Okay, sure.
Thank you, Manik, for
quickly finished, right?
Very much well in time. I really thank you for your so lucid and fantastic presentation of cavity down spectroscopies, biomedical laboratories. Now the session is open for question and answer. Yes, Joji.
Is there any blood test for H. pylori detection, and how reliable is that?
So blood test, people use some antigen kind of test, but this is not so much sensitive. Okay, so now the urea breath test actually widely used, and also the endoscopic biopsy test also there are a lot of fallacies are there, because the endoscopic test is not the, though it is considered as a gold standard method, it is not the 100% correct. The thing is that, so I'm telling you the fact, because H. pylori has a very patchy distribution, okay? And sometimes during the endoscopic procedure, whenever collect the endoscopic tissue sample, it can miss the actual site of infection. Okay, it's a local measurement, but I am doing the global measurement. Okay, so that's why there is some kind of disagreement between the doctor's report and also our things. Okay, we are doing the global measurement throughout the stomach. It's a high sensitive and the spectroscopic measurement. And also to understand whether it is ulcer, non-ulcer, gastritis, it's an endoscopic picture. It's a person's just assessment, just seeing this picture. Okay, and doctor to doctor it will vary. Okay, so endoscopic is, sometimes I say endoscopic is actually positive, but I am getting the negative result. So that is biggest, some kind of very difficult problem to convince the doctor. So maybe sometimes the ulcer is actually dry out, but I am actually looking at the molecular level. So from the just naked eye, you can see that the disease has been cured, but it is actually not. So we face a lot of problems. So it's a debate and all these things.
Okay, fine.
Professor Pradhan, it's very fantastic talk. I just want one query. This hydrogen sulfide detection cannot be used for this H. pylori. Will it not work there? You are not using there, but in small intestine bacterial overgrowth, we are using hydrogen sulfide. In case of H. pylori.
Right. Actually, the H. pylori, it's a very uri-specific enzyme-based test.
Okay.
Okay. And hydrogen sulfide is a sulfur-reducing bacterial infection.
Yes.
So this is the two kinds of, the physiology is actually two different. But we did not check that whether, if we measure only hydrogen sulfide, whether we can check that H. pylori.
Suppose a patient has both H. pylori and small intestinal bacterial overgrowth. There, what would be the?
Yes, actually we have found this a multiple disease. The people have diabetes, SIBO, the multiple disease. Sugar, everything is there. It's very difficult. So to find the real breath print, Okay, so it is extremely challenging.
Yes, Professor Dhara.
Yeah. Excellent talk. Another comment. Raman spectroscopy or whatever your spectroscopy, some spectroscopy sometimes is misleading because the molecular information.
Exactly. True,
Second, my question, have you assessed you have heard of DLW, right? W leveled water. This oxygen 18 and
right, yeah.
now I think our heavy water board, they are all producing that. So what is your assessment, or do you want to make a try for this metabolism, because that gives you metabolic rate, because metabolism is one of the biggest problem now, because obesity is coming up and it's directly targeting our economy. So is there any plan for studying your spectroscopic technique with the DLW water analysis or metabolic analysis? Because you are doing disease, but metabolic.
Yeah, it is another doing different kind of works. Yeah, so I think that will be really interesting to explore.
Just look into that matter.
Sure.
Because now heavy water board has started producing both oxygen 18 and this.
Right.
So
Thank you.
he is from IGCAR and he is from DAE,
Yeah,
so his
I
question is
know.
pertinent to DAE. So yes, Rashmi.
Yeah, thanks sir for very nice presentation. I have just one query, that how oral microflora affects the spectroscopy.
Right. Yes,
and
actually,
if it
So
affects, how it is taken care of, the variation.
Right. Because we have many bacteria in our oral cavity. We collect the breath sample, that is the baseline, after 10 to 12 hour fasting condition. So this is my baseline. Okay. So then we give the 13C enriched urea. Then we collect after 10 minutes or 15 minutes later, we collect another breath sample. So it is actually subtracted from the baseline. So if there is any kind of the residual effect is there, it is actually automatically cancelled, because we are not directly quantify. We are doing the DOB, delta over baseline. The baseline will be different from person to person. So depending on age, weight, height, and sex, basal metabolic rate. Okay.
Any? Jaldi yaar.
Very nice, sir. Sir, I just have one question. How do you account for the humidity and temperature variations by these measurements?
So the humidity and the temperature variation. Yeah, the optical cavity is in the vacuum. It is not an ultra high vacuum. And the temperature, the experiment, whatever the experiment we are doing in the room. Okay. And it's a extremely high sensitive. Maybe if there is some kind of trace amount of water is there, still we can detect it. But we choose the rotational row vibrational line in such a way that it's an interference-free region. We make sure that there is no other absorption features are there. It's because the resolution, you can see that 0.001 wave number. We are precisely probing a single rotational line. So there might be many other molecular species. If you just scan the laser from this side or that side, it might have some overlapping. That's why before doing the measurement in Excel breath sample, the breath sample is a 4,000 molecular species, and many abundant moleculars are there. So we choose the spectral regions, that is the unique spectral region, in such a way that there is no other abundant molecular species. Okay, so that is the interference. All the spectra actually I have shown here, all are interference-free regions. Okay, so that's why it takes actually a lot of time. So there is no, just like methane, nitrous oxide, it's a huge amount of there. It's a parts per million level. It will automatically have some kind of overlapping absorption. So that is the beauty of this technique. If it's a very trace amount of their water, parts per trillion, even sub-trillion level, it will automatically get the signal.
Thank you.
Okay. So, Manik, I have two quick queries. You can tell. So, say, is there any protocol to give the breath samples? Say, for example, as you told that you can collect the breath samples from home.
10 to 12 hour fasting conditions.
Okay.
Yes, actually, first you need the fasting condition, and also there is some kind of exclusion criteria. Who is taking the medication? So that will not work. who have the recent gastric surgery or any kind of things. And also sometimes it might hamper hypertension patient. Okay, so there is some kind of also who is actually smoking. So we found a lot of problems.
Smoking.
The alcoholic smoking. That's why we do the experiment under extremely 10 to 12 hour fasting condition, make sure that he has not eaten anything before doing the test.
That is true. Okay, thank you. Thank you very much. Thank you. Thank you again, once again, for your wonderful talk.
Now I request Dr. Majumdar to present a memento to Dr. Pradhan. I request Priya to bring the memento to dais.
So we move over to our next talk. Next talk is by Professor Renu John. Renu is a very well-known figure in biophotonics, and he is now in IIT Hyderabad, and he's a completely biophotonics person, and he has done several things, and he's doing several things, and his group basically bioimaging techniques, as you have seen that there is bioimaging, then biosensing. It is not there. So, so biosensing and point of care devices, and then he has biomedical signal processing and medical device innovation, and basically he also does low interferometry based imaging. And he has several, he is a fellow of several academic societies like Royal Society of Biology, Optical Society of America, Optical Society of India. So he is a long list of awards and this thing. So without any further this thing, I invite Renu. Renu, 25 minutes plus 5 minutes.
Yes. All right. Yeah, yeah. All right. Thank you very much, Dr. Majumdar, for the introductions, and my gratitude to the NLS team for giving me this opportunity to present my work before the NLS conference. So today I will be briefly talking about how we look at live cells, imaging of live cells at microscopy, and a little bit advances in this directions towards intelligent microscopy. How do we take point of care microscopy to a point of care dimension? So if you look at diagnostics, so essentially the entire community who looks at imaging is looking at how do we image tissues, or how do we image volume tissues, how do we do microscopy and all the way to a cellular level, how do we image them in live, and even looking at volume imaging of cells or 3D imaging of cells, and to a level where probably we are looking at molecular signatures, look at single molecule signatures for diagnosis of diseases. So the whole goal is essentially can we detect signatures early enough so that there is a better prognosis. So most of the microscopists have been asking these questions like can we image live cells without having to stain or fix them, or can we do steady dynamics in real time. So some of these also arose a lot of interest in the computational community to look at can we also bring in a little bit of intelligence into microscopes so that we can have smart microscopes which could take decision, so help the clinicians in decision making. So, so today I will share a couple of things on how do we really look at live cells in 3 dimensions, like can we image them without having to fix and stain them, and study some of the dynamics. So a lot of today's work, we will see like how a traditional expensive microscope can be actually translated into low-cost modules or affordable modules which are as simple as like your mobile phones, which could be portable and taken care into various real-time situations. So some of these microscopes I will explain today. So which would be either multimodal microscopes or looking at 3D imaging applications, and some of these modules which are portable, as well as bringing some amount of intelligence to them. So all of these are all filed patents from my lab, and essentially the basic concept is that when we talk about 3D microscopy, we are essentially imaging the 3D features of the cells. So what we do, and one of the most popular techniques is interferometry or holography. So instead of imaging a bright field image of the cell, we do record a hologram. And the entire theory of holography is well known. So if you know the propagation vector or the diffraction theory, you can in fact back propagate the beam and reconstruct the 3D images in 3D images without having to do much of these. So with a single shot of hologram, we can reconstruct computationally the 3D features of cells in real time, and we don't really have to fix or stain the cells in this process. So that's the basic concept. So the fundamental principle is that this is essentially the Fresnel or the Fraunhofer kernel, which is nothing but a Fourier transform. So mathematically, you are doing a Fourier transform or an inverse Fourier transform of the record hologram, and you can essentially get the reconstructions. And the advantage again is that if you really have to, if there are aberrations present in the system, you can easily correct them with the help of mathematically we can correct them. So we also looked at how do we combine different geometries or multimodalities to a single microscope. So we also looked at a bunch of features where you can have a hologram by interfering a reference and object beam at an angle. But what happens if we are going to bring the angle to almost 0 or close to 0? So which essentially means that if you look at these 4 terms, they are going to collapse and overlap at a single point. So which means that the optics becomes quite simple, because you don't really have to use an additional reference beam. But the mathematics of deconvolving the object information from all these four terms becomes a little bit more complex. So we also tried looking at this, where you can simplify the optics and create a stable microscope, but mathematically a little bit more complicated to reconstruct the image. So I will share with a couple of examples. So we started looking at microfluidic channels, so this is an example of how we record a hologram of a microfluidic channel. These are the terms, and we use background information for correcting the phase aberrations, and this is what we reconstruct from the hologram. So you can see the entire microfluidic channel with its depth and thickness here. So this is about a 100 micron wide channel and about 45 micron deep. So you can see the entire 3D information in the hologram, and we went ahead, looked at imaging like nanometric depths or thicknesses. These are electrodes on a glass plate, and you can do a hologram, and you can see that you can actually image the depth and thickness to a precision of about hundreds of nanometers. So this is about 170 nanometers and about 95, 100 micron, less than 100 micron wide. So we started looking at biosensor chips. These are like microfluidic channels with a glass plate with electrodes on it, which are essentially the biomicrofluidic chips. And you can really see the entire microfluidic channel along with the electrodes that are sitting over it. So we could give the resolution in the Z direction or the depth direction was really tremendous. So we could in real time image features as as to the precision of about few tenths of nanometer. So now we started looking at flowing fluids through this microfluidic channel. So you can see fluids moving through the channels, and we can image them in real time. These are all examples we did. Then we started flowing cells through these channels. So we could study the cells in real time flowing through the cells. We could study their dynamics, observe the divisions of cells, and see how they multiply or divide in real time. And we can also do a lot of processing like sorting or analyzing the structural morphology and a lot of similar things. So this is an example of an E. coli in a microfluidic channel. So it's about like, you can see about 440 nanometers and few microns long. So and we also looked at can we combine multi-model microscopes, like different types of microscope in a single geometry, so that we get complementary information from each type of microscope. So for example, this is a regular bright field microscope, a light source here, which would give you a regular bright field image. You can always introduce a second light source here and record a spectral contrast microscope, which is essentially very important for looking at dynamics of cells or dynamics that are happening within the cells. So, and we can always get a holograph geometry here by combining both the beams and getting a hologram recorded here. And all of these modalities coexist. So you can also record a spectral contrast microscopy image here. So essentially we get 4 or 5 microscopes in a basic simple geometry, and these are extremely affordable or cheap configurations, so you don't have to spend a lot of money on this. So we started looking at some of these examples, and so as we played with the reference beam or made an off-axis geometry, we also looked at can we also, instead of folding the reference beam back, can we also put a piece of scanner at the reference beam so that you can do a tomography at the cellular level. So this is an example of a tomogram done with the help of a microscope or an optical coherence microscope. So this is a dragonfly eye. You can see the entire features of the eye on a live dragonfly. So you can see all the cellular features in depth and thickness just by moving the reference amp through micrometers or pushing the reference amp for getting a tomographic view here. So and we combined this with speckle geometries. So this is a zebrafish embryo. You can see the entire volume information with the help of the tomograph here, and you can also get the blood flow. This is the zebrafish heart, and you can see the blood flow by studying the spectral contrast microscopy. So we can the combination of microscopes get a lot of complementary information, which could have a lot of practical biological applications. So and finally we looked at can we sort of bring in a little bit of intelligence to microscopy. So fundamentally, I mean, when we looked at the type of problems that clinicians are looking at in the case of regular pathological applications. So decision support is one strong thing, like it can essentially augment a clinician in taking decisions or bringing down 1,000 slides of microscopy images to about 100 or 50 images. So that's something which we looked at. Can we do decision support and image classification with the help of by introducing a little bit of intelligence into the microscope? And also we looked at can we also have better reconstructions, better phase or 3D reconstructions with the help of AI embedded into the microscope. So I will give you 2 examples on this. So the first one, so these were the fundamental questions that we asked. Can we do classifications and decision making, and can we do better image reconstruction? So this is an example of one product which has come out from the lab. So this is from the startup Bhabha made data, essentially looking at a regular microscope, which is nothing but doing pap smear or a slide scanning. So there is no innovation here other than just an automated slide scanner here sitting here. So all we did was to plug in with an AI algorithm, which would essentially look at all the cells in real time and point out the hotspots, essentially pointing to the pathology, saying that these are the hotspots where there are signatures of multiple nucleus or cell divisions or heavy nucleated cells, which point to cervical cancers. So this is a pap smear automated microscope. So the company has come up with a platform called Survey.ai, which is already in market and being used for annotation by a group of UK pathologists and a path lab chain. Right. So, so that is how we looked at a regular microscope with some intelligence. Then we looked at, can we also get into the volume imaging of cells without having to use stains. So then we looked at these type of configurations where the cost of the microscope has been really brought down to just a camera with the microscopic slide sitting right over the detector array. So this is essentially like introducing a slide smear or taking the sample, smearing it on the glass plate and almost looking or fitting it onto the detector array. What is happening here is that you have what we call as the object beam and the reference beam all in the same beam. The undifracted light falls in as the reference beam, and what is being recorded is essentially a diffraction pattern of the cells that is sitting over the camera module. So all we know is that you know the diffraction theory. So if we can back propagate the light with the basic Fresnel or Fraunhofer kernel, you can get the 3D information of the cells that are sitting there. So we applied this to a couple of cases. One was oral cytology, where another digital cytology case where doctors have to look at a breast cytology of cells in the buccal cavity, and the second one where clinicians were looking at the pap smears or the cervical pap smears, and the third case was to look at in vitro fertilization, where there is a lot of exercise collecting the sperms, characterizing the sperms, structural morphology and motility of the sperms, and all the way up to post-fertilization. So we looked at all of these cases with the help of this thing. The first example is oral cytology. So a traditional oral cytology essentially is taking or getting the breast cytology, fixing the cells and staining the cells, putting onto a glass slide and looking at all of these to find out if there are multinucleate cells, cells with heavy nucleation, etc. And if the cells are poorly differentiated, what is the ratio of the nucleus to the cytoplasm, to find out if there are anomalous cells point to oral cancers. So this is what it looks like under my microscope. So you can see the entire cell with its strong nucleus, the cytoplasm, and sometimes a lot of the subcellular features on it. So you can see the entire volume of the cells. So the decision making becomes quite easy while looking at this cell, because essentially instead of comparing the nucleus to the cytoplasmic areas here, you can compare the volume of the nucleus to the cytoplasmic volume, which essentially is much more accurate in the case of cancer diagnosis. And all the other features are very clearly evident from a volume information of the cells. So we did this exercise on thousands of cells, and you can see this is an example of a normal oral cell with a single prominent nucleus in all of these and cytoplasm. And the right contrast is here, where you have a cell which is heavily nucleated or a lot of nuclear material, which essentially fills up the entire cytoplasm. So essentially the nuclear to cytoplasmic ratios are way high here compared to this, which clearly indicates that these are not normal cells at all. So all of these results were compared back against with the gold standard histopathology to find out what we are inferring are correct or not. So this is again the second level of application where we looked at in vitro fertilization. So we started with imaging sperms. So essentially characterization of sperms is one tedious exercise at the beginning of the IVF process. So we found that almost there are a class of 80 classes of anomalies which make the sperms infertile. Some of these are shown here. So it is not one classification or two classifications. There are about 80 images, 80 types of classifications which classify the sperm as not good for fertilization or infertile. So now for a pathologist to look at under a microscopy slide to find out these anomalies is quite a hectic exercise. So what is done is that in a standard process, the sperms are fixed, smeared on the glass plate and stained and looked under a microscope. And if you look at the sperms in, without any fixing or staining, they'd be almost like shadows on a glass plate. So, and under the microscope, I will show you exactly what I see under a holographic microscope. You can see the entire 3D features of the sperm all the way to the nuclear region, so the prominent nuclear region, which is almost like about 5 micron head. If you look closer, you can see the acrosomal region of the sperm and the vacuolations present here. You can see the mid-piece region and any sort of anomalies or deformations in the mid-piece region, and all the way up to about 100 nanometer tail of the sperm. So you can see the entire 3D picture of the sperm, and that too totally unfixed on a live sperm. So this again points the fact that you can actually, during an IVF or an ICSI process, you can select the best sperm, cut its tail, aspirate it, and inject into the ovum. So we started all of this exercise, and we found that there are a lot of value addition to the whole process, not just for the selection of the best sperm. So we also looked at grading of the female gametes or the oocytes. So the quality of the oocytes or grading also depends on the texture and quality of the oocytes, which the 3D image could give a fantastic resolution there. So in the sperm classification, we did all the math. Then we could intelligently classify them. A set of algorithms working at the back could do all the calculations automatically, and a simple training algorithm would give you an accuracy pretty high enough. Even with very low training, with less number of data, we could get very good classification. So it is not it's actually a very simple problem to do this classification. So and in the case of embryoscopes, or when we looked at post-fertilization, again there are a lot of features once after the single cell embryo is formed. A lot of more information can be seen by imaging them in 3 dimensions. So essentially, after fertilization, the single cell becomes 2 cells and 4 cell, 8 cell, 16 cell, up to a 3, maybe over hundreds of cells, which forms a blastocyst, which is implanted back into the uterus. So you can actually study these from the single cell to multiple cell divisions as it grows to a blastocyst. So this is actually in 3 dimensions in real time. You don't have to. You don't even have to take the cell out of the incubator. So we pretty much had the holographic microscope attached onto the incubator itself, so that we have a 3D information of the whole process. This is currently a clinical study continuing now. What we found is that right from selection of the best sperms all the way up to a fertilized ovum or an embryo which is getting implanted, a 3D imaging carries a lot of value, and it could bring a lot of information to the clinician. So a lot of studies are currently suggesting that even the symmetry of division of the first cell embryo to 2 cells to 16 cells give a lot of information about the fertility of the the survival of the fetus post implantation. So this is again a study in progress. So and then we moved on to I will show some of the results showing how do we get an intelligent reconstruction of face or 3D information. So traditionally there are a lot of algorithms where you could reconstruct 3-dimensional information. So people started looking at the regular inverse problem approach, where you could create a forward model and back propagate it and iteratively reconstruct the hologram to get best reconstruction. This is something what we call as a classical method. There have been a lot of reports on this, and slowly what we did was that instead of doing a forward model, we used a set of training data, which is like the ground truth information, and we use the ground truth information to to a network which is essentially going to reconstruct the hologram for the best. And as we worked on this, we found that we are essentially losing something here. Here the basic information that we have, the physics of hologram formation is totally lost here, because we use some training data and we propagate it to a network almost like a blind propagation. So now we tried looking at bringing back the forward model and plugging it to the new network so that we get the physics aware network to do the reconstructions. And finally, we combined these two models to get a better model. I will show one or two examples on this and wrap up my talk. So this is basically the basic architecture. We have the hologram which propagates to the network to get the object information. Now I plug in the object information back onto the standard propagation model to get the hologram back. Now a difference between them is essentially defined as a cost function or a loss function. And what we do is to optimize this loss function and feedback that information to the network so that we get a better reconstruction. And this whole process I iterate till the definition of the cost function is satisfied so that we get a better reconstruction. So fundamentally this works very well for homogeneous objects like a red blood cell where there are no features. But when it comes to cells, we had a lot of issues here. The basic problem was the noise here. So what happens is that as the network iterates, the network also sort of learns the noise, and the noise also get embedded part of the learning network. So we had to figure out a way in which we could remove the noise, and then we started looking at how do we remove the noise. All right. So what we did was that we, instead of simply defining a cost function, we introduced a noise factor here, which is essentially a regularization factor. And we started iterating this regulation factor with a small tweaking gamma factor here. And so that added a better algorithm, that got us a better algorithm. We tried different noise models here. We played with different noise models. We got a little bit of incremental better reconstructions, and finally we found that there are better ways. So here in this particular case, we also suffered loss of resolution in the system. So then we moved on to then we moved on to some more information like alternating directive multipliers method, where we could sort of remove the noise tweaking outside the network, and we could essentially define different parameters, where one was essentially the regular hologram propagation, where H represented the forward model. This represents the iterative factor, and we did some Lagrangian multipliers so that as we iterate, we don't go far away from the solution. So we could tweak all these parameters to get better reconstruction. So this is essentially the regularization by denoising, and then we So then we moved on to better architectures. We found that we could save a lot of these iterations or reduce the complexity of iterations by doing skip connections. These are all standard processes when we do the reconstructions using neural networks. So then we started looking at, can we introduce the hologram model back into the picture. So what we did was that we can essentially use a set of ground truth to train our network, and this will give you a better reconstruction. We can plug in back to the other network so that we can get a better reconstruction. So I will explain this a little bit better way. So we have the original information, which is the amplitude information, which we use it as a ground truth database. So whenever we reconstruct an image, we always use the ground truth to compare with the reconstructions from the ground truth and compare with our reconstructed image. This is essentially what we call as a GAN network, which is a generator and adversarial network. So essentially, the GAN network creates an image of the face or the 3D information, and from the ground truth, the discriminator creates another image, and these two gets compared each other. Essentially, this is the same algorithm which is used in all these deepfake videos. So the generator creates an image, the discriminator creates another image from the ground truth, and these two are compared each other to see how they are matching, and if not, then we go again doing this process. Only thing is that we do iterate this GAN network with the help of the feedback. So now the combined system would almost look like we have the generator and the discriminator keeping on creating the images and iterating on it. Finally, so all the previous algorithms remains the same, except that I mean, we have to define tweaking parameters where the best match comes. We have to exit the algorithm. So the number of iterations have to be manually decided, or we have to set the number of parameters. So we sort of define parameters like epsilons, which would say when we satisfy these criteria, we can exit the algorithm. And finally, this is an example of how we reconstructed these pap smear images. So you can see that these images probably are the best in phase which I could reconstruct compared to the stained pap smear images. So I would stop here. I mean, so essentially we looked at how do we reconstruct a 3D face with the help of the physics along with the neural networks or artificial neural networks. And we also looked at, can we take microscopes all the way from the bigger clinical microscopes to portable versions which could be going to rural areas, where we could get the smear right onto the glass, onto the microscopic slide, image them, take the decision making to a cloud, and take the final decision making online itself. So, and we also looked at can we get better reconstruction with the help of generative algorithms. So I'll stop here and open for questions. Thank you so much.
Thank you, Renu, for this wonderful talk, covering the nuances of microscopy and all sorts of supervised and unsupervised algorithms to process the images. So now the question is, this session is open for question and answer. Please.
Hello, sir. So my question is, have you done any real-time imaging-based studies on the formation of bacterial biofilm, like how the dynamics of a bacterial cell changes when it progresses from a planktonic state to a biofilm state?
I haven't worked on bacteria at all, but this could be a real problem.
Okay.
So all of these are real-time data. I mean, the data collected either from the cells, etc., but I haven't worked on bacteria.
Okay. Thank you.
Yeah.
Yes.
Hello, sir. It's a wonderful talk. My question was that how do you decide and what were the parameters you choose when you reconstruct the images from the pap smears? As you said that during the iterative processes, you have to again choose some manual parameters to reconstruct the image. So what were the basis of your manual imaging decisions there?
Yeah. So there are a class of similarity metrics as we use, starting with signal to noise ratio, PSNRs, or structural similarity induction metrics. So all of these are standard metrics used for image fidelity check. The basic question here is that in the case of regular images, which are bright field images, there are ground truth existing. But in the case of 3D images, for 3D images of pap smears does not exist at all. So we had to generate face images or 3D images as ground truth. Then we use our reduced networks to check this out. So that was the challenge here. In most of the times there was no ground truth existing. So fundamentally our ground truth data was first actually we simulated the 3D data by propagating through the Fresnel kernel itself. So that was our simulated data. Then we did basic holography setup like the standard benchmark holography system, and we reconstructed face images and used that as the ground truth for training the reduced algorithms. Yeah.
So one more thing was that in your embryo imaging, right, you showed that images for I think not more than 6 cells for your imaging.
We are, I mean, in terms of ethical approvals, we can keep the embryo for as more than cannot more than 4 cells at the moment. So we are getting the ethical approvals for continuous observation as long as we are not using it for fertilization.
Okay. Now my question was that whether we could go for up to 100 microns or 200 microns of thickness in the 3D holography.
Yeah. So that is the goal actually. We have got animal ethics approvals where we are doing a pilot study now on animals, mice oocytes grown up to the blastocyst level where we can grow them. That at the blastocyst level it would be almost like 300 to 500 micron with almost like 100 plus cells on it. Yeah.
Thank you. Thank you very much.
Anything? Anybody else? You last. Come forward.
I exceeded, I think, my time.
Sir, hello. The talk was really interesting. I just have 2 questions, both in relation to AI. And the first part of the talk, I remember seeing that you said there were around 80 classes of sperms that are really I think they're not ready to fertilize an egg. And I just wanted to know, have you used any sort of multi-class models to classify those 80 types of sperms? Because it seems to be a problem that can be leveraged with AI.
Yeah, it's an AI problem and it was done with AI only. But that classification is quite simple compared to any other problem because there are already well established multi-class classification algorithms already existing. So though there are 80 classes, it is still a simple problem.
So you have done that, right?
Yeah.
Okay. And the second part was, why did you prefer GANs to autoencoders? Because I looked at the model, it looked like an autoencoder model. Was there a specific reason you preferred GANs over autoencoder?
So one was like switching from unsupervised to a supervised model. GANs provided this platform where you could actually use the ground truth data to train the generated image. So that was slightly better, but we could combine the forward model with the physics of hologram formation, which is a forward model, which brought the difference actually. So it is sort of a HD GAN with a physics aware network that brought the difference.
Right. Yeah. And say if someone had to improve your work, what are certain caveats or places where you feel like the AI part could be pushed a little further?
Can you repeat the question?
During the AI, this is the third part of my question, if I may allowed to ask. If someone has to push your work a little to the further, right? For example, if I'm interested, what should I start with in AI? Like for example, if you say GAN, you should probably look into this model or that model. Any certain things?
Probably we can, I think, take this offline.
Sure.
There are a lot of unknowns still left out here. Yeah.
Okay.
Yeah.
Sure. Thank you.
Yeah. Thank you. Yeah.
Okay. So my quick one query that your lens-free imaging has this thing been made into some device?
Yeah. So that's a microscope already, which I saw.
Whatever, and it is being used. Okay.
So the IVF platform is a startup now, SciQuest Private Limited. So led by the 2 clinical experts, IVF experts now. So yeah.
Fine. Thank you very much.
Thank you. Yeah.
So thank Renu once again.
Thank you.
May I request Dr. Majumdar to present a memento to Dr. Renujan, and may I request Vishali to bring the memento to dais.
So now we move over to our next talk and last speaker of this session, Dr. Somadatya Mula. So Somaditya is a very bright scientist from Bhabha Atomic Research Center, and he is a chemist, and he's working on design and development of organic fluorophores, organic fluorophore molecules for optoelectronic applications, and a lot of biophotonics application he does. And he has been awarded with, you can see, so most importantly, see, he got this materials chemistry bronze medal and DAE Young Scientist Award in 2014. So without wasting further time, I invite.
Okay. Thank you, sir, for your kind introduction, and good evening to all of you. Before starting my presentation, I should thank all organizers for the invitation to give me the opportunity to present our work in front of all of you, and for the nice hospitality as we get always in RRCAT whenever we are RRCAT. So thank you for that. So today's talk will be on development of photostable laser dyes and their applications in cellular imaging. So in the laser dye, I will be basically talking about the bispiralic laser dyes. So the structure and everything I will show in the next slide. So before going to that detail, briefly I will discuss about our group activity, whatever we are doing in our group in BARC. So we are basically actually a group of organic chemists. So we are doing development, we are engaged in development of different organic fluorophore based functional materials which will be used for different applications. So as a organic fluorophore, we basically use this kind of dyes. I have given 4 different structures, and you can see all these dyes are based on this pyrrole group. So all these dyes has contained 2 pyrrole group. That's why I talked about the bispiralic dyes. So what we basically do, we do the molecular engineering of this kind of dyes to tune their fluorescence properties, to make them suitable for different applications, to make them apply for different applications. So in our group, we are basically focused on these 5 areas. One of them is chemical and biological sensing. So we make the molecules tune their fluorescence properties to make them suitable for sensing of different important chemical or biological analytes, basically for detection of various disease markers. In another program, we use this kind of dyes for detection of ionization radiation. For example, for the gamma radiation, we developed various gamma dosimeters to measure and quantify the gamma doses. We also use this kind of dyes for development of organic electronics, suppose organic OLED, organic transistors, etc., etc. And the last 2 areas what I am going to talk today, one is the laser dyes. So as this kind of dyes has very high fluorescence, we can use them to generate laser dyes, laser lights using the dye lasers. And also, this kind of laser dyes can be very useful for the imaging, for the cellular imaging, as well as different therapies. So today I will also talking about that imaging of the cellular imaging of using this kind of dyes. So coming to the laser dyes, as you know, this has been discovered in long back in 1960s, and after that it has been used in various fields of science for different applications. And that for these dye lasers, we basically use a variety of organic dyes as a lasing medium in solution or maybe in the solid state also. So whenever we excite this kind of fluorophore with a pulse laser, a source laser, they generate different wavelength of laser lights. The unique features of the dye lasers is that the tunability. As all the organic dyes has a broad fluorescence range, so you can use each dye for around this range for the laser output. And also you can change the dyes to change their tunability. So in fact, you can, using the dye lasers, you can generate the laser lights from ultraviolet to near infrared. So this is the most unique feature of the dye lasers. So if you see in the literature, there are numerous number of dyes are being used in the dye lasers. So I have listed few of them. So for all these dyes, you can see they can be used for a very narrow region, 500 to 580 for the fluorescein dye, for the rhodamine 570 to 650. And among these dyes, this rhodamine 6G is still considered as the benchmark for their photostability as well as the lasing efficiency. From an organic chemist point of view, if I want to change their wavelength, tuning wavelength, it is very difficult to do different chemistry around these kind of dyes. But the dye, whichever I will going to speak, in that case, this sort of tunability is very easy. So I will talk about that. The dye today I am going to speak is it's a boron dipyromethane dye. It's a 2-pyrrole ring linked between a methylene group, and in the lower side, 2 nitrogen is blocked by a boron atom. So it's a dipyromethane dye, shortly known as BODY-PY. So if you see closely their structure, it's basically a cyanide dye, as I showed you before. And this 2 nitrogen is blocked by a linking group. And due to this linking, this has a very rigid structure. And all these extraordinary features is coming from this rigidity in their chemical structures. Okay? So this kind of dye is first reported in way back 1968. But after that, for 20 years, people didn't use this kind of dyes for any kind of applications. But in the late 80s or early 90s, people started using them as a laser dyes to generate laser lights from the green to yellow region. Okay? And slowly, people used to start using this kind of dyes for other applications also, suppose cellular imaging, bioimaging, organoelectronics, everything, blah, blah. Okay? So, realizing their opportunity with this kind of dyes, way back in 2007, Professor Remo Giselle, who is worked extensively with this kind of dyes, he renamed this kind of dyes as a new El Dorado. It's a gold for different fluorescence tool. Okay. So coming to the features of this kind of dye, why this kind of dyes is important. This dyes has a high and tunable fluorescence quantum belt. Sometimes it reaches to 100%. It has a low intersystem crossing rate as compared to the rhodamine 6G. It possesses high molar extinction coefficient, sometimes it's more than 1 lakh. Its tunable range is also very high as compared to the rhodamine 6G. And its triplet excitation coefficient also is lower than rhodamine 6G. So all these properties made them very superior as compared to the rhodamine 6G. Along with this, they are highly solubility in different kinds of solvents. And most importantly, from an organic chemist viewpoint, you can do a lot of chemistry around this dye structure to tune their wavelength and their fluorescence property. So due to these important features, we can see that this kind of dyes has almost double lasing efficiency as compared to the well-known, which is benchmark rhodamine 6G dyes. Okay. But this class of dyes has a problem with this kind of dyes. It's a photostability. Its photostability under lasing condition is lower, almost 100 times less as compared to rhodamine 6G. That is the main bottleneck for using this kind of dyes for average high power lasers for a long time. That lower stability is coming from that whenever we are exciting this dye, it transfers this energy to the available triplet oxygen, And due to this energy transfer, the singlet oxygen is producing in the medium. And this singlet oxygen reacts at this double bond to degrade this dye structure. So whenever you are using for a long term for 16, 17 hours, it started degrading and you cannot use for a very long time to get high laser powers. So our objective was to make them photostable and to make different chemistry around this dye structure to make different tunable laser dyes with the same dye structure. So the easiest thing if you want to make them photostable, first thing you can make them deaerated, you can purge the nitrogen, you can remove all this oxygen from the solution, and also in another way you can add some singlet oxygen quencher like DABCO, TBP, etc. But both these two things is not very suitable when you are dealing with a large amount of solvents. It's purging also, and even if you are using a high amount of the singlet oxygen quencher, sometimes it quenches their fluorescence properties also. So it took a different approach. As a chemist, we try to modulate their structure so that its reaction with the singlet oxygen get decreased. Okay? So what we do, as I told that this singlet oxygen is reacting in this double bond. So in the first approach, we try to make this side sterically congested so that reaction kinetics become slow. So we can in that way we can enhance their stability. In another way, we did the substitution at the boron center, because it is known that if you substitute at the boron center, its chemical stability improves. We wanted to see that their photostability also improves or not. And another cause of this choosing these two center is that if you do the substitution, this substitution at this position, at this boron position, they don't interfere in the chromophore. The chromophoric property remains the same. Okay? If you see their fluorescence properties, it is almost in the same region whenever you are substituting at the C8 position also, at the boron position also. So their fluorescence property remains same. So we wanted to see keeping their fluorescence property, whether we can increase their. So the synthetic procedure, I will not go in detail about the synthesis. So here is the laser performance. When we substituted at the C8 position with different groups, you can see in the phenyl, its fluorescence lasing efficiency is a little bit less, but as we increase their methoxy group, their lasing efficiency started increasing. So we wanted to keep their lasing efficiency same. We don't wanted to compromise with their lasing efficiency. Keeping their lasing efficiency same, we wanted to increase their stability. If you see, the stability is always more as compared to the standard dye PM567. But as we go on, start increasing methoxy group, their stability decrease little bit, but at the end, this dye 4 is almost 2 times more photostable as compared to the parent dye PM567. And this stability is mainly because of the reducing reaction probability of the singlet oxygen, as I told before. But still, this stability is far apart from the stability as compared to the rhodamine 6G. Okay. So if we see the boron substitution dyes, all the dyes, here is the C8 position substitution, here is a boron, and in this dye we substituted both the positions. In all the cases, their lasing efficiency is almost same, and their stability started increasing, and the dye 4 has shown almost 4 times more stability as compared to the rhodamine 6G. Okay. But still this stability is really less as compared to the rhodamine 6G, as rhodamine 6G is almost 100 times more photostable as compared to this pyromesin 567. So here is the narrowband lasing profile of these dyes. You can see these dyes can be used from the 540 to 580 nanometer range. Okay. then we wanted to see that how by changing their boron substitution, it is increasing their photostability. So we did the cyclic photometry. We see their affinity toward oxidation, because it's a oxidation process when it's reacting with the singlet oxygen. But we saw a reverse way. As we substituted at the boron center, their affinity towards oxidation increases. That means this is not the controlling factor to make them photostable, something else. Something else means maybe the rate of reaction with the singlet oxygen, or maybe the singlet oxygen generation capacity of these dyes. So for this, we did the DFT calculations. DFT calculation shows that their transition state, activation energy of this reaction, this singlet oxygen and this dyes, if we substitute at the boron center, this activation energy increases many-fold as compared to the normal dyes. So the reaction kinetics with the singlet oxygen gets slow whenever we are substituting it. So that is one reason that reaction rate with the singlet oxygen gets slow after the substitution at the boron center. And also we singlet oxygen generation capacity by pulse relays studies. Here also we saw that their singlet oxygen generation capacity also, it's decreased whenever we started substituting at the boron center. So all the boron substituted dyes has less reactivity towards singlet oxygen as well as less singlet oxygen generation ability. So both these things made them highly photostable. But as I told you that the photostability is increased only by 4 times. So it is far away from the photostability of the rhodamine 6G. So in another approach, what we change the solvent polarity. We wanted to see whether we can increase further their stability. Because if we see that this transition state is a ionic, we generate the charge here. So if we reduce the polarity of the solvent, we can destabilize the transition state, we can enhance their activation energy. So whenever we change the solvent polarity, so the ethanol to the 1,4-dioxane, less polar solvent, we have seen that their photostability has been increased by almost 40 times. So using the substitution at the boron center as well at the C8, and by changing their solvent polarity, we can get the stable body P dye as comparable with the rhodamine 6G with a double leasing efficiency. So after that, we started using this kind of lasing dyes for the biological cellular imaging. And another example I will show that how we can do the chemical modification of this kind of dyes to shift their tunable range. We can do different chemistry at this position to change their color from the green to red, green to pink to yellow, red, and we tested these dyes. This is in the orange region. Their stability is almost 2 times as compared to the 567, although their lasing efficiency is a bit low. So that uniqueness of these dyes is that we can use the copper vapor lasers, because on other dyes we use the rhodamine NDIAC laser 532 nanometer or copper vapor laser 510 as an excitation source. But this kind of dyes we can excite with the 578 nanometer laser light of the copper vapor lasers. Okay. So after developing all these latest dyes, then we started using this kind of dyes for different cellular imaging applications. Have very high fluorescence properties. Okay. So I will show 2 different examples with this kind of dyes. In one example, we wanted to develop endoplasmic reticulum targeting dyes for their imaging. Because this kind of endoplasmic reticulum targeting dyes are important for specifically for pancreatic cell lines, because this kind of cell lines are highly dependent on the endoplasmic reticulum for their different hormone production. So if you want to develop different therapies for this kind of PDAC cells, very important to image this endoplasmic reticulum and to make them targeted to this ear. So what we did, we took the dye and attached a ear-specific moiety, which is a phenolphthalein BF2 dye. It is known that it targets to the endoplasmic reticulum. And we add in a position where we anticipated that this part will not affect their photophysical properties, but it will carry this molecule to the endoplasmic reticulum site. Okay? So we did a lot of calculations to see that this part is actually twisted as compared to it is in the orthogonal position as compared to our original chromophore. So it did not affect their photophysical properties. Here also you can see that all their photophysical properties of the dye is almost similar when we added these dyes. Okay? So it didn't affect their photophysical property, but we anticipated that it will carry this molecule endoplasmic reticulum site. So when we did the cellular imaging studies, we saw that all the three dyes is nicely growing into the cellular system, and we checked with different tracker dye. We saw it's nicely matching with this our dye 3. That means it's nicely going to the endoplasmic reticulum. It's also slightly matching with the mitochondria tracker and lyso tracker also. Little bit, if you can see, it is not exactly matching, but with the endoplasmic reticulum tracker, it is matching almost 100%. So it is nicely going to the endoplasmic reticulum site. But when we do the cellular imaging studies, we got a surprising results. Initial time, it was green, as we expected, the dye is green, but with time it changes their color. If we see in starting it was yellow, if we see in 2 hours time, this green dye become almost red. If you see this live cell imaging, see that all these dyes initially it was and with time it became slowly yellow to red. So it was surprised because when we did all these ledging studies, it was throughout the studies it the same color, but why it is changing their color? So we did a lot of studies with different solvents, different polarity system, and what we find that if we change their polarity of the solvent, these dyes started aggregating, and due to this aggregation, they change their color from yellow to red. So that means when this endoplasmic reticulum, they generate biogenesis of the lipid droplets from the endoplasmic reticulum. These dyes are going to the lipid droplets, and due to change their polarity, they are changing their color. So eventually, if we take the single dye with the same laser excitation at the 490 we use, you can image endoplasmic reticulum as well as the lipid droplet at the same time. And this kind of dyes is not known so far, because if you want to image endoplasmic reticulum, you use another dye, and for the lipid droplets, you need to use a different dye. And for both the dyes, you need a different laser excitation. That is the main problem for the bioimaging. But using our dye, with the same dye, same laser excitation, simultaneously you can image both endoplasmic reticulum as well as the lipid droplets. Okay. So in the next example, I will show that how we can use the energy transfer system to develop a imaging agent. As I told before also, this example, that with the same dye, we can image both the molecule, both the cellular part at the similar time. So we wanted to develop another system, whether we wanted to see whether with the same laser excitation, we can image different parts of the cellular component. Because nowadays what we do, If you want to image one part of the cellular system, we use a green emission dye. We use a 490 laser excitation. For the another part of the cellular system, we use another dye with different color. For that, we need a different laser excitation source. But if we can make a combine of these two to make the FRET system means if we condemn connected this green and yellow, eventually if you excite this green dye, it will emit, and this emission energy will be absorbed by the second molecule, and eventually you will get the emission from the second molecule. So if you take two different imaging agent, you can excite with the same laser light. In one case, you will get the green emission, and with your FRET system, you can get a different color emission. So you wanted to see whether this kind of system we can use it for the cellular imaging system. So this is a classic example of this kind of dyad or triad system. It is reported that if you can attach 3 different body P dyes, if you excite this blue dye or the green dye, always you will get the red lasing emission. So anywhere in the spectrum, anywhere you excite, it will transfer their energy, and this energy transfer is very fast. This is 100%, this is 91%. So eventually, anywhere you excite, you will get the red emission. Okay? We wanted to use this kind of system for the cellular imaging studies. So for the blue emitting dyes, we develop a new type of emitter, which is called a tetrapyrrolopyrrole dye, TAP dye. It is also again that's bispyrrolic dyes. So it absorbs a blue region, and it will emit in the blue region, which will be absorbed by our dye. So we constructed this kind of dyad. We take our donor molecule, we attach it with the body P dyes to make this kind of dyad molecule. So we did a theoretical calculation. We saw that these two dyes are really separated. This is not in the planar. So they don't disturb their photophysical properties of each other. Okay? They are behave like an individual chromophore. Okay? So this is the synthesis. I will not go into the details. When we started doing the photophysical study, we saw that in the dyad one, both the molecule are present. Okay? If you see this blue one, this is absorption of this donor, and the green one is the absorption of that acceptor, and the red one, if you can see, both the peaks are there. So that means both the molecules are present in this dyad, and they are not interconnected electronically. Okay? If you see the fluorescence also, this is the fluorescence of this donor, and this green one is the fluorescence of this acceptor. But if you excite at this donor, you don't see any donor fluorescence. If you excite here, you don't. This red one is the dyad, so you don't get any donor fluorescence. You always get the acceptor fluorescence. So, okay. So that means from here you can see the very efficient energy transfer from this donor to acceptor. Okay. So these we did a lot of transient absorption spectroscopy to see there how fast this energy transfer is. So here in the fluorescence time resolved fluorescence studies, you can see that decay of this fluorescence of this donor and this fluorescence of this acceptor, it is almost in the femtosecond region, 122 femtosecond. That means this energy transfer is very fast, and if you can see, this energy transfer efficiency also is almost 100%. So we use this dye. So we wanted to see if we excite at this place, which color we are getting inside the cell, and at this acceptor also we excite at the 488. So in both the excitation, we got the green laser. That means this energy transfer also is possible inside the cellular in the cellular environment, and we can use them for a cellular imaging. So this is the example what we wanted to do. We take a blue emitter for the nucleus targeting dye is the HEST, and we took our dye, this diode, and we excite with the 405 nanometer laser. So in the blue excitation, we didn't see any image in the 500 to 600 nanometer region, but for our dye, we get the green emission. So if we combine with the same laser excitation, we can see both the part, nucleus as well as the cytoplasm. So this kind of strategy will be very useful to make the cellular imaging studies for the future directions. Okay? So I'll stop here. So this paper also is recently published in Chemistry European Journal. So quickly, these are my group in the BRC. All this work is done by Mr. Sudeep Gorai, Richa, and this Nunes Kohli. And also I should thank my collaborators from India as well as from the abroad, and DAE, BRC and HBNI for their funding as well as the facility. And this is a slide for Homi, Bhabha and HBNI. I guess everybody is aware of this, so I should not take much time for this. So thank you very much. Kind attention.
Thank you, Mullah, for very illuminating talk on different dyes. So the session is open for questions. Mike.
You are using organic dyes. Why you don't use inorganic dyes? Will not it work? It is not degradable.
Yeah, but its solubility will be less if you want to go for the organic solvents, na? The ethanol or some other solvents.
Yeah, solubility doesn't matter. If it is nano.
Yeah, you can use it. You can use it for that but I don't know that tunability range may be less as compared to the organic dyes.
You can make it tunable by varying the lanthanum.
Yeah, but efficiency wise, I don't know, it will reach to that level of rhodamin 6G or
no, these are very efficient.
Okay.
You can make it laser.
Okay.
Okay, he is working on organic dyes, so.
Dr. Mullah, it's a very fantastic talk. One question. These body P dyes, you said that they have lower tendency towards intersystem crossing, right? And photodynamic therapy requires more intersystem crossing.
Yes.
So how do you achieve that? These are contradictions.
So I told you that we do that lot of molecular engineering. Okay, so we make strategy to make a dye which is less generating singlet oxygen to make it a more generating singlet oxygen. One is the easiest example. If you attach some heavy atom with this dye,
that's what I was coming to.
It will make favorable this intersystem crossing. This is the easiest way, but there are several other molecular engineering without adding that heavy atoms also. You can make them efficiently intersystem crossing, make them efficient intersystem crossing in the body P also.
And do you compare the intersystem crossing probability with the existing photosynthesizer? Have you compared?
Yes.
Is this comparable?
Yes.
Okay, fine.
These are highly efficient if you attach all these heavy atoms and other dyes.
Good talk. You talked about photostability.
Yes.
And you are considering fluence as a peak fluence or average fluence? Photon fluence. Because if you are using pulse lasers, I think the peak power will be too high.
This is the photostability, whatever I have shown, it is in non-lasing condition.
Okay.
Okay, so just to compare that how much it is stable, it is all the data.
On biological applications, the fluence will be quite low that way.
Yes.
But if you are going for lasing applications,
photostability is not at all a problem because you are using it for a very low time.
Fine. Okay.
The only problem is for the long run, for the high average.
Any other question? Yes, Sachin.
Sir, as you mentioned, this dye stains the lipid droplets also. So, by chance, have you checked out like this dye also stains the naive lipid droplets or already matured lipid droplets also? So,
as it is going from ear to lipid droplets, so it's from the starting from the lipid droplets. Whenever it is generating, it is going to the lipid droplets and until the mature droplet also. So everything you can image.
Okay, so this will give the information about the lipid storage as well as the
Yes, yes.
lipid droplet biogenesis.
Biogenesis as well as storage, both you can get, yes.
Okay, thank you.
Yes.
Hello, sir. It's a very nice talk. Sir, my question was that when you substituting the body P with NF2, you said that it was NFB2, right? So,
PF2.
PF2. Yeah. So it was actually your singlet oxygen generation and as well as the reaction with singlet oxygen got down, right?
Got down, yeah.
And that paper also talks about the photodynamic action of that particular dye also, right?
No, not with that dye.
Okay,
with some other dye.
some other dye, right? Sir? Okay, sir. Okay, that's okay.
So, no other. Okay. Back. Come forward. Why you are so back?
You should not be sitting back.
It was a nice talk, sir. My question is like, did you see for any other dye modification where you are seeing the changes in color? You just mentioned that in ER it was green color and then later on it was yellow. You went for any other dye, like same changing phenomena is observing?
No, with any other dye, no, I didn't see.
So it is just with this modification only?
With this modification, yeah. Even if you place the same attachment with some other parts, with other part of the dye, it didn't show this aggregation. Only this specific, the two position, whatever I have shown, if you attach this molecule with that position, it is showing the aggregation, okay? Not other dyes.
Okay, is there any possibility like this changing color phenomena is not just binding with the lipid moiety or any other substance like biological substance which is present in the cell?
No, it's this color change is not for the binding with the lipid droplets, it's a change in the environment. So if in a cellular environment, water is there, so it is polar environment. But is lipid droplets, it is non-polar environment. So when the dye is going to the polar to non-polar environment, okay, it started stacking in the non-polar environment.
Okay, thank you very much.
Okay. Yeah.
Thank you for the nice talk. You had mentioned that the lacing efficiency of this dye is twice that of rhodamine 6G.
Yes.
But rhodamine 6G itself has close to 100% quantum efficiency.
Yeah.
So how can we get double the lacing efficiency from this?
Okay. So this extra efficiency is coming as I saw in the slides. These slides, its fluorescence efficiency is high, but if you can see there, triplet to triplet excitation coefficient. The part of the dye is going to the triplet state. In the lacing condition, that can go to the higher triplet state also. So this reduces the lacing efficiency also. So that is really low as compared to the rhodamine 6G, and also that rate of intersystem crossing is also low as compared to the rhodamine 6G. So all these factors means all together they enhance their lacing efficiency in the body P dyes.
Anybody else? No. So let me ask you one just curiosity driven question. So just when you use these dyes, newly synthesized dyes for imaging of cells, so what advantage do they have as compared to the already existing dyes which are used for these things? Any age over all these dyes, existing dyes?
Okay. So main advantage of this kind of dyes is, you can, as I told that you can do lot of chemistry. Okay. So whatever color you want, whatever attachment you can want to do. Okay. So whatever market available dyes, if you cannot do any molecular engineering. If you go to attach some other dye, some other ligand, some other anything, it's very difficult. But this kind of dyes are very easy to do their molecular engineering. If you want to make it mitochondria specific, you can make it lysosome specific by attaching different groups. This is the major advantage with this kind of dyes.
But now the existing dyes also this kind of specificity.
Yeah.
Some of the dyes.
Some of the dyes. But the interesting features of these dyes are using the same dye you can make all these all these features in the same die structure. You don't have to go for the rhodamine for mitochondria or for the lipid droplet for other dyes. So using the same dye structure, you can generate a lot of molecule for all different parts of the cellular system. This is the main important part. And another is fluorescence is so high. It's very useful for the imaging applications. So that is another major advantage.
Thank you very much. So let us thank Mulay once again.
Now I request Dr. Majumdar to present a memento to Dr. Mula, and I request Aparna to bring the memento to the dais. I request Dr. S.V. Nakhe to come to the dais and present a memento to our session chair, Dr. Majumdar. I request Priya to bring the memento for the present. Before we proceed further, I have an important announcement to make. The buses for banquet at Hotel Enrise will leave from this venue at 7:30. Now we will proceed for, we will continue with the ILA GBM, Indian Leisure Association General Body meeting in this very hall. I request the ILA ground floor. Yeah. So the ILA meeting GBM would be in the ground floor mini auditorium.